Good day, everyone. Welcome to Transportation Researchers Conference. This is track 5, session 1. My name is Mahmoud Mesbah, and I'm going to be co-chairing the session with my colleague Mariana Benoliel. Today we have 4 presentations. We introduce each presenter before the presentation. There will be 20 minutes for presentations and 10 minutes for questions and answers. You can type your questions in the chat box, and Mariana and I will go through the questions and ask them verbally from the presenter after the presentation. I'm a faculty member at Amirkabir University of Technology, or former Tehran Polytechnic, and an honorary senior lecturer at the University of Queensland. I have a background in civil engineering and transportation planning. I've got a PhD from Monash University in transportation, and my research interests are transportation modeling and planning, optimization of transport systems, public transport, and application of advanced technologies in transport. So without further ado, I go to the first presentation presented by Tao. Tao is a PhD student in urban and regional planning in the Humphrey School of Public Affairs at the University of Minnesota. His current research involves in the interaction between land use and travel behavior, pedestrian and bicycle safety, and the impact of transit on travel demand. He applies novel research methods such as machine learning in his work to explore the potential nonlinear relationship between the land use and travel behavior. Thank you, Tal, for your presentation, and the floor is yours.
Thank you for the introduction. Good morning, everyone. My name is Tao, and I'm currently a PhD student from the University of Minnesota. It's great to have the opportunity to present our research here. Today, my topic is the road less traveled. Does real transit matter? It's a work cooperating with my advisor, Professor Jason Cao, who is also in this room, and my colleague Xinyi. As increased travel demand results in many social and environmental problems, real transit has been deployed to mitigate vehicular travel demand and promote transit ridership in the US. The left plot here shows increasing travel demand in the US in the last 20 years. The total VMT in US in 2019 was 3.3 trillion trips, which is about 20% more than 20 years ago. The left plot here shows the increasing effort in building real transit in the US. In 2017, the total number of real transit system was 88, which was 70% more than 20 years ago. In the same year, the real transit ridership was 4.9 million passengers, which is also 70% more than 20 years ago. However, building real transit is not an easy task, and it requires high subsidies. This plot shows the green line in the metropolitan area, the Minneapolis-St. Paul Twin Cities metropolitan area. It was in construction from 2011 to 2014 and started to operate in 2014. The cost of this project is $957 million, which is about $80 million per mile. Another project is the Green Line extension. It is also in the Twin Cities. It is still in construction. Its budget is about $2,000 million, which is about $138 million per mile. So building real transit is not only expensive, but becomes more and more expensive. So quantifying its effectiveness is very important for policymakers to garner public support for real transit investment. Many scholars have examined the influence of real transit on the road traffic. Some of them compare the effect before and after the operation of real transit directly. Some use quota experiments or difference in difference. They compared before-after effects and also included treatment in the control groups. Generally speaking, the treatment group usually is area where the real transit could influence, while the control group is area where the real transit could not influence. The current literature, however, has two limitations. The first is that they do not account for the effects of confounding factors, such as transit supply and land use along the roads on road traffic. For example, when a real transit line is deployed in a corridor, the transit agencies will try to adjust the bus routes along the corridor or near the corridor to optimize the benefits of the whole transit system. And those changes in transit supply will also change the travel demand in the corridor. The second limitation is that field studies test whether the impact of real transit on road traffic changes over time. The real transit can generate new development along the corridor. Those new developments could result in an increase in trips to the corridor. And also, when the road is not congested, drivers might switch back to use the corridor again. Therefore, we raised the two research questions about the effect of transit on travel demand in this study. The first is, how does a light rail influence ADT of the road segments within its service area when accounting for the confounders? The second is, how does the influence changes over time? The method we applied in this research is also called experimental research design. We take the green line as a treatment and compare ADT of the road segments in light rail inference area and non-inference area before and after the operation of the green line. As being said before, the green line was under construction from 2011 to 2014, so we excluded those years from our research. We take the year from 2009 to 2010 as a before period, and took the year from 2015 to 2018 as the after period. Since we are pretty interested in the changing effect of the real transit on road traffic, we split the after period into two parts. The first is from 2015 to 2016, and the second is from 2017 to 2018. We also considered to control those potential confounders, such as land use, transit supply, and road classification. This plot shows the distribution of those light rail inference area and non-inference area in the study areas. This green line is the green line light rail in the Twin Cities, and the red area is the light rail inference area. Basically, it's a 1 mile buffer along the green line. So we take the road segments within this red area as those observations in the treatment group. The blue areas here are those non-inference areas. We take the road segments within those blue areas as observations in the control groups. We use the negative binomial regression to construct the models because the distribution of the dependent variables is over-dispersed. Specifically, we have two models. The first, model 1, examines the difference in vehicular travel demand before and after the opening of the green line. In this model, we have the variable ART to indicate whether the observation is in the treatment group or control group. And we have opening to indicate whether the observation is before or after the opening of the green line. And we have the interaction term of those two variables, which is also the policy variable we are interested in. So if this interaction term is, the coefficient of this interaction term is negative and significant, it shows that the opening of the green line reduces the vehicular travel demand of the row segments in the Lyreal inference area compared with those in the non-inference area. Model 2 shows a change in vehicular travel demand over the study period. So in this model, besides ART, we have two period variables to indicate whether or not the observation is in the targeting study period. We take the year from 2009 to 2010 as the reference point, so we do not include the variable in the model. We have two interaction terms, which also the policy variables we are interested in. Similarly, if those variables, the coefficient of those variables are significant and negative, it shows that the green line reduces travel demand on the row segments in the Lyreal inference area during the corresponding period, compared with those in the non-inference areas from 2009 to 2010. All right, let's see some results. So this table shows the results from Model 1, including the coefficients of the variables, the p-values, and the relative change. The coefficient of the interaction term between Lyreal and the opening is -0.2 and significant. So it means that after the opening of the green line, the ADT of the row segments in the Lyreal inference area decreases by about 18% compared with that in the non-inference area. So based on this result, we know that the green line reduces the vehicular traffic of adjacent road segments. This result is consistent with current literature and also consistent with increasing ridership of the green line. In 2019, the average weekday ridership of the green line was about 44,000, so which has already exceeded the projected ridership in 2030 by 10%. We controlled a lot of confounders, and most of them have significant relationship with ADT. For example, those three variables, road classification, they all have significant relationship with the road traffic. Those variables, land use variables, we include the commercial area, industrial area, institutional area, and the residential area. Among them, commercial area, institutional area, and the residential area, they all have positive relationship with the road traffic. And among the three variables, institutional variable has the largest effect. Industrial variable is negative correlated with the road traffic. This makes sense because the industrial land use generates fewer trips than other land use types. Transit supply has a negative relationship with ADT. It does make sense because transit competes with personal vehicles. This is the result from Model 2. Those two policy variables, those two interaction terms, their coefficients are both negative and significant. Specifically, the coefficient of the interaction term between year 15-16 and ART is -0.25. It shows that the ADT of the row segments in the Lyreal inference area decreases by about 22% in the period from 2015 to 2016, compared with the period from 2009 to 2010. And the coefficient of the interaction term between year 17-18 and LRT is negative 0.18. It shows that the decrease in the ADT of the row segments in the light rail inference area is around 16% in the period from 2017 to 2018, compared with the period from 2009 to 2010. We use this plot to show the relative change of ADT in the light rail inference area, which is induced by the light rail. This result suggests that the opening of the green line reduces vehicular travel demand on the adjacent roads during the first 2 years of operation, but the effect becomes smaller during the following 2 years. There might be 2 reasons for this. The first is triple of convergency. So if travel demand is reduced due to policy intervention, for example, telecommuting or transit-oriented development, this reduced travel demand will be offset by the demand switched from other modes, times, and routes. The second reason is that the green line increases property values and attracts real estate development along its route, such as apartments, retail stores, and restaurants. New development induces more people to travel to and from this area. We also estimated the effects of the green line on ADT using models without controlling for the confounding variables, and this table is the result. Generally, the effects of the green line would be substantially overestimated if we do not account for the influence of the confounding variables. For example, the estimated reduction of ADT in the after opening period is about 36% in this model, which is almost double the effect estimated by the previous model, which is 18%. All right, let's conclude our results. The first is the green line reduces ADT of adjacent road segments by about 18%. This finding emphasizes the important role of rail transit in travel demand management. The second is that while the green line reduces road traffic in the first 2 years of operation, the effect becomes smaller in the next 2 years. This decreasing effect might be because the land use induced by the light rail along the corridor and the travel demand switched from other routes and other routes and modes. The third is that it is critical to control for confounding factors such as road classification, land use, and transit supply. Otherwise, we are likely to substantially bias the estimate of the real transit effect. Generally, the transportation system benefits from rail transit in several aspects. The first is that rail transit is more attractive to auto users than bus services. By replacing regular bus services, the green line substantially increases the transit ridership along the corridor. Substituting the transit for driving reduces VMT and those related negative externalities such as traffic congestion, air pollution, and crashes. The second is that rail transit improves system efficiency. Because the opening of the green line, some travelers who used other routes or other modes of transport other than driving, they switched back to drive on the roads in the surrounding areas. But the capacity of the entire transportation system has increased, right? And we also know that this effect is decreasing. But if this decreasing effect is due to land use development induced by the green line, actually this is more desirable by the urban planners because it shows that the transit is effective in shaping urban form. Well, that's all for my presentation. Thank you very much.
Thank you very much, Tal, for the presentation. It was great to hear the results of your study on the Green Line in Minnesota. There has been a question from the floor. I'll take that first. Then I have also a few questions for you. Let me bring up the chat box. Yeah, it's from Alex Bigazzi, very next presenter. Is asking if whether the coefficients, interaction parameters of 1516 and 1718 were significantly different from each other.
Thank you for this question. So the reference point is the period from 2009 to 2010. So year 1516, year 1718, they are significantly differently from those reference points, but we did not check whether they are different from each other. Yeah, we do not check that. Yeah,
I think you had something to the point that there were different effects in those years, but not certainly checked that. Yeah, this graph. While you're here, I was wondering why you coupled those years and didn't go through year 15 and 16 separately.
So this is due to the availability of the data. The local agency, they detect those ADT about twice a year. So they might detect this road in this year, but they will detect another road in another year. So basically every road will have like ADT detected twice a year. So we in order to get more observations, we try to combine those years.
Right. I have a question about capacity efficiencies. I'll read the question. Rail transit only improves efficiency if there are sufficient travelers. Comparing the bus with 80% utilization and tram with 80% utilization, the rail system is likely to be more efficient. Yeah, that's sort of a fair comment. You want to comment on the efficiency of this rail LRT system?
The rail transit is likely to be more. Yes, actually, the rail transit is more efficient than the bus routes, the normal bus or the local bus. Do you think the economic downtown had a strong effect in the ridership in? So actually, we consider that part, and we did not include the downtown area in. So the road segment, we did not include the downtown area, the road segments in the downtown area in our study. We excluded that part.
Right. I can see there's a question on ridership, and can you comment on the frequency of this line for those who are not familiar with the area, and the headway frequency of this line and the possible ridership?
Where is the question?
I'm just asking the question.
Okay.
What's the frequency of this green line, and do you have any on the ridership values?
So the green line is about 10 minutes. So the headway is about 10 minutes. So it's about 6 an hour. most of the time. And the ridership, as I mentioned before, the ridership, the weekday ridership is about 44,000 in 2019.
That's per hour.
Yeah, that's daily.
Right. Right. So not a heavy ridership. Okay. I can see a lot of activity going on in the chat box, so I'm trying to catch up.
So
to obtain the efficiency sources, yeah.
So
have to obtain efficiency sources for these transportation systems. That's probably replying to another comment.
How you obtain the efficiency scores for these transportation systems? Can you explain more about what is efficiency scores?
Yeah, I think it was a comment on efficiency of different rail and bus systems, and there's a question on how to derive that efficiency, and then the answer is the rail may not be generally more efficient, but has a higher capacity provided for the users. On a slightly different topic, overall, can it be that the same framework can be used during the future years? Do you have data, especially during this pandemic? Did you have access, or are you planning to expand this for the effect of that on ridership during these years, this recent year?
So actually, we do not have the ADT for the road segments for during the pandemic, but we do have some other data from the Met Council, so which is the local planning agency, and we do use that data to test So it's not about real transit, but it's about how the road traffic changes in different socioeconomic groups, and how the general transit will influence this traffic. So we do have some research about that, but that is not real transit. It's just the general transit.
Right. And the source of data for all these years since 2009, was it consistent? The same source every other year, collected traffic volumes from all roads?
No, it's not consistent for all the roads. Some roads has observations in 15 from 2015 to 2016. Some roads have observations from 2017 to 2018. Actually, they are not very consistent.
Okay.
Not very consistent.
Right. It's good to know. Thank you very much, Tao. So Jason was saying that the data is from the same source, so probably expecting a fair comparison across different years. That's how I can read Jason Carl's comment. Can you respond for the last question? There's Dan von Jennings asking about what type of model was used, probably repeating what you've already presented.
The model here, so is ADT, so it's auto traffic. It's auto traffic or vehicle traffic detected by the local road agency.
Yeah, and a general linear, what was it, binomial regression model was used. Yeah, negative binomial regression was used. Yeah.
Oh,
Yeah,
so this
okay.
model, sorry, negative binomial, sorry.
Yeah. Thank you very much, Tal, for your time. Thanks all to all the audience for the questions. We'll have our next presenter, and I'll give the floor to my co-chair, Mariana, to introduce the next presenter.
Our next presenter is going to be Alex Bigazzi. Dr. Bigazzi is an associate professor at the University of British Columbia in Vancouver, Canada, and has a joint appointment in the Department of Civil Engineering and the School of Community and Regional Planning. His primary areas of research include motor vehicle emissions, active transportation, and emerging human-electric hybrid vehicles. So I'll give the floor to Dr. Bigazzi if he wishes to speak. Thank you.
Thank you very much. It took me a second to find the unmute button. Can everyone hear me and see the slide okay?
Yes.
Great. Thanks. I'm looking forward to this presentation today because it's something I've been working on for the last few years, and I think it dovetails in nicely with some of the conversation in the chat at the end of the last presentation about comparing the efficiency of different modes of transportation. So in this, I'm going to be talking about the marginal emission factors for public transit, and specifically here looking at relationships of marginal emissions specifically with urban scale and density. But specifically, I'm going to set it up a little bit with just kind of making the case for the importance of marginal emissions, and then we'll get into the specific details a little bit after that. So when we're talking about transportation and sustainability, not always, but very often we're talking about either pollution emissions or greenhouse gas, local pollution emissions or greenhouse gas emissions. Sometimes also energy consumption, sometimes fuel consumption, but these tend to be kind of key outcomes of interest in the sustainability sphere for transportation. And usually we'll be looking at some sort of figures like these. And I pulled up a few arbitrary ones, one from the Sightline Institute, and one from the CBC, which is our local or our national news service here in Canada. And the examples here are comparing different modes of transportation, and we're looking at average greenhouse gas emissions per passenger mile. And that's quite often the way it's presented as the average emissions rates or average emissions factors across different mode options. So for example, in the conversation before, the relative efficiency of bus and rail might be presented as average emission factors. And you'll notice in these, a really important aspect of it is, of course, the occupancy of the vehicles. So for example, here, a car with 1 passenger versus a car with 4 passengers has a factor of 4 different emissions factor. Same thing, transit buses, whether they're a quarter full or 3/4 full, have vastly different emissions rates. So the occupancy of the vehicles is really important. But here, what I'm more interested in is the metric itself. So when we talk about average emissions, they're very easy to calculate. If we have a bus that's emitting 1,000 grams of CO2 per mile, we have 5 people on the bus, we just divide one by the other, and we get 200 grams of CO2 per passenger mile or per person mile. Similarly, if we have a single occupant vehicle emitting 200 grams of CO2 per mile, and we have a single person in that vehicle, then that vehicle is also emitting 200 grams of CO2 per mile. And so in this scenario, you might say that these two modes of travel, a bus with 5 people or a car with 1 person, have similar impacts in terms of the environmental impacts per passenger mile of travel. But if we think about how we're going to use that information, and in particular from the traveler's perspective, if they're trying to decide what are the environmental impacts of their personal choices, and then zooming out as transportation professionals, if we're trying to decide what kind of policies we want to enact in order to encourage people to use one mode of transportation or motivate them to use one mode of transportation over another, what we're actually interested in is the marginal emissions, not the average emissions. So the marginal emissions is how the total emissions change with a change in usage of a given mode or a given system. Right, so when we add an additional passenger trip or passenger mile to the system, that's not going to increase emissions by the average emissions rate, right? So even though a bus with 5 people and a car with 1 person might have a similar average emissions rate, their marginal emissions rates are probably going to be quite different. And it's really those marginal emissions that are more relevant for decision making, for developing sustainable transportation strategies, and for informing the public. Now, this is something that has been well understood in the energy sector for quite some time. And so when we talk about the climate impacts of increasing electricity production and consumption, for example, for conversion of the fleet to electric cars, we don't make the assumption that a great expansion of electricity production is going to have the same kind of production profile and impact profile as the existing energy consumption, right? And here's just one example I pulled from that kind of literature on the environmental impacts of energy production. And you can see in this context, they're forecasting that the energy mix will transition from coal to natural gas as the total amount of energy production increases, right? So marginal impacts of energy are going to be different from the average impacts of energy. But this is something that we don't really talk about in the transportation sector outside of getting marginal emissions factors for electricity. So in a recent work, we developed a analysis framework to estimate or to calculate marginal emission factors as a fraction or ratio of average emissions factors. So if you have an average emissions factor, this is a way to convert it to a marginal emissions factor using 2 key parameters. And again, the average emissions factor is just total emissions divided by passenger miles traveled or person miles traveled, whereas the marginal emission factor is the change in total emissions with the change in person miles traveled. And there are 2 key parameters here in the equation shown on the slide, and there's the reference if you'd like to see the details for the development of this. The first is the elasticity of vehicle miles traveled to passenger miles traveled. So it's essentially the percent change in vehicle miles with a given percent change in passenger miles. So if you double the passenger trips and that doubles the vehicle trips, then you have an elasticity of 1. Conversely, if you increase your passenger trips on your system without increasing service at all, so the same number of vehicle trips, then you have an elasticity of 0 here for this. So this is basically what is the relationship between vehicle and passenger travel. This other term here is the elasticity of vehicle emissions rates to vehicle occupancy or load. So this is essentially accounting for primarily the mass effects of increasing numbers of people on the vehicle increases the fuel consumption and then consequently the emissions. But it also accounts for a bit of an operational effect because, for example, in a bus system, higher passenger loads tend to lead to longer dwell times and more frequent stops. So you get a slight increase in emissions rates with more people taking the bus as well. So using these 2 key parameters, if we estimate these, then we can calculate marginal emission factors as a fraction of the average emissions factors. Now, both of these elasticities are expected to be between 0 and 1. So this whole term here will be between 0 and 1. So the marginal emission factors can range anywhere from 0 to 100% of the average emissions factors. And in that work, we used some aggregate data from all over the US to estimate. First, on the left here, what we're looking at is that marginal to average emissions factor ratio for different travel modes. Again, this is aggregate data for the whole country. And what we found is that, as you might expect, private vehicle travel has a marginal to average emissions factor ratio at 90 or above, 90% or above. So essentially what that means is additional person trips in private motor vehicles tends to be accomplished with additional private motor vehicle miles traveled. Conversely, for different types of transit, we saw lower ratios, which means that a portion of additional passenger trips on transit is accomplished by additional vehicle miles traveled, but less than proportional increase to the increase in passenger travels. And then if we take these ratios, and we apply them to average emissions factors by mode, again, national data for the US. Here on the right, we're looking at average and marginal emissions factors in mass of greenhouse gases per passenger kilometer in this case for different modes of transportation. And you'll notice, for example, for bus transit, the average emissions factors are fairly high because the US tends to have low bus ridership, low bus loads in general. But the marginal emission factors for bus are much lower because when bus ridership increases, the vehicle miles traveled by bus doesn't increase by nearly as much versus private vehicles where the marginal and average emissions factors are much more similar. Rail transit has a higher marginal to average emissions factor ratio than bus transit does, but the average emissions factors are lower, and so the marginal emission factor is still lower if we compare bus and rail. We also looked a little bit by city. This is the energy intensity in terms of BTU per passenger kilometer reported in the National Energy Data Book. And on the left, you have average intensity, energy intensity for different light rail transit systems by city. And then we calculated that marginal to average ratio. And what you see on the right is a significant reordering of the energy intensity of these different rail systems from a marginal intensity perspective versus an average intensity perspective. So, so a lot of that is to make the case of the importance of marginal versus average emissions and the need to look into this further. And it's particularly important for transit because the difference between marginal and average emissions factors is very large for transit and larger than for private travel modes. So the question here is we wanted to dig into the transit one a little bit more and look at just starting with the basic fundamental urban scale characteristics of population, area, and density. So we know that transit is more efficient in higher density locations because you can move more people more efficiently by transit if you have higher density. So we wanted to look at how the marginal emissions factors relate to average emissions factors in the context of changing urban scale characteristics. And in particular, are the effects of urban scale on the sustainability of public transit different if you look at it from an average versus a marginal perspective? So to do that, we did transit system level estimates of marginal and average emissions factors for urban areas. We estimated those two key elasticities. So the first one is the elasticity of vehicle to passenger miles traveled. For that, we used US Federal Transit Administration panel data, a data set with which many of you are probably familiar. We aggregated it to 376 urban areas over the 27-year period. And we used a log linear two-way fixed effects panel data regression model where we had urban area and time fixed effects. And then we had this parameter here, beta, which would give us our elasticity value, as well as an interaction term here, where the interaction is with an urban scale variable. And because of the correlation amongst these urban scale variables, we just tested them one at a time. So we tested population, land area, population density, the ratio of those two, and transit system extent, which is also reported in the FTA data set. And so our elasticity estimate is the beta parameter plus the interaction term for the scale of a specific urban area. The other elasticity value, we unfortunately don't have direct data to estimate it. So for that, we assumed certain values based on the literature. So we found about half a dozen studies for these modes that have empirically estimated fuel consumption or emissions based on passenger loads. And so we have elasticities of 0.16 for bus, 0.05 for rail, and 0.10 for other transit. And so what this means is that as you increase passenger loads on bus, it has a bigger effect on the emissions rates of bus than increasing passenger loads for rail, which makes sense because the body mass is a lower portion of the total mass for rail cars than for bus cars. And also changing rail ridership has a smaller operational impact on rail fuel consumption than changing bus ridership, because rail's always making the stop, whereas bus isn't always making the stop. And then finally, for our average emissions factors, because we weren't focused on that, we just used average national data for per VMT emissions factors from the vehicles, which is a limitation, but we're really focused on this differentiation between the marginal and average emissions factors. So first, looking at that first elasticity value, the elasticity of VMT to PMT. Here what we're looking at is the estimated elasticities in the 5th to 95th percentile range of each of these urban scale variables. So the 5th to 95th percentile population, urban area, density, and route extent. And we're dividing it up over 5 transit modes as defined or aggregated up from the FTA data. So they defined a couple different rail services, so we've aggregated those. A few different bus services, we've aggregated those. And what you're seeing in the bars here is the range of elasticity over ranging urban scale variables. All of these interaction terms were significant at a 0.05 threshold, and they were all positive effects, meaning the elasticity of VMT to PMT is higher in larger cities, both by population and land area, and it's higher in higher density cities, and it's higher in cities with larger transit systems. So in other words, VMT is more dynamic with changing PMT in larger cities. And this is going to be related to, and now we're moving to hypothesis range, unused capacity. So larger cities have less unused transit capacity. Differences in the proportion of choice versus captive riders on the system, differences in operational constraints, and differences in budget constraints as well. If you look at where transit systems in different sizes of cities get their revenues. In particular, smaller cities get a larger proportion from non-fare box sources. So again, in all these, larger cities have more elasticity of VMT to PMT, and that, if you look at the equation, leads to larger marginal to average emissions factor ratios, meaning closer to 1. We also see that urban area scale has a bigger impact on bus elasticity than for other modes, and we see that bus and other transit are much lower than rail, demand response, and shared ride, which are more in the 80 to 90% range. Meaning rail transit VMT increases closer to proportionally with passenger travel than bus transit VMT, for example. So moving this on to taking those elasticity values, combining it with the elasticity of emissions rates to occupancy, we get our estimates of the marginal average emission factor ratios, the actual average emissions factors, and marginal emissions factors. And what I'm showing here is the elasticity of each of these values to our urban scale variables. And this is just for bus emissions, which are more responsive to urban scale than the other transit modes. Okay, and so what we see, because of the elasticity values shown here, we get marginal to average emissions factor ratios that increase with population, area, density, and route extent. So all 4 of these elasticities have positive signs, meaning the marginal average emissions factor ratio increases with urban scale. But as we know from elsewhere, average emissions factors decrease with urban scale because transit service provision is more efficient in larger, higher density cities. Okay, so these two actually have kind of contrasting effects on the marginal emissions factors. And so we have average emissions factors falling, marginal emissions factors increasing as a proportion to average emissions factors, but the average emission factor falling is a bigger effect, and so marginal emission factors still decrease in larger, higher density cities, but they decrease by less than average emissions factors. In other words, average emissions factors are about 50% more sensitive to urban scale than marginal emissions factors. This is another way of looking at it. Here are all 376 urban areas split up into population tertiles, and we have average and marginal emissions factors showed as box plots for each. So the orange boxes are the average emissions factors, and the green boxes are the marginal emissions factors. This is for low population tertile, the medium population cities, and the highest population cities. And this is another way of essentially visualizing the information in the last slide. We see that marginal emissions factors are much more consistent across city size than average emissions factors, which fall more than marginal emissions factors fall, even though marginal emission factors do fall a little bit as well. And you'll notice, of course, also that these box plots are really wide, and that's because urban scale is not the only influence on the efficiency of these systems, right? So the bus occupancies are influenced by a lot of other factors, and so you get a wide distribution at various population tiers, but still you can see the differences between the marginal and average emissions factors. So as we get into smaller cities, the average emissions factors increase much more than the marginal emissions factors. And this is actually quite important if we're going to look at transit as a competitive sustainability mode to private car travel, because typical private cars, of course, it depends on the type of car and occupancy load, but we might see emissions factors in the range of 200 to 300 grams of CO2 equivalents per person mile traveled. And so quite often this private car travel emissions factor will actually be between the marginal and the average emissions factors, meaning that bus will be less sustainable from an average emissions factor perspective, but more sustainable if we actually look at it in terms of marginal emissions. So to wrap up, marginal emissions factors do decrease in larger cities. So even from a marginal perspective, larger cities provide public transit more sustainably, but not as much as for average emissions factors. And public transit, especially bus, is more efficient when we shift to that marginal perspective, and it's really especially important for bus transit in small cities, which tends to have low ridership and so high average emissions rates. And so someone might say, well, if you look at the average emissions rates for bus, it's actually higher than if I just drive my own car, so why would I take the bus? Well, that's the failing of the average emissions factor, so we really need to move it to a marginal emissions factor. And again, high urban density supports transit efficiency from both those marginal and average perspectives. And hopefully this will kind of help us move towards this marginal perspective when we're assessing the sustainability of our transit systems. Now, there are a number of limitations to this. Again, we're focused on this marginal to average emissions factor comparison. So this was not detailed estimates of emissions factors by cities, and there's a lot of important local characteristics that influence emissions factors. You know, vehicle types and age, fuel types, terrain, climate, weather can make a big difference, various operational and maintenance constraints. So the important takeaway here is, again, the marginal to average differentiation and not specific average emissions factors. The FTA data set, if you've used it, you know there are a lot of data errors and omissions. It isn't 100% reporting for the entire country, but it is a very useful large data set for this type of analysis. We still have limited information about that elasticity of emissions factors to occupancy, so that needs to be researched more, especially for rail transit. There's more on bus transit. And so these are important limitations, but we find that they're unlikely to affect the main findings, which is this differentiation between marginal and average emissions factors and how they relate to city size. So happy to take questions now, and if anyone would like papers, please email me. I'm happy to send them to you and answer questions in another venue as well.
Okay, thank you, Alex, for this wonderful presentation. I hope you're all hearing me properly because I am with connection problems since the beginning of the presentation, actually. But I have some questions here for you. One of them is from Jason, I think, whether marginal emissions change depending on the additional passenger mile change in the supply of transit. Is that right? And the other one from Mahmoud, how do you see the role of capacity in MEF? Do you assume that transit systems can accommodate the additional ridership? I would like you to answer these two questions if you can, please.
Yeah, Sorry, I'm pulling up the chat right now because you broke up a bit right during the first question.
Which one didn't you hear? Sorry.
The first one from Jason Cow, whether marginal emissions change depending on whether the additional passenger mile changes the supply of transit.
Yeah.
Yeah, so so in the calculation of marginal emissions factors, that elasticity of VMT to PMT is the relationship between passenger ridership and transit supply. Now, what's not differentiated here is, so this is going to be a two-way causal relationship, and it is really hard to differentiate that with a temporal data set, because transit planning is anticipating some changes and expecting some changes in ridership, and so in some ways the change in supply is responding to ridership, and in other ways it's driving ridership. So what this elasticity reflects is the way that those two have changed in the past for a specific system. So specific system will have changing ridership and changing VMT over time. And so the idea here is what is the pattern in the relationship between those two in terms of the elasticity or percent change in each. Hopefully that answers your question. What was this? And then the second question was, can you repeat the second question for me? Sorry. I'm not good at queuing them up in my brain.
Constantly muting and unmuting, or else I'll cut you. I lost that. How do you see the role of capacity in MEF? Do you assume that transit systems can accommodate the additional ridership?
Yeah, so again, for the calculation of the marginal emissions factors, you don't actually have to assume anything about the capacity. You're assuming that the marginal emission factors reflects the historic change of VMT with PMT in a given system. So it accounts for how that system has accommodated additional ridership, typically with increasing capacity. And so the assumption is kind of that the historic trends will predict future changes in VMT in response to changing PMT. Hopefully that clarifies. And I see there's a lot of other chats here that'll take me a second to catch up on, and I appreciate the back and forth.
There's an interesting question here, which I would like to see answered, actually. What are the implications for planning and policy making of this?
Yeah. Okay, so at a fundamental level, we've been talking about public transit as a sustainable mode for a long time. This supports that public transit is sustainable. So essentially, this isn't saying any fundamental change in whether or not public transit is a sustainable mode, but it does address this, maybe not for everybody, but for me, it's been this nagging kind of thorn in the side of public transit promotion, the fact that the average emissions rates are higher. And I've heard people bring that up as an issue before. And so hopefully this provides a structured kind of analytical way to change our framing of the climate impacts of different modes of transportation, and ultimately, what I'd like to see is, if we go back to those first images like this, that we're making these types of figures and calculations and comparisons based on marginal emissions factors and not average emissions factors. It also is something that I would suggest. Not just large-scale analysis consider, but also transit agencies can be looking at this as well. I think most transit agencies have sustainability report cards that they put out in some way, and I think this should be part of that presentation to the public. So not just what are their average emissions impacts, but what are their marginal impacts as well. Yeah, so I see Kara Kockelman has just put up a question about average loads. Yeah, you're absolutely right. It's on the order of magnitude of single-digit passenger loads for bus systems across the U.S. and Canada. It's higher in Canada a little bit. And of course, this is massively higher in big cities where we tend to focus, right? So, if you're doing this analysis in any of the big cities, you're going to get much higher loads. But when you zoom out to the whole country, the average loads are on the order of, and I don't have it right in front of me, but on the order of 10 or 8 to 10, yeah. How does service frequency influence MEF? Was another question. Service frequency is part of that elasticity. So this doesn't differentiate whether the VMT is increasing. It's just VMT, regardless of whether it's more buses on the same routes or longer routes or additional routes. So it is a high-level analysis for sure. Another great question about operating emissions versus life cycle emissions. It should definitely include life cycle emissions, and this is one of those inconsistencies in our accounting, is that I think most of the better life cycle estimates that are coming out are using marginal emissions factors for electricity production, but not using marginal emissions factors for the actual operations side. So we should be using life cycle emissions, and it should all be from a marginal perspective, in my opinion.
Thank you. Does anyone have any other questions that you would like Dr. Bigazzi to answer? If not, I think we can move on, and I'll give Mahmoud the floor, please. Thank you.
Thank you all very much.
Thank you,
appreciate the opportunity.
Thank you. Thank you very much.
Yeah, thank you, Alex, for the inspiring presentation and reminding us that the public transport is a great way to go. The next presenter is the co-chair herself, Maria Ana Benoliel. Maria Ana is a second-year PhD student in SERS department at Instituto Superior Técnico in Lisbon, Portugal. Mariana has a master's degree in environmental engineering with a specialization in environmental management and sustainability, and is currently a scholar from MIT Portugal program. Her primary field of research regards the improvement of railway stations towards sustainability. Thank you very much, Maria, and the floor is yours.
Thank you for having me here in this wonderful conference and hearing what I have to say. I am going to present to you something that I am working on my PhD, which is a decision support tool for the optimizations of railway stations towards sustainability. I am presenting to you a PDF because the PowerPoint just jammed. So if you cannot see, please tell me, okay? So first I'm going to make a little bit of an introduction for you to understand the context of my research. Then I'm going to move into explaining the methodology and case study, and then to future work. So for a little bit of context, so nowadays sustainability concerns are higher in the transportation sector. For example, in the European Union, 1/4 of the greenhouse gas emissions comes from this sector. So the tendency is to adopt greener and smarter mobility. On the other hand, mobility patterns have deeply changed. So people are wanting more efficient transport, more connected transport, more safer and accessible modes of transport. So the challenge here is to improve mobility, to address these parameters, but also do it with less resources, less energy consumption, and less emissions. So rail, because of its characteristics, is being regarded as the backbone for this sustainable transition. So there is a need to shift from road to rail, being freight or passenger rail. In my case, I am studying passenger rail, so this is what I'm going to focus on in this presentation. So how do we how do we shift from road to rail in case of passenger rail? We can do this several ways. One of them is by, of course, addressing the attractiveness and comfort of rail traveling. We can do this by reducing traveling times, reducing waiting times, improving the efficiency of transportation, but also improving vehicle comfort and, more importantly, station comfort. If you think about this, stations are the first and last mile of rail traveling. So if you improve the comfort of the passenger who pass a tremendous amount of time waiting for their trains and also passing through the stations, if you increase the comfort and you increase the attractiveness of these stations, you are increasing the attractiveness of traveling by rail from the first to the last mile, if you combine it with the vehicle comfort and the traveling times and all the things that I've talked about previously. So it's very important to ensure that lighting, indoor environmental quality, noise, safety, security, all these issues are addressed in decision making when improving or rehabilitating or constructing railway stations. This is a nice example, Atocha railway station in Spain. I absolutely love this station. I've never been there, but I like it because it looks very comfortable and looks very bright, and people are clearly enjoying their time in the station and waiting comfortably for the trains. So green station concepts have been rising in the European Union and outside the European Union as well, so all over the world. But these decisions that I'm talking about of improving the sustainability of railway stations or improving the comfort of railway stations are very difficult decisions to make because they depend on the context in which railway stations are implemented. And the two examples that I bring you here are examples of two model green stations, one in Germany, the one on the left, and the one on the right in Japan, Utsuya stations. And they are examples of what I am trying to explain to you, because Germany and Japan are very different countries in dimension, in sustainability priorities, in user needs, in mobility patterns. Economic and regional context is also different. So, of course, decisions and solutions that are going to be implemented at the stations are going to be very different from one another. And so the context is very important in this case, and decision making is very difficult and time consuming. This is just to exemplify what I am talking about. So if you look, for example, at water harvesting, in Utsuya, you have two types of water harvesting. One for green infrastructure, and for green infrastructure here I am referring to green facades, green walls, and green roofs, and the other is through pervious pavings, so pavings that let water run off. And in Capernaum, you only have water harvesting through the green infrastructures that I previously mentioned. On the other hand, for example, in Utsuya, you have energy storage systems installed at the stations, like solar batteries and solar cells, but in Capernaum, you do not. So as you see, dimensions, context, legal frameworks, construction needs, construction details, and also user needs and other things deeply influence decision-making. And so decision support tools in this context are very useful tools to help us understand to which way are stations sustainable or not, and to which way we can improve them and how we can improve them cost efficiency and according to context and according to stakeholders' needs. Now, there are several types of decision support tools. Two of them that I would like to talk about are firstly certification schemes, and secondly assessment tools, which I'm going to refer to further on. So certification schemes have been widely used across the world, mainly in the building sector, but some of them, like BREEAM and LEED, have also been applied to railway stations. So these certification schemes help us understand to what extent is a station or a building sustainable. So, and what are the critical points for improvement when looking out for sustainability? They grade stations according to their level of sustainability based on a set of criteria or parameters that are previously established on, for example, water efficiency, waste management efficiency, energy efficiency, noise, emissions. All of that is considered in certification schemes, and buildings that they assess are graded based on their positive or negative contribution to these parameters. But they are limited to that. They just assess to what extent a given building is sustainable and what are the critical points. They do not go further into the analysis of which improvements can we actually do and how these improvements may change the grade or the sustainability level of the station that we're assessing, nor do they help us find the best fit solution, which is what ultimately what we want with an efficient and quick decision making. Assessment tools, on the other hand, have also been widely used in buildings, some of them in non-residential buildings, and they help us assess the current sustainability, also model alternative scenarios, and do a little bit of cost analysis to see which scenarios are more cost effective. But to the extent that I have read so far, these kind of assessment tools only focus on energy and indoor air quality. They do not go deeper into analyzing, for example, the materials management or the waste and water and noise management and parameters. On the other hand, they are also not tailored for the railway building specifically. So we would have to adapt them so they would fit into the context that we want. So again, we have the context problem. There is, in fact, an assessment tool that was developed by the European Union, which is Station Quality Management System, which is the one on the right of the table there that we have here. And this quality management system helps to assess, certify, and model alternative scenarios in a range of parameters much more wide than the one of the assessment tools that I previously talked about. But it doesn't help us with cost analysis of these improvement scenarios, nor does it help us finding the best fit solution. So analyzing it based on context, cost, and stakeholders stakeholders' opinions to see which one is more cost beneficial and more context fitted. So what SUStation actually does is it assesses, it certifies, it helps us see, it helps us compare an alternative scenario that the user inserts with in regards to the baseline scenario of the station as we have it. But it doesn't help us see which one of the alternative scenarios that we are modeling is the best one in that case, to apply in that case. So the most cost effective and cost beneficial. And it's in this sense that I am developing the methodology that I show to you here. So as you see, it's very straightforward. The methodology is very simple. Well, the layout of the methodology is very simple. First, you start with the analysis of project data. What I call project data is the data that is going to give us the context that I have been talking about on and on and on during the presentation. Then we move on to assessing the current sustainability of the station based on 4 categories that I'm going to develop further. And then we can proceed into modeling and analyzing the scenarios for improvement, or we can stay and have a building performance simulation and diagnosis and a sustainable performance grade. So, as I said, first we have the qualitative and quantitative assessment of the context information and of the data from what I call the level A, so the sustainable performance assessment on non-traction energy, noise, indoor environmental quality, safety, security, and a range of parameters, which I am also going to develop further. And then we have the modeling and the analysis, the multi-criteria and cost-benefit analysis of the scenarios that we wish to implement for improvement at the station, based on the results from the previous assessment that we've made. So going a little bit deeper into each of the models that I've talked about, First, as I said, we have the gathering of context information, being information on the station building or information regarding the regional context, economic context, political context in which the station is implemented. And this context is going to help us decide which one is the best fit solution for our station at the last level of this analysis. And then we moved into assessing the current sustainability of the station based on 4 categories: resources, final energy, infrastructure, and health and well-being. So resources analyzes the management and efficiency of waste, water, and materials at the station. The final energy is basically the assessment of the management and efficiency of non-traction energy, and this is very important. I do not go deeper into traction energy in this case because we are talking at the station level, so I do not consider the traction energy. And it considers for the analysis parameters related to supply, consumption, and sustainable approaches to reduce consumption at the station. On the other hand, in infrastructure, we go into the construction and integration details. Integration here is urban integration. So how is the station integrated into the urban environment? Is it accessible? Does it have connections with public transport modes? How is connectivity done? Etc., etc., etc. And construction is also related to materials. So it goes a bit deeper into the materials that are used and how bioclimatic design is applied to the station building. Then for health and well-being, we have 2 types of assessment: comfort and safety and security. Comfort analyzes acoustic comfort, environmental comfort, and also goes a bit into the perceptions of people of this acoustic and environmental comfort, thermal comfort, lighting levels, if people feel or not safe at the station, so safety and security in this case. Then, as I said, we can stay, and sustainable performance grade is going to be delivered based on the performance of the station in all these 4 categories that I've talked about. A little bit like what happened in Sioux Station. So based on the criteria, on the grades from the criteria that were analyzed for each of the categories, a sustainable performance grade is going to be given to the station. And then we can proceed into the analysis and choice of improvement scenarios. So in here we can create several scenarios. And then these scenarios are going to be assessed through the assessment categories that I've just talked about. And another grade is going to be produced. And then we can compare that grade to the baseline scenario and see which of the scenarios are best graded in a ranking of scenarios. And then these scenarios that were best ranking, for example, 2, think about 2 that were graded 5, for example. We do the cost-benefit and multi-criteria analysis and see which one is more feasible for our context, based on our context information and on the context in which the station building is implemented and constructed. And then we can choose the most sustainable and cost-effective scenario and cost-beneficial scenario, of course, to improve our station. Now, the question here is, how am I going to model this and how am I going to make sure that this methodology really works? This is simple. I'm going to choose a case study for it. I've already chosen this case study, actually. It's going to be held in Entre Campos railway station, which is a very central station in Lisbon. So here in the picture, you see a 5 meter to 650 meter radius from the station. You can see that it's close to a lot of residential buildings and also to a lot of business clusters. So what you have there in very tiny letters is several agencies that are placed nearby the station, some governmental agencies, some cultural spots, and others just companies that work nearby. And then you have here in the image, you can see that it's also within a walking distance from 2 major green spots. So in there where it says 20 minutes, I can assure you it's 10 minutes walk. So Google Maps made a mistake because I actually live nearby the station, so I know that it's 10 minutes walk, and the other is 6 minutes walk from two big gardens where people go to walk the dog, to cycle. So this is a major spot, and it has a major distributional role within the city and a strong intermodal connection with public transport and active modes. But this station is also structurally very deficient, and it has a lot of issues concerning comfort and safety of passengers. So as you see, it is a very important station within the city, but it's not very well developed in terms of what it is, the building integration, and also the safety, security, and comfort of the passengers within the station. So it makes a nice case study for testing the methodology, which aims to assess the current sustainability status, model and test the feasibility of improvement alternatives, and choose the most suitable solution for improvement within the station. And this will help us to implement the sustainable principles in the life cycle of stations and adopt a cradle-to-grave approach to decision-making, also reducing time and costs associated to it and increasing resiliency and efficiency of applied solutions, and also working towards what I just said, which is to improve the traveling attractiveness from the beginning until the end of the railway journeys. Some future work. So the future work here should be based primarily on the short term, on the developing of field research and case study, which were interrupted, unfortunately, by COVID. So we were starting to do our data collection and our stakeholder interviews when the state of emergency was declared in Portugal, or a bit before. So we had to stop it abruptly. So right now we are waiting for things to get a bit more stable to continue with this work. And meanwhile, we are developing level A and level B analysis. So now we are defining the standards criteria and weights in which level A is going to be defined. And then we have to move on choosing the best technique or combination of techniques for multi-criteria analysis, and also adjust the assessment multi-criteria and cost-benefit analysis frameworks so that this could really work properly and be implemented into the case study. But this is a very early stage research of the doctoral thesis, so right now I cannot give you any further details. But I am open to questions, more simple now or more complex, by my email, or if you have any other suggestions that you can give me for my research, I would also be very much happy if you could share them with me. Thank you very much for listening, and now I'll be very happy to answer your questions. Thank you.
Thank you, Mariana.
Just stop sharing the screen.
Okay. People might ask questions from your slides, so you might keep that. I just want to start with a question on your assessment framework. Mm-hmm. With assessing the sustainability status, do you think that every criteria should be assessed separately, or there are given thresholds for certain criteria? For example, there should be a minimum level of safety or minimum level of energy consumption that should be passed before we go to this sustainable level, and we can consider that station in this sustainability framework.
Yes, yeah. Definitely. So can I answer? Yes?
Sure.
Okay. So definitely, this is a very interesting question. Of course, we have to give a positive or negative grade, as I said, to the station or to the parameter that we're analyzing. Of course, we should have some standards that we are going to have. So some thresholds of sustainability that we are going to have. Energy, for example, energy consumption cannot go, as you said, above a certain limit, or for example, acoustic comfort can also not go above a certain limit, you see. But this is also related to the context, because in several countries, the legal frameworks are different. So, for example, you can say that above some kind of degree level of noise, people are not, it's not environmental pollution if you have it. Let me just rephrase this because it was weird. If you have a noise level, a legal framework that tells you which noise levels are actually noise pollution, I cannot simply tell that below the limit that they are legally set, it's not sustainable. You see, I have to go through the legal frameworks. So I think that those thresholds are going to change a bit according to context. In some cases, like for example in noise pollution, but in other cases we can define our own thresholds, and we can see also if people are actually percepting below limit noise levels, because people can. I'm talking about noise because it's a nice example of what I'm saying. So if you are in a station where you say, okay, this is below the legal level, so we're cool. But if you go and talk to a person that lives nearby the station and say, I can't stand the noise, this is not sustainable. Because something that I haven't referred to in the presentation, but that is very important, is the social dimension of sustainability, which in my opinion is very disregarded when you're certifying or assessing sustainability in some cases. So you really have to listen to the opinions of people, and this is something that I'm going to really focus on in this methodology, because if people say that they hear more noise than they are supposed to, but legal frameworks say it is below the limit, in my opinion, it's not sustainable, you see? So we have to work with stakeholders, all of them, to see which kind of threshold we are going to say that is sustainable or not. So not just considering legal frameworks, but also considering the opinions of stakeholders. And this is how I'm going to work in this methodology. I don't know if I answered your question, but
yeah, there was a follow-up question on the economic and the social aspects of that. I think you touched on it based on your noise example, but do you want to take a look?
The concept on sustainability consider the absolute on environment, society, and economic. We will consider the impact that the station causes on aspect of social contribution or economic growth or something like this. Yes, definitely. Yes.
Yeah. Probably one last question is about data availability. Do you think that's going to be an issue in your framework? Does your framework need access to very detailed data, such as built maps of the station, which could be not be easily available, or any other type of data?
Yes, and this is one of the things that I'm following up right now, is the question of data, because data, of course, you also have the problem with the data sensitivity. So some of the data might be confidential, of course, and I understand that. And so one of the things that I'm really working on is trying to achieve the amount of data that I need without jeopardizing, of course, the confidentiality of data, and taking into account that this is a huge amount of data, and that I would have to select the data that is more important. But we are also following up on that and see which of the data is more important, so that we can also manage the methodology. Because in some cases what happens is that methodology are so full up with data that they do not work, because you need a lot of data to input, and the amount of time and the amount of money that you waste just collecting the data throws all the other time and money that you need to implement the rest of the methodology. So what we're going to do here is we're going to see which of the data is more important for context, so which one gives you the general and big picture, an important picture of what is happening at the station, and follow up on that. And that is what is going to be important for our methodology. Because of okay.
Thank you very much, Maria. I think it's time to move to the next speaker, because I don't see any. There's
a question, sorry, from Sasanka to me. privately, yeah, because it's private. Towards sustainability, are you also trying to minimize waste from the stations? Yes. And I'm sorry to follow up on this question because this is a very interesting question, considering that many of the sustainability assessment tools that I've seen only consider waste, doing the waste separation at stations good, is sustainable. This cannot happen. You have to do it from the whole life cycle, so from construction until deployment, reduce the waste. And my methodology is also going to focus on that if possible. Thank you very much.
Yeah, thank you again, Maria. So I guess I'll get back to you and hand over to you again for introducing the last presenter of this session.
Yes, so I'll be very sorry if I don't pronounce your name correctly. So Samuel Chng, I think, is an applied social and environmental psychology focusing on decision-making and behavioral change research. And his primary areas of study include sustainability and technology use. And currently, he is in a research fellow in WIQ Center for Innovative Cities and Singapore University of Technology and Design. So I'll give the floor to Mr. Samuel to give us his presentation.
Thank you, Maria. It's nice to be able to present to everyone here today. So I'm from the Lee Kuan Yew Center for Innovative Cities at the Singapore University of Technology and Design. And I'm a psychologist by training, but I've had the opportunity to work with Associate Professor Lynette Cheah, who's from the engineering faculty, actually. And we share a common interest in transportation. And my primary work in the center was to look at how people are actually using technology, particularly the new disruptive technologies that will be coming up in different aspects of work, social, and also even in mobility. So today I'll be sharing some of the findings that we have gotten. This is an ongoing work, ongoing research that we have been doing. So in general, our focus is on understanding AV and how they will be introduced in public transport in Singapore. And I'll give a very brief context on why we are focusing on public transport AVs rather than the other applications of AVs. Okay, so a little background about Singapore. So Singapore, it's quite dense and it's a very small city. It's a city-state itself. And it has a very high public transport ridership. So at last check, it's about 70% of mode share during peak hours. And also we have about 7.5 million public transit ridership per day. And more than half of it, so about 4 million trips are made on buses and 3.5 million trips are made on either the MRT or the LRT. Okay, so in Singapore's strategy to become a smart nation, there are many initiatives that I'm embarked on, and one of it is looking at autonomous vehicles to transform mobility in the nation. So autonomous vehicles are part of this vision, and a lot of work has been done in the last decade. And one of the focus of introducing public AVs into Singapore is applying them in the context of public transport, because it's kind of really the backbone of how people travel within the city itself. And the aim is to bring different forms of mobility, and it also addresses some of the key challenges that we face currently, which is the constraint in our land area. We can't devote more space to build new roads to have a bigger vehicle population. And also we are facing some manpower challenges. So AVs present an opportunity to help public transport in the long term. And also, let's say, the traffic congestions, especially if you apply it to freight. So to fulfill this or to reach this vision, there are multiple trials that are currently underway. So you see two pictures on the right side. one trial recently concluded. It was on Sentosa, so it's a small island catered mainly for tourism. So they trialed two different types of AVs. One is the shuttle, as you can see in the picture there, and another one is a small shuttle. So the trial has ended, but there are other ongoing trials, and one of them is at the National University of Singapore, where they are testing out a fixed route shuttle. And so with all these trials, the Land Transport Authority in Singapore has also expanded the test areas. So you can see on the picture on the bottom right. So the initial AV testing areas were only the areas in red, but it has since been expanded to cover the entire western region of Singapore. So that's about almost half of the city is available for AV testing. And there are intentions to actually roll out AV trials in early 2020s in 3 neighborhoods, and these neighborhoods have been already defined to test out different types of AV services over there. So it's an exciting time. Within the next few years, we'll probably see different applications of autonomous vehicles into public transport. And so we decided to study this really to understand in preparation for the implementation or testing at scale of autonomous vehicles, how ready are people when coming to accept this new form of mobility, particularly when it's driverless and on the roads. And yeah, I could mention this too, that we have had driverless trains, LRTs, from 1997, or 1999 actually, and then in 2003 we introduced driverless mass rapid transit. So the city itself is not, it's used to having driverless systems, but not on the roads. Yeah. So I'll be sharing two findings from two studies that we have conducted. One quantitative and another one qualitative. So we conducted a pilot survey to understand what is the AV acceptance in public transport, and we did this using an online platform, and we had a sample of 210 valid responses with a big range of 18 to 79, and about 47% of them were female participants. And within this sample itself, we had about 74% of participants who were daily public transport users. So this is very close to what is out there in the general population, where it's about 70%. And so the target for public transport ridership is actually 75% by the year 2030. So we are very well on the way there. And so this survey focused on a few aspects, of which I'll present some today. So we're sharing the findings with regards to what our participants expected in terms of or what they perceived were the benefits of implementing autonomous vehicles in public transport. What are some of their concerns with regards to introducing them, and what are some of their preferences that they would like to see as part of the implementation effort. And also lastly, to look at what is the prevailing intention or acceptance of autonomous vehicles. So looking at benefits, so we presented to participants a list of benefits and asked them to share how much, to what extent do they agree with these benefits. And the benefits that I've presented in this table, they are presented according to in decreasing order. So with the benefit with the highest mean score at the top. So a lot of them, majority of them, about slightly more than 50%, they believe that AVs, when introduced in public transport, will help improve public transport reliability and also lead to shorter traveling time. it is important because over the past few years, Singapore's public transport system, particularly the train system, has been facing some reliability issues, but they've largely been resolved following the last few years. But I think there's an expectation that if you're introducing a new mobility mode to public transport, then you would naturally expect this to improve the reliability. And also, a number of them expect it to improve their travel comfort and also reduce the traffic congestion. And of note, there's quite a number of them, a sizable amount of them thought it will actually solve the transportation problems of those who are facing some challenges now. For example, the elderly or people with disabilities, they would have better access to public transport. And when we look at the concerns that some of them might have, if you can see on the right, the mean score, you notice that the mean score, the extent to which they agreed with some of these concerns were generally a lot higher. We had stronger opinions on this compared to the benefits, where a larger portion of our participants were in the neutral range. So we see some of the top concerns, they are more or less focused in terms of the technology. It could be related with the understanding of what AV technology is and what are some of the safety safeguards or how do some of the systems function on board. So for example, the concerns are whether the AVs will be confused when they're on the road and meeting unexpected situations, or whether there could be accidents because of technical errors. And if there is an accident or incident, then what would be the liability if an AV is involved? And also, of course, concerns about cybersecurity. However, we see that the concern is slightly lower in terms of whether AVs will not drive as well as human drivers, which is slightly lower, but then we see a more polarized range of answers over there too. Okay. So when we moved on to what would the public expect in terms of when AVs are being implemented, we see it's quite clear. And once again, we see very strong answers for some of the options given to them. For example, they would expect that the systems would be extensively tested before it is being introduced in public transport. And there's also a strong inclination for humans to be involved in monitoring the system. So there's a differentiation here because we have two options. One is the second one, where we say that humans are actively monitoring the system. This could be remotely, but they would be told that there is active human monitoring, as compared to, if you look at the option right at the bottom, having human operators on board the vehicles. There's slightly less inclination for that, even though there is still majority of them would somewhat agree that they would like human operators on board. But again, we see the issue of clarification of liability. So 90% of them would want some sort of clarification in terms of liability when autonomous vehicles are introduced. And of course, we see public education, they would like to know more about the technology, and also some incentives for early adopters or for even testing out the vehicles when they are initially implemented, with free rides or lower fares to incentivize them. And this is probably important if AVs are being introduced alongside conventional vehicles. So why would commuters choose an AV over a conventional vehicle if both would take them to their final destination? So when we look at the overall acceptance, we find that there is a positive acceptance out of a score of 5. So So we see the mean score in terms of acceptance was 3.87, so it's quite high. And across all the other studies that we've been doing in terms of new disruptive technologies, we see that it's quite consistent that Singaporeans have general receptiveness towards these technologies. And notably, we did not find any significant difference across demographics. So, for example, there was no difference across age, across employment or income, or even gender. So we didn't find any significant difference across this. And once again, it's consistent across our studies used in the Singapore population, which is slightly different from what previous studies have found. And when I did some further analysis, we found that the perception of benefits actually predicted the acceptance rather than the concerns, even though the concerns were showing stronger responses. So that is the pilot survey that we did, which then went on to inform some of the subsequent work that we did. And I'll be sharing the citizen dialogue that we conducted late last year. So we conducted a dialogue together with Create, another research institution in Singapore, and together with partners from 23 other cities, coordinated by Mission Public. So it was a citizen dialogue where we invited members of the public to join us for a full day discussion. So it's about 8 hours of discussion where we understand or discuss the whole concept of driverless mobility, what it means, what autonomous vehicles are. We explain in depth to them, like what are the SAE levels, so the automation levels, what are some of the possible service models, and we engage them in active discussion. So some of the topics that I'll be sharing is, for example, like what is their level of trust or confidence or optimism in terms of introducing autonomous vehicles into the mobility landscape, and also what are some of the service models that they would prefer. So the cities that are involved in this study are listed on the right, and you can see Singapore was the only Asian city that was involved in this study. So most of the cities were in Europe and also in North America. So today I'll just talk about the findings that we had from Singapore. So we had 61 members of the public join us for the full day dialogue. So we started right at the start, even before sharing any information to them. We asked them what they thought about the arrival or the dawn of driverless mobility. And it was quite a simple question. So we just wanted to get a sense at the start of the dialogue, how they're entering the dialogue. So you see that 74% of them thought that it was a good move, a good thing that driverless mobility is being introduced. And when we look further, we asked them to share words that they associated with driverless mobility and what they thought about it. So you can see a word cloud on the right. So a lot of the words are associated with it being, exciting, future, it's cool, it's the new way forward. It's even one of it is revolutionary. So it's this very positive, very idealistic connotation that comes together with driverless mobility with participants in Singapore. So after that, we shared slightly more about what driverless mobility is. We showed them a couple of videos, what experts would say about driverless mobility. And then we asked them to reflect on what are some of their hopes and what are some of their concerns with regards to introducing driverless mobility in Singapore. And so we summed up their responses into 5 hopes and 5 concerns, and this paralleled quite closely with the findings that we had from the pilot study. So we found that their hope is that driverless mobility will really improve transportation in Singapore, reducing the travel time, improving the door-to-door travel, and it will improve the safety on the road. So somewhat at the start of the dialogue, people trusted that AV technology is safer, and they would be programmed to obey rules which humans are very prone to challenging. And it would, in the longer run, with AVs being autonomous and dynamic, then it will help to reduce the traffic congestion that we are facing. And it will also, there's a hope that it will reduce transport costs because of the introduction of new shared services. And that with this, it will collectively improve the transport experience, and hopefully they would have more free time to do other things apart from traveling from point to point. But at the same time, they had some concerns, and not surprisingly, the top concern that we noticed is on safety. So there is some apprehension on whether AVs can be trusted, how safe is the technology, and specifically how AVs interact with vehicles that are human-driven, so the man-machine interaction. And then, ironically, there's some that are worried about the cost. So now that we're introducing autonomous vehicles, they're expensive technology, would this mean that it's going to be more expensive? And if private vehicles will be automated, for example, like you see in the more advanced cars with some automated features, they're generally more expensive. So would it mean that owning a private vehicle that is also autonomous would be a lot more expensive? And there are also concerns on the reliability of the technology. So will there be, for example, some technical errors or breaches that will affect the reliability of the AVs? And also back to the issue of liability and a limited understanding or knowledge about how things will be in the future, because it's in a few years' time, and we haven't really, at least in Singapore, had a AV accident that's so public that people are able to judge who is liable for the accidents and who regulates the systems and so on. And lastly, also about data security. So how will the data be used? So not only the transport operators collecting the data, the service providers are collecting the data, the transport authorities are collecting the data. And if you
Samuel,
have,
we are running short out in time. So if you could wrap up and you would ask a question from the group,
okay.
Would that sound good to you?
Yep.
Can you wrap up for us, please?
Yes. Okay, so just 2 more slides.
Okay.
So we found in Singapore, we know that there's a general optimism towards autonomous vehicles. So we also compared with 4 other cities, both in North America and also in Germany. Not Germany, but Europe. The different cities in Europe. We see that Singapore has a high optimism, but this is also seen in other cities too. And lastly, we'll talk about the preferred autonomous mobility service models. Okay, so we gave participants 3 different types of models for simplicity. So one is private ownership, and on the other end would be public transport model only, and the in-between would be a ride-sharing model that we would be quite familiar with now. So we can see across all 5 cities, the preference is for a public transport model and introducing AVs into the mobility system. And in Singapore's case, it was highly desirable to have a public transport model compared to the rest. Okay, so if this, and the presentation and I'll take questions.
Okay, so we have time for one question. I have one here from Mahmoud. He asks, what incentive was offered to the participants for a one-day focus group?
Yeah, I think Lynette answered that question to Mahmoud. We offered the incentive to the participants, but I think you can see that we had 61 participants. It was very difficult to recruit the participants and convince them to join us for an entire day. Typically, research involvement would be maybe half an hour. So yes, we had to offer incentive to the participants to do this. And it was, I think, slightly higher than your typical research, like a survey, but it's equitable to the amount of time that they had to spend. And it was a weekend. Yeah.
Okay, thank you very much for your presentation and for answering the questions. And sorry for the wrapping up so quickly, but we are really running short of time.
Thank you.
So I would like to thank all the participants for the opportunity and.
Okay. All right. Welcome everyone to BTR online conference. This is track 5, section transport research methods and econometrics. Today we have 2 co-chairs, Rico, Krueger, and me. And today we have 4 speakers, including Patricia Bancel, Rico Krueger, Diviakan Talian, Mariel Houston. And so for each speaker, we have 20 minutes presentation and 10 minutes for Q&A. And for the audience, if you have any questions, please leave your question in the Q&A section. We will answer the question in the Q&A section and leave your question in the chat box. And so for the first speaker, Patricia Bancel, let me introduce every speaker first. So the first speaker, Patricia Bancel, Dr. Patricia Bancel is a Leverhulme Trust Early Career Fellow at Imperial College London. He received his PhD from Cornell University in 2019, Master of Science from the University of Texas at Austin in 2015, and Bachelor of Technology from Indian Institute of Technology, Delhi in 2013. He is mainly interested in developing methods at the intersection of machine learning and econometrics, with application in travel demand modeling. Our second speaker, Rico Krueger. Dr. Rico Krueger is a postdoc at EPFL, and he obtained his PhD from the University of New South Wales, Australia. His research focused on the development and application of machine learning and statistical methods to solve problems in transport engineering. Our third speaker, Diviakan Talian. Diviakan Talian is a PhD candidate at Northwestern University and currently works as a graduate research assistant with Professor Hani Mamasani at the Northwestern University Transportation Center. He holds a master's degree in civil engineering from the University of South Florida in Tampa and a bachelor's degree in civil engineering from the Indian Institute of Technology in Varanasi, India. His previous research has been in the areas of road choice set generation, road choice modeling using large-scale GPS data, and incorporating attitudinal psychological factors in discrete choice models. He is currently interested in and working on application of machine learning methods in transportation, econometrics analysis, and social networks aspect of travel. Our last speaker, Mariel Houston. Mariel Houston, who works as a junior researcher at the Institute for Transport Studies at BOKU in Vienna, Austria. She holds 2 master's degrees, one in human geography from Lund University and one in social ecological economics and policy from Vienna University of Economics and Business. Maria is currently in the final stage of her PhD studies at BOKU. Her PhD focused on the analysis of sustainable tourism mobility using both qualitative and quantitative methods. Okay, so I think we already taken enough time. So please, Patrick, you may start your presentation if you like.
Thank you, Yiyang, for excellent introduction, and thank you everyone for joining this session and talk. I hope you would enjoy this econometric methods talk. So in this talk, I would be talking about some fast methods to estimate count data models, and this is a joint work with Rico Krueger, Michel Berlier, and Daniel Graham. So spatial count data models are used to explain and predict frequencies of aggregate phenomena such as traffic accidents in geographical distinct entities. It is also used in various disciplines like epidemiology or geography or regional science. So it's pretty much very contemporary methods these days in these disciplines. But when we model these spatial count data, as you have example on the right side of the slide, it is the youth pedestrian injury count data from New York City, and you can see that there is a lot of aggregation of crashes there, and that's why, because of these aggregation in certain areas, we have spatial dependence, and due to the systematic correlation in various unobserved factors. And at the same time, we also have spatial heterogeneity because the effect of covariates on counts are varying across spatial units. So accounting for these spatial dependence and spatial heterogeneity is important, because if we ignore these effects, then we end up with biased parameter estimates in our link functions and also the inaccurate inference. But at the same time, when we account for these spatial effects, we end up with very computationally complex estimation. And these days, data sets are growing in size, and they are becoming available on a streaming basis. So it is important to find methods which can estimate these models almost in real time. For example, if someone wants to predict, like, every day the factors affecting how the factors affecting COVID-19's death counts, then obviously we need to find methods which can efficiently predict these crash counts, these COVID counts. So traditionally, we use Markov chain Monte Carlo methods. In short, we call MCMC. The idea of MCMC is if you have a posterior density that we want to achieve or estimate for parameters, the key idea is we sample from that posterior density. And you can see on the right-hand side of this, we have, in the bold, we have the true posterior distribution, and the histogram is of the posterior samples. And it has been proven that if we run over Markov chains long enough, we end up with asymptotically we reach to the posterior distribution. So it seems good in theory, but when we work with count data models, we have to use Metropolis-Hastings algorithm because due to non-conjugacy, as we will discuss a little bit about this later. So when we use Metropolis-Hastings and work with this Gibbs sampler, we have 4 potential issues that we encounter. One is computation time, because we need to run Markov chains quite longer to ensure that they reach their samples. We are reaching to asymptotically to a posterior distribution. And we need to store all these posterior draws. So if your data sets are longer, if you have too many parameters, then storage cost is significant. Convergence assessment is also sometimes difficult. We have to run multiple chains to, there are ways to do the convergence assessment by just one chain, but still it's hard to check the convergence while doing the simulation. mostly you first do the MCMC and then you do the convergence assessment. And also, by the nature of how MCMC draws are taken, there are serial correlations in the draws. So these are potential issues, and especially when you have Metropolis Hastings algorithm, these issues become more prevalent, which are very common in spatial count data models. So recently, in last decade, I would say, in Bayesian machine learning literature, variational Bayes has emerged as an alternative to MCMC. And it has as a very fast alternative to estimate these traditional linear models. So the idea of variational Bayes is as follows. We have, again, the bold line is our true posterior. What variational Bayes does, it assumes that there is some parametric family of distributions which approximate this posterior distribution. So that's why it's an approximation, but it works in practice, as we would see. So we assume that this Q theta conditional on nu is a variational distribution which approximates the two posterior distribution. And intuitively, the whole point of this estimation is we want to minimize some sort of a distance between these two curves. And the idea is we find the distribution parameter, parameters of variational distribution, so that we reach closer to the posterior distribution. So the way intuitively we set up the problem, it automatically becomes an optimization problem because we are kind of finding the distance between two things and minimizing it. So it sounds like an optimization problem. So so this variational Bayes method recasts the Bayesian estimation as an optimization problem instead of a sampling problem that we have in MCMC. And as I mentioned, we approximate this posterior distribution using parametric variational distribution. And there are several advantages of recasting this problem as an optimization problem. We don't need to store draws because we just need to store some parameters of the variational distribution that can be order of like less than 100 generally. Convergence is easy. Assessment is easy because it is as simple as in any optimization problem. You just look at the two conjugative iterations of an optimization and see whether the model has converged or not. Serial correlation is no longer an issue because we are not taking draws, so that issue is not there. And I think this is the last characteristic of variational Bayes sets it apart from MCMC, that it is scalable. So there is a whole sub-discipline in this variational inference domain about where people use stochastic variational inference, and that allows to scale this method to millions of observations in practice. So we wouldn't get into stochastic optimization today, but we will just in this talk, I will talk about how we develop this VV method for fast estimation of count data models with spatial dependence and spatial heterogeneity. So I'll start with a model formulation. We assume a negative binomial likelihood where our yi is some count in maybe crash count in specific spatial unit I. We assume it to be negative binomial distributed with the shape parameter R and probability parameter Pi, where our Pi is our logic kernel with the link function psi I, and psi I has our beta I, which are the link function parameters, and we assume them to be varying across spatial units, and that accounts for spatial heterogeneity. And phi I is our spatial dependence, is the term that captures the spatial dependence across spatial units. In this study, we assume spatial heterogeneity to be normally distributed with the mean mu and full variance covariance matrix sigma. And in terms of spatial error specification, we assume matrix exponential spatial specification. Generally, I mean, there are various other specifications like conditional autoregressive structure. There is no specific reason to choose one over another. It's more of like a computational convenience. That's the reason we use this specification. So once we have this model set up, we get to the basic details of the estimation. So generally, when we have a negative binomial distribution, we don't have conjugate priors. So as a consequence, we don't have conditional distribution of linked function parameters which have known distribution. So in the absence of these known distributions, we have to do Metroplus-Hastings algorithm. So in recent years, like in 2013, Paulson introduced this polygamma data augmentation technique, and we use that technique to address this non-conjugacy issue, even in variational base. So the idea of polygamma data augmentation is we introduce a polygamma distributed auxiliary variable in the model, and once we condition on this auxiliary variable and all other variables, as we do in Gibbs sampler, the likelihood of the observed count is translated into a heteroscedastic Gaussian likelihood. And once it is converted into the heteroscedastic Gaussian likelihood, it's kind of a linear regression model with spatial error term as well as heteroscedastic error term. So the problem becomes much simpler as compared to what we had earlier. And once we have this, once we apply polygamma data augmentation on our setup, now the next thing is to understand how variational bayes work on this augmented model. So as I discussed intuitively before, this variational bayes seeks to minimize the probability distance, which we consider real divergence in this case, but one can assume different measures of this probability distance. And this is the distance between an approximate variational distribution and the posterior of interest. And as I mentioned, then it's an optimization problem when you have minimization, where you are minimizing this distance. Now the key part here is how do we select this variational distribution? Because the quality of the approximation would depend on the choice of the variational distribution, and also how complex this optimization problem is. That also depends on the choice of variational distribution. So mostly there is a trade-off between quality and complexity in this case, but we will see how it unfolds in our case. So traditionally in machine learning literature, it all started with the most simplistic variational distribution, where we assume the posterior independence between different parameter blocks when we define the variational distribution. And once we define the posterior independence, the joint variational distribution is product of all these densities, individual densities of parameters. And the good thing about this mean field variational bayes is if we have a conditionally conjugate model, which we have for most of the parameters except few, after using the polygamma data augmentation, MFBB, this mean field variational bayes, leads to a coordinate ascent algorithm, and which makes things very easy. The updates of this variational distribution are very simplistic. But when we do this simplistic mean field variational bayes, we realize that our spatial association parameter tau and spatial error scale parameter are not recovered so well in our simulation study. So we had to think about other possible options for defining this variational distribution. So here's the thing that we finally do. And what we do is we use a different type of variational distribution, which we call integrated non-factorized variational bayes. And it was used first by Han et al. In 2013 in a different context. What it does, it decomposes the parameter space into two disjoint subsets, theta c and theta d, to introduce dependencies in the variational distributions of two sets of parameters. So we were thinking that maybe our tau and sigma square are not recovered well because we are losing the dependency of tau sigma square with other link function parameters. So that was the thought process which was going through behind choosing these tau and behind going through this method which can create some dependence between these tau sigma square and other parameters. So in this case, theta d is or tau and sigma square, which were not recovered so well, and theta c is all other parameters. When we have this setup, when we specify this variational distribution in this composite form, and try to minimize the KL divergence, it's pretty difficult. The problem becomes complex as we try to minimize KL divergence. But if we condition on these theta d, then this problem is same as mean field variational inference, basically. So the idea was, how do we condition on theta d then? So to do the conditioning on theta d, we define a grid. In this case, a two-dimension grid, because tau and sigma square both are unidimensional variables. So we define a two-dimension grid on tau and sigma square. In our case, it was, in case study, it was around 20 cross 40, so it was 800 points. So we define a grid point on theta d, and for each grid point, we run MFVB separately on each grid point, and then we compute for each grid point using Boltzmann distribution and combine all the updates that we get on each grid point. Because an MFVB is very fast and all these grid computations that we did are in parallel, this entire process is parallel. So if we have, let's say, in theory, if we have 800 cores, we can put each of this process in each core. So that's the beauty of this this conditioning and this grid type structure. So without getting into detail of how these methods are derived, which are available in our paper, I would directly get into how these methods work in practice. So we conducted simulation study as well as empirical study. In the simulation study and empirical study, results were similar. So I will mainly focus on empirical study. So we consider this we study youth pedestrian injury counts in census tracts of Bronx and Manhattan County in New York City. And this is the spatial plot of those counts, as I've shown earlier as well. We see significant spatial dependence among these crashes. Pedestrian injury count data was available online, but we populated data with some census demographics as well. So we had poverty status, ethnicity variable, as well as number of workers, social fragmentation index, which talks about which is created based on number of isolated vacant housing units, single household units, and various other ways to quantify the social fragmentation. We have data on average annual daily traffic, as well as private vehicle commute mode share. So these are the variables that we had and we use in the estimation. So if we discuss about in this while I discuss results, I wouldn't focus on the interpretation of these coefficients. I would mainly focus on the recovery of these parameters, how MCMC and variational Bayes are compared in terms of recovery of parameters of these variables. So in terms of estimation time, on a regular 8-core computer, INFBB takes 17 minutes. MCMC takes 117 minutes. It is because we don't have all the resources that we can use. We just use 8 cores. But if we have more number of cores, then this computation time can go to less than 1 minute, actually. In terms of goodness of fit, we consider log score as well as 2 other measures. One is the David-Sebastiani index and rank probability. David-Sebastiani uses mean and variance of posterior predictive distribution, and rank probability uses full predictive distribution. If we look at these mean scores, both are pretty similar. But if we look at the credible intervals, we see that the INFBB is relatively narrower, and which is not surprising, as we would see similar trend in parameters as well. in the posterior distribution of parameters as well. And this has been also established in the literature that INFBB sometimes underestimates these variation in the posterior distribution, and which has implications in inference. And in the end, it's an approximation, so it's acceptable if it is within limits. So now let's discuss the recovery of posterior distribution of individual parameters. So in this case, on the top row, we have all the fixed parameters from the link function. And we can see that MCMC and INFBB are doing equally well in terms of recovering of fixed parameters. In the second row, we have mean of the posterior distribution of the mean of the random parameters. We can see that the posterior mean of the mean is pretty close, but the spread of the credible intervals are much narrower in INFBB as compared to MCMC. The same thing that we have seen in credible intervals as well. In this plot, we have on the first row, we have variance of the random parameter and basically their posterior distribution. We can see that the recovery is pretty similar for INFBB and MCMC. And in the last row, we have other parameters like spatial error scale, as well as spatial association parameter and negative binomial shape parameter. We see some differences in negative binomial shape parameter, but when we see this in terms of numeric differences, it's not so significant. So we have seen that in terms of estimation, both are doing pretty much similar except the credible intervals. We also do the in-sample prediction to see how well they are doing, both methods, MCMC and INFBB. So we predict the youth pedestrian injury counts and plot their histogram on the left, and we see they are doing pretty much pretty similar in terms of predicting youth pedestrian counts. And because this was the aggregate measure, we thought like let's look at the what is happening in each spatial unit. So we take the difference of the predicted youth pedestrian injury count in each spatial unit in using INFBB and MCMC and plot them on the right of this plot. And we see that most of the differences are close to zero. So it's not just at the aggregate level, even at the spatial unit level, they are doing pretty similar in terms of in-sample prediction. And we also checked the...
Pratik, sorry to interrupt. So we have 1 minute. Can you wrap up?
Yes, I'll wrap up in 1 minute, yeah. So we have this spatial error, this posterior distribution of spatial error in MCMC and INFBB, and both also appear similar. So in terms of goodness of fit and recovery of posterior distribution, as well as in-sample predictive accuracy, both methods are doing pretty similar. So conclusively, we derived this INFBB method for fast estimation of count data models. We have seen that the INFBB is around 7 times faster than MCMC on a regular 8-core computer, but it can be made 100 times faster due to this parallel architecture. And we have seen that the INFBB offers similar estimation and predictive accuracy as of MCMC. The future research directions are we can extend this model to spatiotemporal to account for spatiotemporal dependencies, and also for estimating counts in real time by extending this method to stochastic variational inference. Thank you for listening. I would be happy to answer any questions.
Thank you, Pratik. Yeah, we do have 2 questions from the audience. The first from Professor Kara Kalkman. So the question is, do you recommend INFBB for all spatial count models to other Bayesian machine learning options, since it's more straightforward and transparent, respectively?
Yes, based on our results in simulation and empirical study, I would say that it can be used for all spatial count data models. But the thing is, we have derived it for negative binomials. So if someone assumes Poisson log normal, we need to derive another updates for this method. And then if someone is doing multivariate count data model, then we need to extend that. So this is kind of a first study, and there are various ways to extend this to multivariate modeling and maybe Poisson log normal as well as spatiotemporal count data model to make it more versatile in practice.
Okay, so we have another question. Can you clarify what do you mean by spatial heterogeneity in the coefficients? Is there a hierarchical spatial structure imposed on the betas?
Yes, it's a hierarchical structure, as I include this in the specification. We assume this in the second equation, we assume beta I to be normally distributed with mu and sigma. The key idea is, for example, if we take the cash count data example, then what we are all saying here is the effect of, let's say, social fragmentation on youth pedestrian count in one spatial unit might be different than the other spatial unit. So this is captured by this spatial heterogeneity that we have here. And rather than specifying each effect in each spatial unit, we just define the distribution on this spatial effect heterogeneity.
Okay, thank you, Pratik. I think, there's another question, new question can pop up. So does this method work well for small sample size data?
Yes, based on, like in this study, we use a 600 samples, and it is doing as well as MCMC. But I think if we have smaller sample sizes, it will do as well as MCMC in the sense that that's my expectation. We haven't gone to like sample size of 100 or 200, but yeah, like for 500, it will certainly work. And it also depends on basically the spatial, how much spatial heterogeneity there in the data. Because sometimes we don't have that unobserved spatial heterogeneity and try to estimate these models, then we cannot really identify these parameters from the estimation. So that spatial heterogeneity should be inherent to the data.
Sounds good. Okay, so I think that's all for Pratik. Thank you for your presentation. And now we'll welcome Rico Krueger for the second presentation. Rico Krueger, you may start if you want.
Okay, can everyone see my screen now? Yes.
Yep.
Okay, so I am going to present about a new spatial count data model with Bayesian additive regression trees for accident hotspot identification. This research is a joint work with Pratik Bansal from Imperial College London and Prasad Budavarapu from UT Austin. So in road safety management, crash count data models are used to produce rankings of hazardous sites and to predict crash counts at hotspots. Traditionally, crash count data models are Poisson log normal models or negative binomial regression models, and these models account for spatial correlations between spatial units. These models also assume a linear and parameters link function. This linear and parameters link function is suitable from an interpretability perspective. However, the predictive performance under such a linear and parameters link function may not be sufficient in some applications. So therefore, analysts typically try to improve the specification of this linear and parameters link function by applying some transformations to predictors such as taking the log of some variables or squaring variables, as well as sometimes analysts create dummy variables from variables to improve the interpretability of the model. However, the issue is that in spatial count data models, exhaustive specification searches are often not feasible because the model structures are quite complex due to the need to account for unobserved heterogeneity and spatial correlations. In machine learning, some methods have emerged to automate this specification search in spatial count data models, and some examples include kernel-based regression, neural networks, support vector machines, as well as different kinds of deep learning architectures. However, these, However, these modern machine learning approaches are subject to three limitations. So first, they typically do not account for spatial correlations between observations, and also they do not offer straightforward ways to construct confidence or credible intervals, because these approaches are typically embedded into a frequent-based inferential framework. And another aspect of these ML methods is that they are fully non-parametric with no easy ways to include an additional interpretable part into the link function. So to address this gap in the literature, we propose a new spatial count data model, which is a negative binomial regression model with a semi-parametric link function. And this model specifies the non-parametric part of the link function using Bayesian additive regression trees. And using this Bayesian additive regression tree framework, or BART, allows us to induce an endogenous partition of the predictor space. So in other words, the specification search is automated by including this BART component into a count data model. So at the same time, we also retain interpretability, because even though we have a BART component in our model, we can still add a linear and parameters link function component into the model. So, and this allows us then to additionally include random parameters and spatial correlations into the model. Another positive aspect about this model is that it is embedded into the Bayesian inferential framework, which makes it easy to account for various sources of uncertainty and also to compute credible intervals. So I now want to explain what BART is. So BART is essentially a non-parametric regression framework, which specifies the regression function as a sum of trees. So an example of BART is shown on the right. So here we have a single tree in this ensemble of trees, which is BART. So the idea is that we have different splitting rules for each predictor, where we divide the predictor space. So for instance, here on the right, we induce a partition by assuming that all observations where x1 is less than 0.7 are sent to the node mu j1, and all other observations are sent to this other decision node. And here, if x2 is less than 0.4, observations are sent to node mu j2, and otherwise they are sent to mu j3. So the idea of BART is to induce a partition on the predictor space, which induces or allows for both nonlinearities as well as for main interaction effects. And BART, in BART, the advantage of BART is that both the decision rules, which are these T parameters, as well as these leaf nodes, these mu parameters, are estimable parameters in the model. So, and our contribution is now to incorporate BART into a spatial count data model. So on this slide, we summarize the proposed model. And so we assume, as in the previous presentation, we assume that our observed counts y for spatial unit I are described by a negative binomial likelihood, where the probability parameter is specified using a logit parameterization, and where R is the negative binomial shape parameter. We then assume a semi-parametric specification for the link function psi I. So we assume that psi I depends on capital GI, which is barred. So it is a sum of trees, as we can see here on the right. And additionally, we can include another linear and parameters part for interpretability. We also capture spatial dependence in the model by using the matrix exponential spatial specification for a random effect vector phi, which is also included into the link function. So one issue with the negative binomial model, as we pointed out earlier, is that the negative binomial distribution does not have a general conjugate prior, and therefore the conditional distributions of the link functions do not constitute known distributions, and is difficult to perform inference on such a model using Gibbs sampling. As a remedy to this issue, we introduce Polya-Gamma distributed auxiliary variables into the model, and conditional on the auxiliary variable, the likelihood of the observed counts is then translated into a heteroscedastic Gaussian likelihood. And this is certainly advantageous in this context because it's much easier to deal with a Gaussian likelihood, and also BART was originally developed for Gaussian models. So this makes combining BART with a spatial count data model much simpler. So we now we test this proposed spatial count data model on real crash frequency data from 1,158 continuous road segments of 11 highways in the greater Houston metropolitan area. And we consider data which covers an observation period of 4 consecutive calendar years. And for this analysis, we assume that the data from each year constitute a separate sample. And this allows us to compare the performance of BART on different samples. So this is the sample description. So as I said, we consider crash counts aggregated across different categories of crash severities. And then we consider a number of other variables which pertain to the road condition, the geometric design of the road segment, as well as some information about the traffic, such as the annual average daily traffic volume, as well as the truck traffic percentage. And as I said before, we divide the sample according to the years of the observation period, or the different waves of the data collection. So to test BART, we consider 4 different model specifications of a spatial count data model. So 3 of these specifications consider a restricted predictor space, which we call predictor space 1, where some continuous predictors are converted into dummy variables and are also log transformed, for instance. So using this this corresponds to the state of practice in the empirical analysis of crash frequency data, where we typically try to reduce the size of the predictor space by imposing these converting continuous predictors or making some transformations. So we test NB-BART, which is the proposed negative binomial regression model with spatial error terms and a BART-based link function. But then we also test a model which we call NB-fixed, which is a standard negative binomial regression model with a spatial error terms, a linear and parameters link function, and all parameters are considered to be fixed parameters. And then we consider another specification, NB-random, where we allow a combination or where we consider a combination of fixed and random parameters in the link function. And the fourth model specification that we consider uses an unrestricted predictor space too. Unrestricted predictor space where all predictors are considered in their original form. So this is really to show the advantages of the BART component in the model, because we allow BART to induce an endogenous specification on the predictor space. So we apply this model to the data that I just described, and we perform inference using MCMC methods. The first thing that we do after we have estimated this model is to assess the model fit using two criteria, namely the log point-wise predictive density, LPPD, which is essentially the log likelihood integrated over the posterior density, as well as the root mean square error between the predicted accident counts for each road segment and the observed accident count. So here we see the results for the 4 different samples for the different waves of the survey. And we can see that the specification NB-BART, which uses an unrestricted predictor space, performs best for all samples. And another observation is that NB-random and NB-BART1 are approximately on par. Typically, NB-random is slightly better than NB-BART1, but the differences are not substantial. However, NB-fixed is clearly outperformed by all other methods. We then also assess the site ranking ability of the different methods. So in this application, we rank sites by their posterior mean probability to belong to the top 5% most hazardous sites in the network. And we compare the site ranking ability of the different methods by assessing the temporal consistency of the produced site rankings over the different observation periods. So we consider 2 criteria which are well established in the literature. I don't want to go over these definitions in too much detail, but we consider the site consistency test, which measures the ability of a method to consistently identify a site as risky. Moreover, we consider the method consistency test, which captures whether a method can consistently identify the same set of hazardous sites across 2 observation periods, as well as the total rank differences test, which is essentially the absolute difference between the produced site rankings in 2 time periods. So on this slide, I now show the site ranking results. So here we show the observed crash counts, as well as the results from an EVE ranking, where we simply assign a value of 1 to sites that belong to the top 5% most hazardous sites, and 0 to all other sites, as well as the probabilistic ranking results for the alternative methods, namely NB-fixed, NB-random, and NB-BART 1 and 2. And here we can see that there are actually no substantial differences between the different probabilistic methods. They all perform equally well. However, we still observe a difference in this distribution of these probabilistic site rankings as opposed to the observed crash counts. This is because the probabilistic ranking methods do much better at capturing the uncertainty that is inherent to the riskiness of a site in a road network. Now I show the results for the site ranking consistency using these three criteria that are introduced. So we can see that NB-BART2 performs best in terms of site consistency for all comparison periods. And however, we do not observe any substantial differences for the other 2 criteria, but the differences between the methods for each criterion are also small. therefore, we conclude that NB-BART2 performs at least as well as the more established methods NB-fixed and NB-random at site ranking consistency. So BART also provides some information about the importance of different predictors. So this is different from elasticity, what we typically calculate for count data models. In the context of BART, variable importance is related to the proportion of times that a predictor is included in a splitting rule. And here we show the variable importance for all predictors for 3 of the 4 observation periods. We restrict the display of the results to 3 observation periods to avoid clutter. But the main insight here is that the pattern that we observe in terms of importance is relatively stable for across different observation periods. So the importance of different predictors does not vary much for this data set. And another observation that we can make is that for some variables, such as the road overall quality index, the importance of the variable actually increases as we consider the continuous version of the predictor, which is obvious in some way because naturally a predictor can be partitioned in more ways if it's a continuous variable instead of a binary variable. So, and to conclude, I want to highlight several key takeaways. So what we did is we proposed a NB-BART model, which is a spatial count data model, which endogenously partitions a space of predictors. And using this BART component in a spatial count data model allows us to flexibly account for interactions as well as nonlinear relationships between predictors. And we have also shown in a case study that NB-BART performs as well or better than state-of-the-art models in terms of goodness of fit, as well as in terms of site ranking ability and site ranking consistency. And one recommendation that we can make in terms of practical applications of this method is that if predictive importance is of central importance in an application, NB-BART may be better than other negative binomial models which use a linear and parameters link function and random parameters, because we automate the specification search and we do not need to conduct a search on how to specify the link function using BART. There are 2 immediate avenues for future research. So one of them is to extend this proposed model to a multivariate setting to allow for the joint modeling of different crash counts by crash types. For instance, we can consider different crash types by severity or accident type according to the vehicles that are involved in the crash. And another direction for future research is to accommodate spatiotemporal heterogeneity into the model. Yes, and so this concludes my presentation. And I'm ready
Thank you, Rico.
for questions.
Yeah, so we do have several questions from the audience. The first question comes from Professor Carol Kaufman. So to Rico and Pratik, in terms of applied results, what are the best ways to protect pedestrians? What are the settings we should avoid? What surprised you in predictions? What variables are most practically significant or important that you didn't expect? Also, where did you get those Houston data? Since they work with TXDoc networks and CRIS files, but may not have seen several of those X yet.
Yes, so maybe I first comment on the importance different predictors. So of course the primary emphasis of this work is not on deriving recommendations for policy. It's more about testing these different methods, but especially in terms of the work on pedestrian injury counts, one result that I found quite surprising is that the racial composition or the diversity of a census tract seems to have a critical influence on the observed crash counts in a census tract. Regarding the data source, so we worked with Prasad Budavarapu, who extracted this data from census, not from databases on crash counts and road condition databases, and he collaborated with TXDOT.
Okay, thank you. And there's another question from Adia Maduri. Thank you for the presentation. Questions. One, how do you choose between Fi and Xi? Assume that the variables being used within the parametric and non-parametric are not the same. Second question, how would a purely non-parametric estimation function perform? Is there merit to having a functional form still, as in going purely BART over NB BART?
Yes, so I think the first question is about, if I understand correctly, the question is whether we put x1 here or x2 here. Is this the question? Did I understand that correctly?
I think the first question is, how do you choose between Fi and Xi? The Fi, I think she also mentioned the Fi.
Fi, what is the Fi again? You mean the, because we have a, now I understand. So this part here, the semi-parametric.
Yeah, I think so. Maybe
this decision would be driven by an empirical objective. So, for instance, if the analyst wants to test a hypothesis, whether there's some predictor should be better included as into the linear parameters part of the link function. This is certainly, there's still some flexibility for the analyst to, for instance, if the analyst wishes to calculate elasticities for some variables that are interesting from a practical perspective, then it would be better to calculate, to incorporate these into the linear and parameters part as opposed to the semi-parametric part. So the main argument that we want to make is that we do not need to give up this linear and parameters part. If there's an application where it can still be useful, it can be accommodated in this model.
Okay, sounds good. I think that's all questions for now. Oh, there's a new question come up. Can you explain the impact of RMSE on result?
The impact of RMSE on results. So, where the RMSE results? So the
on slide 12.
On to slide 12. So so we calculate the root mean square error, which basically is a quadratic difference between the observed counts and the predicted counts. And because of this quadratic term, outlying observations are penalized more strongly by RMSE as opposed to using an absolute error.
Okay. Sounds good. Yeah, I think that's all for the questions. And thank you, Rico, for your presentation. do you want to proceed your sharing of the section?
Yes, sure. So
thank you.
Next up is Divya Kant, and he will present about real-time short-term traffic forecasting and meta-learner-based ensemble framework.
Thank you so much, Rico. Let me share my screen with everyone. Can everyone see my screen now? Okay, hello everyone, I'm Divya Kant. I'm a PhD candidate at Northwestern University. I'm presenting today a recent work on real-time short-term traffic forecasting, a meta-learner-based ensemble framework. This work is jointly with Kim and Professor Hani Mamasani from the Northwestern University as well. Before I begin the presentation, just wanted to let everyone know that the results that we have so far are still very preliminary. What we have is very primitive in its form, and we are sort of in the process of developing this further. So just wanted to sort of tone down everyone's expectation with the results from what we present. Okay, so the problem that we are dealing with is of predicting the state of traffic on a network at a point in time, at a certain future point in time. We want to do it in short term, which means we want to predict traffic state a few minutes or a few hours in advance, as opposed to, for example, long-term forecasts, which are generally used for planning purposes. We want to do this in real time, which means we want to update this information as new data is available so that most up-to-date estimates of traffic states are available to us. In terms of traffic state, what I mean is that we are interested in variables that define the state of the traffic on the network. For example, traffic speed, traffic flow, traffic density, and travel time. Of course, traffic speed and travel time are related to each other here. And then we want to predict it either for the entire network or for select few links of interest. If the entire network is not of interest, then we can just do it for a select few links. This information is useful for a variety of purposes. For example, from traffic operations perspective, you can use this information for signal control. You can use this information for variable message signs, or you can also use this information to design certain congestion mitigation strategies. For example, rerouting traffic from a certain route to a different route. From the user's perspective, you can use this information, for example, in navigation systems, where then it can be used by the users for trip planning. This real-time data can also be used, for example, for designing pricing algorithms for ride-hailing services like Uber and Lyft, which rely on this information and then give a particular cost or price of a particular trip to a user based on their origin and destination. The previous studies that have been done in this area, there are hundreds or probably thousands of them so far in last several decades of research. They can be broadly categorized into 4 different categories. Of course, there are some methods which fall outside these categories, but more or less, I think they can be divided into statistical framework. For example, ARIMA state-space kind of model, a machine learning-based framework. For example, you can use neural network, you can use CNN regression, support vector regressions, etc. Traffic flow theory-based methods, for example, you can use real-time DTA simulation models like DynaSmart or DynaMid. These are at least 2 that I'm aware of. Or you can also use some hybrid models. For example, there are papers where researchers have tried to combine, for example, an ARIMA model with a neural network kind of model. The most popular data sources for such real-time predictions is, for example, from loop detectors, GPS data, or even video data. Though there is a lot of research that has happened in the last several decades, a few potential issues that exist with many of the work that is out there is one, researchers often rely on a restrictive hypothesis case. For example, if your model has a linear form and the true data generating process is not linear, you probably will never be able to fit your available data to the true data generating process. Even if you use a more generalized model form like a neural network, determining the optimal hyperparameters as well as parameters of those models is generally tricky. And then generally what is seen in research is that there is no single model that performs best in terms of the prediction accuracy here. What generally is seen is, for example, there is a particular model that performs better in certain situations, then there's another model which performs better in another particular situation. So when we use one single model to do this forecasting, you might not get the most optimal result here. The last potential issue is that generally there is no use of the feedback information that we have available. What I mean by this is that as we predict, for example, from one time step to another and then move forward, there is a feedback information available from the observed data. Basically, we know what the predicted value was and what the observed value is for a particular time step. But generally, we don't use that information to learn from the mistakes that have been made by these models in the past. So with these issues that are presented, we have two important research questions in front of us. One is that, can we combine these different models to improve performance? And second is, can we learn from the mistakes that have been made during the previous time steps to make improvements? With these two questions, we take an ensemble learning approach to the methodology of predicting, for example, traffic speed or other state variables of interest. Ensemble learning is a method where individual models are trained and their predictions are combined. And what is generally seen in research is that these tend to perform better than using a single model for prediction. The ensemble models help tackle the statistical, computational, and representational problems associated with single model approach. There are four major categories in which most of the ensemble learning methods can be categorized. One is bagging, one is boosting, then there is random subspace sampling, and then there is stacking. Bagging is a method where you use multiple models trained with each subset of available data. Boosting is a method where you train sequential models. Once you have a model, you use the misclassified data points from that model and then over-represent them in the subsequent data set and then retrain your model and then go on from there. Random subspace sampling is a method where you use multiple models, each trained on a subset of features of the variables that you have available in the training data set. And then there is stacking, which is the focus of research in this particular work as well, where a meta-learner is trained, which combines predictions from individual models to give you a final prediction using sort of cross-validation data set. We use stacking in this work, which was initially proposed by Wolpert and Freeman in 1990s in cross-sectional data analysis context. What we have in stacking is we have two levels of models. We have a level 0 models, which are independent models giving you independent predictions. And then there is a meta-learner model, which takes the predictions from model at level 0 and then combines it with the cross-validation information to train the meta-learner and then give you a prediction which is a combination of predictions from level 0. And generally what is seen is that this tends to perform better than the individual models. What is generally also seen and prescribed in the literature is it is beneficial when we use independent models instead of having models which are sort of built upon each other. For example, if you use a linear specification and then use a sort of modified form of linear specification, you might not be able to see significant improvements. For training the meta-learner, general approach that is taken is to use a leave one out or a K4 kind of strategy. And for meta-learner, you can use a variety of different algorithms. For example, you can do least square estimation, you can do a k-n regression, a random forest, etc. So we translate this information, this concept of stacking to real-time traffic prediction here. But there are a few issues that needs to be kept in mind when we do it. One is we are dealing with real-time information for a particular quantity of interest, which means there are serial correlations between the data that we have. But for the sake of this exploratory work, we have for now ignored that serial correlation. the way we operate in stacking is that we operate on a rolling horizon basis at time step t. We use data from time step t to t minus w, for example, which is the size of the rolling window, and then predict, for example, for time step t plus 1, 2, 3, and so on. For level 0 models that we have here, we use independent predictors here, very different predictors, which brings in diversity, which brings in novel knowledge, novel information from each of these models. And then we use the inflowing information that we have from the observed values to define the training data set that is required for the meta learner. What basically we do here is that as you are on, for example, time step t, you predict for t plus 1, but when you go to t plus 1, you know what the prediction was at t plus 1, and you also know the observed value of traffic state variable of interest at t plus 1. So we use this information to define a training data set, and then use that training data set to train a meta learner, which combines predictions from the base models to give you final forecasts. How do we train the meta learner here? Currently, we are using two approaches. We are testing these two approaches, but there are a number of possibilities here, which we are still trying to explore. We don't have a definitive answer right now, which one is the best way of going here. We use a non-negative least square estimation approach, which was proposed by Bremen in 1996. What this does is that it assigns weights to different models based on the performance of these models in the past, while making sure that these weights are positive and at the same time they sum up to 1. The sum up to 1 constraint is not explicitly specified because Bremen gave a theoretical solution that constraint is sort of unnecessary. And the second model that we use for meta learner is a k-nearest neighbor regression. We use the method where we use historical data to learn what would be the best prediction for the future data set using the meta learner here. We use this approach to do a case study where we have 24-hour traffic speed data from 10 different loop detectors on Interstate 435 in Kansas City. The loop detectors give us data on space mean speed at every 1 minute interval. And then we use this information to predict travel speed, traffic speed 15 minutes in advance, which means if currently it's 5 o'clock in the morning, we are trying to predict for 5:15 how the speed would look like. At level 0, we use 4 different models. We have a KNN regression, we have a multi-layer perceptron, we have an ARIMA model, and we have a DynaSmart X, which is a real-time network traffic estimation and prediction system which is based on traffic flow theory. The KNN regression is a non-parametric approach which tries to find the best, closest example to the point for which you want to predict in the training data set, and then predicts based on that. A multi-layer perceptron, it's basically it's a deep neural network that we're trying to use here. Then ARIMA model is a classic statistical approach that is used to predict time series type of data. And then we also have DynaSmart X, which is the real-time DTA-based simulation model, which uses a modified green shields model at its core to define the progression of traffic over time. At level 1, we begin with a warm-up period. What we do here is that since in the beginning we don't have the performance information of the individual models, we just take an average of the predictions that we get from the individual models to make the prediction. And then once we have sufficient information on the performance of the individual models, we engage the meta learner here. To train the meta learner, we use a variety of different strategies. Basically, we are looking at the history of the available performance data we have starting from 5 minutes in the past to up to 16 minutes in the past, which means 5 steps in the past and 60 minutes in the past. And then we use these different values to see how the results look like in terms of the performance of these models. We use absolute percentage error as the measure of performance defined in terms of the percentage difference in the observed and the predicted speed values at different time steps. we compare the total absolute percentage error and the cumulative values to see how the total errors and the dynamics of the APE values look over time. And then we also compare the number of instances in which for example, a particular model has the least absolute percentage error as compared to the other ones. So here we are not comparing the value of errors, but we are comparing the number of instances in which the errors that we have received from a particular method is lowest. So these are some of the results that we have. So for example, these are the total absolute percentage error for different detectors in different models. So if you look at one of the figures, what we see here is that the blue solid line is the variation of total absolute percentage error for the non-negative least square meta-learner. And then the orange line is the variation of the total absolute percentage error for the meta-learner where KNN was used. And then the horizontal lines that we see here, these are the total absolute percentage error for different methods which are at level 0. So for example, a KNN, a multi-layer perceptron and a RIMA model, and then a DynaSmart here. What we see here so far is that at least for the non-negative least square one, the absolute percentage error first decrease and then sort of increase as we look back into the history, which basically gives us an indication that going too far in the history probably might not be a good idea, but but at the same time, you still not need to go at least some amount in the history to get the best results. In terms of KNN, what we observe here is that as the history information increases, the error that we are getting from the KNN meta-learner, they are increasing. Of course, in I think almost every cases, there are instances where for some value of the performance history, we have cases where the meta-learner has performed either slightly better or equally good as the best performing base learner model. So in almost all cases, we will have instances where these meta-learner have performed better than the base models. However, at the same time, the improvements that we have seen here in the results, they are not significant, which is sort of discouraging, but I think that is something that can be looked into by taking into consideration a very different meta-learner, which probably takes into consideration the nature of the data that we have in hand. Here we are looking at the total absolute percentage error. At the same time, we also wanted to look at the variation of this total absolute percentage error over time. These are the results for some of the detectors, but we see similar results in other cases as well. What we generally see here in the results is that the meta-learner tend to perform better when we are in a non-breakdown kind of situation, which means we are not in the peak periods of traffic. But when we hit the peak period, specifically the evening peak period, the meta-learner approach does not perform very well as compared to the base models. For example, in this figure, we see that the bottom one is the non-negative least square meta-learner, which was here performing better than the other one in terms of the cumulative error. But when we hit this peak period, then it starts performing worse. This sort of is slightly encouraging, which shows that at least meta-learner is not completely completely useless. It does give you some improvements, but fails to do that in the breakdown situation, which are generally hard to predict as well. We have the speed profile information here for two different detectors. What we see that the first figure here is the observed value of speed over time, and then the subsequent figures are for different methods. So for example, we have the meta-learner 1 and 2, and then for different individual models. And then we also have the predictions that we would have got from an average learner, which basically does is takes a simple average across the level 0 models instead of using some training data to perform. At least what we see here is that using a meta-learner approach preserves the profile really well, specifically the breakdown information, which is of interest to a lot of transportation operations professionals because we want to avoid or sort of get rid of these breakdowns generally. Another important thing that I noticed here is that taking an average across level 0 models probably might not be a good idea. Here, what is happening is that since probably the base models disagree a lot during the breakdown situations, we see that the breakdowns sort of suppressed in the two situations as compared to what we see in the previous ones. We also compared the number of instances where one particular method showed the least APE for each detector. So if I look at this particular, the first detector 1251 value, this basically says that out of all the instances that I had in my data, the meta-learner model with least square non-negative least square estimation performed best for 251 times, and then we have these numbers for each and every. Once we look at this information across all different detectors, what we see is that in terms of the number of instances where the meta-learner performs best is actually the highest across all different models. Of course, the non-negative least square estimation performs better here as compared to KNN. We see actually close to 9% improvement in terms of these instances as compared to, for example, the ARIMA model, which is the best performing model at level 0. So what basically it means here is that while the meta-learner approach does perform badly in terms of, for example, the breakdown situation, that's where the errors are higher. But in terms of the non-breakdown situations, it is actually performing better than the base models. The total values, for example, that we saw in the previous slides, they were slightly on the higher side because of those breakdown situations where the absolute percentage errors were much higher as compared to the level 0 models. But in terms of absolute instances, I think the meta-learner models in general are performing better. Of course, the improvements that we see so far are not very significant, but at least there are improvements by using these models that we have. In terms of concluding remarks, I think, as I mentioned, we do see some improvements, but they are not very significant. This could be because of a variety of reasons. The most important one is the meta-learner that we are using. We are currently using a very basic meta-learner which does not take into consideration of potential serial correlation in the incoming data that we have in hand. But at the same time, we do see improvements in terms of the number of instances in which the stacking models have performed better than the base models. A few limitations as well as avenues for future research is that one, there are a lot of hyperparameters in the models that we have used. Some of them were determined based on a certain level of testing with the data, but we don't know currently what is the best value of these hyperparameters. So probably having a way to tune those parameters would be a good addition. Second, the performance data, we currently did not include any serial correlation. There are a variety of different ways we could do that. For example, we can use a meta-learner which is, for example, a recurrent neural net kind of meta-learner which takes this into consideration. We can also use, for example, a least square estimation with serial correlation information, taking that information into consideration. That probably could help us receive better results as compared to what we have right now. And then in terms of incorporating uncertainty, when we are combining these models, we are currently not looking at the uncertainty information. And I think from user perspective and from even the professional's perspective, having information on uncertainty is of interest. It would be good to understand how we can sort of determine what the uncertainty in the point estimates that we have currently would look like. And then we also would be interested in knowing if we can use a stronger implementation of level 0 models. Currently, we use a very basic implementation. We don't have, for example, exogenous variables like, for example, weather or maybe spatial temporal dependencies from other links or other loop detectors in the area, etc. it would be of interest to understand if combining strong model makes them even stronger, or if the improvements that we see from weak models to a combined model are good, but combining stronger to make another combining stronger models, the improvements are not as good. I think that's all I have for now. Thank you so much. I'm open for questions.
So maybe I'll ask the first question. So how do you currently weight the different inputs to the meta learner?
Okay, when we are at time step, for example, t, we have predictions for time step t+1, t+2, and so on. But when we go at a certain time step in future, we have what the predictions were for those points, and we also have the observed values of traffic speed of those points. We use these values to define basically a training data set. So these are the performance of these models over time, and then we use this value to train the meta learner. One approach that we use is a non-negative least square estimation. So basically we try to minimize the error between a linear combination of these individual models and the observed value, and use the parameters that we have to then get the final prediction of the combined predicted value of speed.
So how would you contrast your approach with a Kalman filtering approach? Because a Kalman filter has similar elements, right? You predict, smooth, and filter, and so on.
I'm not very well aware of Kalman filters. Frankly, I have heard about them, but I haven't used them personally. But I think one important, if I'm not wrong, one important distinction that I can make is that we are using multiple models here. And I think that really brings in novel information from each of those models. We have seen in the results that we have is that we don't see a consistent performance of an individual model over time. But combining these models can help us, for example, get the best of all worlds, get the best values from different models over time, and that can probably boost the overall performance of the models.
Okay. Yeah, maybe it would be helpful to look into the concept of the Kalman filter.
Sure, definitely.
This overall conceptual framework is quite similar to what the Kalman filter does.
Okay. Pratik sent me a private message asking how to get the confidence interval. In these kind of combination, I think that's one of the avenues of future research that I mentioned earlier. I think when we have, for example, a statistical approach where we do have some sort of confidence interval value, I think a combination of them, we can still devise some information. But I think the major problem that exists is with, for example, certain machine learning methods where we don't have that information. To be honest, so when we are bringing in multiple learners, it would be of an issue how to combine these predictions while taking into consideration the confidence interval. But that's something that is of interest to me, and probably I'll look into that in future.
Okay, maybe one more question. We have time for one more. For anyone. Okay, otherwise I think we go ahead with the next presentation by Maria on a joint mode destination choice model to explore factors influencing urban rural tourism trips in Austria.
Hello, you should hear me by now.
Yes, we do.
Okay, and my name is Maria, and I am currently in the last stages of my PhD on urban rural tourism mobilities. And my presentation is much more of an application of statistical models rather than model development as the previous ones. But maybe it's still of interest to some of you, and If not, there might be some nice pictures on it that may alter your future destination choices. Austria is a very pretty country for that. Okay, I cannot move. How do I? Now, okay. So the starting point of my presentation was a research project that we conducted where we looked at the effect of climate change to induce heat waves on tourism behavior of Viennese urban citizens. So in other words, would people leave the city to travel to more refreshing rural areas if it gets hot in the city? And the term that was sort of the framing for this project is Sommerfrische, which is a German word and describes a very old-fashioned Austrian concept of traveling where town dwellers would leave the city for several months over the summer to move their entire family and household to a summer house. But clearly that's far away from the type of vacation that, well, the tourism realities nowadays. So the starting point for our analysis was a bit that when looking at the tourism statistics in Austria and also some of our survey results, without wanting to spoil them too much, it became apparent that domestic tourism within Austria, even for urban citizens that tend to be very like public transport affine, is very strongly car dominated. And we didn't quite expect such high car usage rates, given that 45% of Viennese households did not actually even own a car in 2017. But yeah, why does any of this matter? So tourism is a significant contributor to climate change, and transport is one of the, well, key emission sources. And in the European Union, the car is responsible for around 70% of all tourism-related emissions. And global estimates consider transport responsible for 3/4 of all tourism-related emissions and 5% of all global emissions. But at the same time, at least in Austria, the tourism sector is very based on kind of nature-based tourism destinations. So a lot of like mountains and lakes and activities such as hiking, mountain biking, climbing, etc. So the tourism industry is also very sensitive to the effects of climate change, which basically makes the tourism industry holds a key responsibility to reduce such emissions. And in order to change mobility patterns, we clearly need a better understanding of what motivates people's choices. Like, why do they actually choose the car over public transport, even though it is actually available? So clearly alternatives exist, but it's very hard to, motivate people to also use them. And to support this process, we looked in greater detail at the relationships also between destination and mode choices and the factors influencing both of these, which leads me to my research question, or the one we looked at. So why do urban travelers, despite their predisposition for public transport, often opt for the car when visiting rural areas in Austria? And which destination and public transport features influence their choices? So as I said, we used Austria as a case study and analyzed this for leisure-related trips from the urban area of Vienna to a wide range of different, like rural, predominantly nature-based tourism destinations, which we define as urban rural tourism trips. So to give you a brief overview of the structure, I will start by giving a very quick overview of existing literature in the field of mode and destination choices for tourism trips specifically. And afterwards, I'll outline the methodology that we followed with a special focus on the data mining processes and the model development. And this is followed by the results of the multinomial logic model that we used and the insights that we gained from them on the different motivations behind urban rural tourism mobility. And I will then end this presentation with a very brief discussion on the implications and policy and planning directions that are sort of follow from this. Okay, so clearly, as you can see from this slide, there is an abundance of research on both destination and transport mode choices in the tourism context for either arrival trips or on-site mobility. But so far there isn't really much research that looks at tourism destination and mode choices in a combined interlinked manner to also understand how these decisions influence each other and how they are both affected by supply and demand side factors, and yeah, also supply side factors from tourism and transport side. Yeah, also most of the previous studies only included a limited number of influence dimensions or attributes groups. So you see that we considered these 5 different attribute groups and sort of try to understand a bit which ones, where sort of different studies put their focus on. And from that, we can see that most previous studies on mode choices used some form of regression or multinomial logic model. However, none of them really included destination features as a factor that could also influence mode choices. So they mainly focused on transport features. Previous studies on destination choices used a much wider range of different statistical models, but usually only covered transport features in a very, very general way and not trip specific. So it's more like the general accessibility of a destination, but not how can I actually get there. And most of the studies, previous studies that combined both choices used either bivariate probit models for like broad categories of destinations. For example, do I stay in the city or do I also go outside? Or did I visit one destination or more than one? And we try to sort of address these different research gaps and use the multinomial logic model that allowed us to integrate spatially specific destination choices with a lot of different destinations, as you can see in the lower row. With their respective trip characteristics and also destination features. And so you can see that we basically really try to integrate a range of different dimensions. So among all the possible influence dimensions, the main question was a bit, okay, which one should we include? And we looked into a range of different studies on various behavioral models, including rational choice or random utility theories, and also the theory of planned behavior and tourism mobility paradigms. And try to sort of collect a bit what kind of factors we could include in such a model. And which kind of data we can also actually access. So this is a bit of our collection of different factors. So the uppermost 2 categories are sociodemographic variables and socio-psychological factors, such as values, attitudes, and preferences. And they have been the focal point of many empirical studies on both destination and mode choices in the past. But especially for sociodemographic variables, more often than not, the models actually are more strongly defined by the subjective factors rather than the objective ones. And so sociodemographic determinants seem to be a little troublesome sometimes in actually explaining behavior. And then we also considered, mainly from tourism research, the various travel motivations and also experiential expectations that people might have when they go somewhere. So what kind of feeling do they expect? And the situational context, which they also construct through their personal travel preferences. And this could include like the trip duration, complexity, what kind of accommodation, the luggage that results from their travel motivations and activities, etc. So certain travel motives or activities also involve traveling to remote places with few people and very low public accessibility, which might conflict with public transport usage. But we also saw that public transport can actually also enhance the travel experience, for example, for non-circular hiking or biking trips. And the last 2 categories basically both include supply side factors. So we looked at attributes of car and public transport trips, such as travel time and speed or costs, the required number of changes, or frequency of intervals, and other elements like this. And yeah, as I also said before, most mode choice models usually disregard destination features, but within a tourism context, they seem to be very important, which is why we also try to include those factors. But yeah, this is basically an overview of all the dimensions that could play a role in the connected choice of destination and mode choices. Unfortunately, it wasn't possible for us to include all of these dimensions since data availability is a major constraint, clearly. And we have mainly worked with survey data, hence the yellow demand side factors. But in order to also get information on the gray supply side data, a mining process, like data mining process, was needed, which I'll briefly outline in the methodology section that will follow. Yeah, so within the beforehand mentioned project, a quantitative survey was conducted with roughly 900 Viennese participants. And that one was informed by qualitative focus groups and also telephone interviews beforehand. The survey itself was conducted online and inquired many information on people's socio-demographic background, their general travel preferences. And within one specific action, people were asked to name their last trip to such an Austrian, like rural Austrian tourism destination, and then include further information on trip length, chosen transport mode, etc. So based on these information, we geocoded the destination location using a Google Maps integration R. But yeah, since we also wanted to account for supply side factors specifically for these destinations, clearly the survey data aren't enough because you can't ask people all those questions. So instead, we had to merge data from different sources with the self-reported destination and mode choice data from the survey. And we used a number of different sources that I also placed there. So in order to get information on trip characteristic for both car and public transport alternatives, we used data from the Verkehrsauskunft Österreich, it's called. So it's like a general travel query system. And we basically developed a matrix of 21 origin districts in Vienna times the 295 destinations in our data set and ran a query for each combination of origin and destination for both possible transport modes, and would receive data such as travel time, the number of changes that is required, the frequency of intervals, how often can you actually go on that route with public transport system in Austria. So they basically use real life transport data for the train system in Austria. And you can run these queries to sort of check routes and also the quality of those routes and how often they go, etc. Yeah, so we would get that for both the car and the public transport alternatives. And then we used OpenStreetMap queries for all of Austria to create a data set on tourism amenities, such as hotels and cafes, etc. And they were then sort of merged with the destination by a spatial joint in GIS. So we would draw a little circle of 20-minute bike distance from the center and sort of counted the number of amenities for different categories, accommodation, gastronomy, etc., that fall within this radius to sort of understand how high the density of tourism infrastructure is that is accessible within 20 minutes of biking or 60 minutes of walking. And then we conducted like a Scotty queries and manual internet search to also retrieve information on in-destination mobility offers, such as cable cars, bike rentals, boat rentals, and all sorts of information that you can only get by searching for them manually. Yeah, and ultimately we merged all this data together through unique identifiers of destinations and put them into a multinomial logic model. And we chose that specific model type because of the disaggregate and revealed preference nature of our survey data, because of the availability of spatially specified attributes for each specific destination on both trip and destination features, and also because of the large number of destinations which were not categorical. Like we didn't have a rural versus urban, but they were like a large number of different rural destinations. Yeah. This is just a very short picture of the sample description, which I will not focus on too much. We basically used a sample, or got the sample through an online access panel, which was representative for the Viennese population by age and gender. As you can see that the numbers are the same. But yeah, the sample participants were more educated than the average Viennese citizen. And also the sample is not representative for all Viennese travelers, although 80% of the people in our sample said that they actually did visit one of these places and also provided information on it, which I think is quite a large share. Okay, with regards to the model development, yeah, this started off as a rather complex process because of two main aspects. So the first one is that we had a large number of alternatives. As I said before, we had 295 different destinations in our data set, and yeah, 2 different ways of visiting each of them by either public transport or car. And second, throughout this entire data mining process, we ended up with a large number of possible candidate variables for the different factor dimensions, which amounted to 341 variables. So to minimize the complexity and number of variables in the model, we started the model development process with the pre-screening of suitable variables. And to do this, we employed semi-partial correlations with the different choice variables, so mode and destination choice, to estimate their predictive power in the model. And later on, we compared that sort of in an ex post pairwise comparison between the t-values of model parameters and semi-partial correlations, and found a fairly good match, which made us pretty confident that we did a good choice there. So yeah, in terms of model structure, we considered that the combined choice of mode and destination choices may generate a nested structure of alternatives. But we tested this, and yeah, the nested specification revealed that the nest parameters did not significantly differ from one, which is why we rejected that and chose to go with a very conventional multinomial logit model, which takes the following form. Okay, I will continue with the descriptive results. So the total number of trips that were in the sample were 692, 24 of which were done by public transport and the rest by car. 64% of respondents traveled with their partner, but possibly also other people, such as children. The average trip distance was 181 kilometers, reached with an average speed of 85 versus 56 kilometers by car and public transport. And for a surprisingly large number of trips, train connection was actually available, which we attribute both to the high railway network density in Austria, but also to the fact that within our geocoding, we used train stations or central locations as input places because we did not have address-specific destination data. Yeah, and many of these places also have different types of in-destination mobility offers available, which kind of reflects the kind of tourism destinations that people went to. So they were looking for mountains and hiking opportunities, but also lakes for swimming, etc. Okay, so one interesting aspect that we found already within the descriptive analysis was the relationship between travel distance and travel time. And the screening of variables indicated a strong correlation between distance and duration, which probably isn't as surprising. But when we tried to disentangle the effects of distance and duration, we calculated the specific travel duration, which is sort of the inverse of speed, which is shown in the figure here. And that shows a pretty systematic difference between the car and public transport. While the car is faster in most cases, the speed difference to public transport actually diminishes as the distance increases and disappears at about 400 kilometers. And that is largely due to the fact that Austria also has a high-speed infrastructure available, which is used for longer distances. So ultimately, the normal distance was left in the model, but instead of duration, we included the specific travel duration or inverse of speed. So the following slide basically shows the main modeling results. And yeah, the figure shows that, the results with regards to the strength and direction of each of the variable influences on both mode or destination choice. And just to sort of, warn you, the rho square is very low for this model, but it's also not really a suitable diagnostic criterion in this case, because it automatically or inherently decreases with an increasing number of alternatives. And since we had such a large number of alternatives, that was kind of to be expected. And since we were interested in the predictive power of the different person, household, and destination features, the t-values of all parameters and the sum of the t-values represent the better diagnostics in our case. And despite the high number of predictors, the model is still fairly robust. And we tested that by comparing the t-values of the parameters with those of the bivariate correlations between the parameters and the dependent variables. So in terms of actual content, sort of, the results provide some new insights into what affects destination and mode choices of urban-rural travelers in Austria. So among the socio-demographic variables, the only ones that were actually left were mobility tools, such as car or public transport discount cards. And they sort of show that tourist mobility choices are related to people's habitual mobility, despite sort of the difference in context that they actually are very much used to using public transport at home, but not within the rural destination. The travel situation affects people's mode choices through two variables, both travel company and the type of accommodation. And once people travel with a partner, it decreases the likelihood of using public transport, which might be caused by the fact that traveling with more people increases the cost proportionally, basically, while the car doesn't. And on top of that, privacy and the enjoyment of the trip together sort of as a group and the intimacy among people also favor car use for groups of 2 or more people. Private accommodation in our model increased the likelihood of public transport usage, which came a little surprising to us. But former studies or former analysis have also shown that many people who travel to these places have kind of family or friendship ties to the rural areas. So they might sort of gain access to mobility through their family or friends at home. And our study, as much as other studies before, confirmed the importance of travel distance and time. And the two main findings in this respect are that the longer the distance, the lower the probability of basically visiting a destination at all. And the longer the distance, the higher the probability of using public transport instead of a car when visiting. And overall, the results show that public transport travelers are less sensitive to travel distance or travel times than car travelers are. And this might be because of the steep increase of travel speed with public transport over longer distances, but clearly also the enjoyment of secondary activities such as reading or sleeping or talking, on the phone, etc. And public transport travelers within the Austrian context are almost insensitive to travel speed, but they are very much sensitive to the type of vehicle. So being forced to use a bus instead of a rail connection is sort of perceived as a downgrade in terms of travel quality. And car travelers, in contrast, are quite sensitive to travel speeds, and to them, low car travel speed usually implies driving on small rural roads, which can be, pretty exhausting on longer distances. So with regards to destination features, we see that there's a lot to be done also within destinations to attract visitors and shape their mode choices. And the most influential variable in that respect was the quality of web appearances and availability of information points, both with regards to mobility information, but also general tourism information. Mobility offers in the destination also matter and illustrate, what kind of activities people are looking for. The availability of destination guest cards, including free public transport, also tends to have a positive effect. Beyond the individual benefit that arises from such cards for people, it also demonstrates a more systemic destination quality, because they kind of portray the destination as a well-connected, engaging, and forward-thinking community, which is probably a worthwhile public perception. Okay, and with that, I would already go to the summary of results and just, basically my last slide. So to sum this up, the trip characteristics seem to be more influential on tourism choices than socio-demographic characteristics are. And while mode and destination choices are often treated separately in tourism research, our analysis shows that they are actually intertwined and that there are sort of links between both choices and the different features of them. And yeah, both destination and transport features affect the combined choice. Yeah, with regards to travel time, we see that public transport travelers are more willing to accept long distances because they can use the time for pleasurable things, but also because they benefit from high-speed trains and longer distances. For a destination, this sort of means that public transport has actually the potential of attracting visitors from even further away, if they can sort of offer a direct train connection, or at least a good train connection. And yeah, public transport operators are kind of required to provide comfortable and affordable train connections to such destinations. And yeah, the substitution of some of these rural branches in the past is not really helpful in that regard. Yeah, with respect to destination features.
One more sentence. We need to give some time for questions.
Yeah, I could basically, I mean, it's all written there, so I can also just stop here. Destination features are clearly also important, and especially in tourism context, it's very important to consider them sort of as choice factors and not only look at typical transport features such as cost, time, etc. Yeah, and tourism mobility is connected to everyday mobilities, both in terms of mindset, but also locked like path dependencies created by cars and public transport tickets, etc. And that is basically it.
Yes.
So yeah, thank you for your attention.
From Pedro, he asks, the rho squared is low, but what about the first preference recovery indicator, globally and by different traveler types? Is the observed OD matrix sparse? We know that MNL does not deal well with such matrices. The choice set is a very relevant issue to consider, I suppose.
Is there somewhere I can see that question? Because I did not catch all of this. Yes. But I can't open the chat window.
Yeah, so then the question is, maybe we start from the back. So the choice set, how did you define the choice set? How did you identify the relevant destinations?
We basically asked people for the destinations that they have last visited, that they sort of consider like in rural destinations, and they would just give us the name of the village or town, which we would then sort of use in the geocoding process, or So it was given by the survey respondents.
What about the out-of-sample predictive ability of the model? Since the rho squared is low, how does the model do at out-of-sample prediction?
I'm not quite sure I understand that question.
So have you tested your model to predict
no.
held out data?
No, we haven't really used it in a predictive way. We've basically only tried to explain past choices, but there is no sort of future prediction element in it.
Okay. Then I have one more question. So how do you incorporate the duration of the stay at the destination into your model?
I mean, that was generally a little difficult. We only had that as a categorical variable, which was either it was a day trip or it was a short trip of 1 to 4 days or longer than that. So we basically included it as a dummy variable in the model. But okay. I think for future studies, we would probably also ask for a more detailed, specific day kind of information, because that variable didn't show to be very important. And I think it could have been.
Okay, so I think if there are no more questions, I think we can hand over to the next session. Thank you everyone for attending these 4 presentations.
My name is Ali Nadi. I'm a researcher at Delft University of Technology, Department of Transport and Planning. And today I'm very honored to be a co-moderator of this session together with Mahmoud Mesbah from Amirkabir University of Technology. The topic of this session is shared economy and micro mobility with a 3 at the end, which reminds me that we already had 2 other sessions with the similar topics. which means to me that this is a very hot topic in transportation research field. And it makes sense to me actually, because maybe 5 or 10 years ago, we could say that shared mobility is the future of the transportation, but I believe that now we are living in the future. And that's very nice that we can see different researchers from all around the world bring different aspects of this mobility into scientific research, from optimization, network design, demand estimation, you name it, behavior modeling, etc., so that in practice also they can get advantage of the findings in the scientific researches. And looking into the topics of the presentations, so I couldn't be more willing to listen to this presentation. But before jumping to the presentations, I would like to hand over the session for a moment to Mahmoud Mesbah for his introduction. Mahmoud, could you take the floor?
Okay, thanks, Avi. Just welcoming again everyone to this is the third session of track 5. I'm Mahmoud Mesbah. I'm from Amirkabir University of Technology, former Tehran Polytechnic. I have a background in civil engineering and transport planning, and more recently I've been interested in transport modeling, the optimization of transport systems, public transport, and application of advanced technologies in transport. Today, just from the program you saw on the website and what you can see here, there has been a slight change. The third and fourth speakers swapped, so we would have Yiyang Lu presenting first, and then followed by Chng Wang. That's all for today. If you're planning for listening to either of those presentations, just set the time for those. Without further ado, I'll hand over back again to Ali for the first presentation.
Thank you, Mahmoud. So our first presenter is Felipe de Souza. He received, he will present on an optimization-based strategy for shared autonomous vehicle freight repositioning. And he received his engineering degree in control and automation engineering, and he is a master in engineering in automation and system engineering from the Federal University of Santa Catarina, Brazil, in 2008. And he also got his PhD degree in transportation system engineering from the University of California in 2018. And since then, he is a postdoc appointee in Vehicle and Mobility System Group at Argonne National Laboratory. His main research interests are traffic modeling and control, transportation system simulation, and dispatching algorithms for on-demand mobility services. So, Felipe, could you take the floor for your presentation? I will just stop sharing for a moment.
All right, everyone, it's a pleasure to be here. My name is Felipe de Souza, and thanks for the introduction before. I'm here to present the presentation on vehicle repositioning. This is work conducted together with me and Josh at Argonne National Lab, and Murthy and Kara Kokeman and UT Austin. So let's discuss about a little about it. So then we are talking about repositioning. What do we mean by that, and why do we need to do that? So, so usually, like we need to undertake repositioning trips due to imbalance on demand, where the trips happening on the, let's say in systems like Uber and Lyft, or like you provide a door-to-door service. They would just request a trip from some origin where they are, some other destinations where they want to go. But then this is not evenly spread on the network. So then let's say one common pattern is, for example, in a monocentric city like this one portrayed here. In the morning peak, people are going from the suburban areas to downtown. So then usually they request the vehicles to pick up them at suburban areas. So then like we need vehicles to be available close to the suburban areas. And then this person is pick it up and then it's dropped off at downtown area. So then these vehicles getting accumulated at downtown area. So then in the end, what we have, if people don't, either like let's say Uber or Lyft driver themselves, they don't go to another place with higher demand, or they just stay there. We have vehicles accumulated on downtown area where we don't have enough vehicles where the requests are coming, which is on the suburban areas. And then the trend may reverse on the evening peak. So then we need to do these trips to actually, so to counterbalance that, so then we can have vehicles closer where the pickup locations of the customers are going to be, or it's happening at a given time. So then what's the specific goal? So then we want to move these vehicles close to their pickup location, because then with that we can minimize customer wait time. But then at the same time, we don't want to increase that much the empty miles or unloaded miles. If for example, if it was a human-driven video, on this research we're targeting if that was AV. So then let's say that we think that there will be a lot of demand in a particular area. We send a lot of vehicles, but then the requests don't come. We just waited resources, right? So we moved the vehicle to a place, and this vehicle didn't get more trips at that location to other place. So then in the end, we just added VMT, while you're not helping much in minimizing customer wait time. So why is that not straightforward, or like what influenced that? So this depends a lot on the prevailing demand, which is a challenge because we never know how exactly this demand is. Also, maybe, well, this can be mitigated a little bit through the matching algorithm, but then depends on how vehicles are assigned. And finally, what's the travel time from each location to each location? So then we want to make short trips for repositioning, or even for pickup trips, and so on. So, let's let me introduce the repositioning strategy itself. So, as I mentioned on the title, it's an optimization-based strategy. So, what are the variables? So then, first of all, we consider here that we have a region divided into zones, smaller zones. And most of the times, maybe even a traffic analysis zone of the MPO, like that's already in place. But then this can be, we have zones. So then, like in these zones, we have all the variables defined. So how many vehicles are they, and what's the travel times between each zone, and so on. So our decision variable here is XYJ, is that how many vehicles we will reposition from zone I to zone J, which must be integer. TYJ is a travel time from zone I to zone J, and this can be, we are considered here that we have travel times, but then this can be any other measure of cost deemed appropriate. SY is the supply of vehicles in zone I, and then this supply takes two types of vehicles. So then we consider the supply on zone I, the vehicles that's already there at zone Y, waiting for new trips, which we refer to as idle vehicles. And then those vehicles also that is doing any other operation, let's say another vehicle, it's going to another zone K, doing a pickup, and then we will end up doing a drop-off at zone I. We are already considering that this vehicle eventually will be available at zone I, and then we are counting that as a supply of vehicles at zone I itself. And finally, VI is then, this is the actual number of vehicles that's idle at zone I that it's either available to pick up new trips, but actually also if I want to reposition one vehicle from one zone to the other, from zone I to zone J, we need to have idle vehicles to do that. So then even though like there might be vehicles coming in the future, by now we can only dispatch the idle vehicles at zone I. And finally, and then this you'll talk a little bit later how we define that. Fy is a minimum supply at zone I. So then this is like the least amount of vehicles that we want to be available at zone I at a given time. So these are the variables, and then what we do is that at fixed time steps, we solve the following. I think it's a bit hard to see, but then I will explain one of each soon. We solve the following optimization problem. So we want to minimize total repositioning time. That's the objective function defined here. So then for that's the end goal. And then the first constraint is saying that we want to make to take the decision to change x and y, x, y, j, in order that we always have for all the zones a number of vehicles available, or the supply or the future supply. So then we can see here that we have the supply as of the time that we cast this optimization problem, and then the base on the balance of vehicles that is coming and leaving this zone. We want to have that higher than the minimum number of vehicles or the minimum supply at zone I. So in this way, if you can do that, all the zones you'll be with enough vehicles to serve the demand. And finally, as I said, we can only reposition vehicles that are idle, even though maybe SY is greater than VI. Like we can have a supply of one zone greater than the number of idle vehicles, but then in the end, when we take this decision, we can only dispatch idle vehicles, and this is what this third constraint is capturing. And finally, X, Y, J must be integers and non-negative. So yeah, so then these are the bounds of Xij. So then it's just like with non-negative. Of course, we cannot have negative vehicles being repositioned from one zone to the other. So then the idea of it's to solve this optimization problem, which I'll summarize later how we do that. So then. One key aspect here is that how do we set Fy, and then what could be the problems if you set this Fy to be too high. So then, as we said, ideally we need to set Fy according to the demand. So then, if like one specific zone has no incoming demand, and incoming demand here, I mean a pickup location of a trip. So then, let's say you're now door-to-door service like Uber, you go from A to B. We want the vehicles to be close to A. So then in the end, if one location has no incoming demand, we don't have vehicles there. But then if it's higher, then we, if the demand is higher, then we want to have more vehicles there. So then, for here, we use a very simple approach that we are running this management system like we're controlling the fleet, serving requests, and then while we can see what happens on the short term backwards, right? So then we are going like, let's say it's 11 a.m. and then we can see, for example, at a given time period, let's say half an hour, how many requests happened on this past half an hour in each zone, and then this we assume to be the prevailing demand at that zone, and then more or less we are assuming that this demand will prevail into the short term, into the future. Of course, we mentioned here that we really don't know what the demand will be. We plotted here like the yellow, that to mean like we sort of like made a good guess, but then like maybe it can be one location that had the high demand for a while and then it's decreasing. Maybe we are in that case, if the demand goes like this blue line here, we are overestimating the demand. But then it's a simple approach that you're just looking at what's happening in real time and then interpolate that to the future. But then there's one another potential issue with that is that we cannot set this FY too high. Let's say that we have only 50 vehicles in the whole network, and then we need, let's say, at least 60 vehicles in each zone. Let's say it's very the demand is very high. There will be no way that we can serve this demand. In this case, probably because like the demand is much higher than how many vehicles we have to supply this demand. So what we need to do in this case is that we need to reduce Fy. So then in this case, we cannot even solve this optimization problem because it would be infeasible, right? There's not XYJ that we can, for all zones that we can supply that. So what do we do? So then we sort of know how many vehicles need to be moved to any given zone, like if the zone has lower supply than demand, lower demand than supply, and how vehicles that a zone can supply. So then either one zone is sinking vehicles and the other zones are supplying vehicles, and then we cannot, we always need to match this balance. So then we always can check that. So then what do? That we see if this inequality holds. If it doesn't, what we do is that we scale down for one alpha, like we do. We just reducing by its small steps until we find what will be the prevailing demand that we can turn this optimization problem feasible. So just a summary. So then at every control time step, let's say every 5 minutes, 10 minutes, or so on, we are managing this fleet. So then we can know what's the supply and how many vehicles idle we have on each zone. We'll obtain the predicted demand based on this that time window that I explained. If we can check for feasibility. If not, we scale the demand so as to be feasible. We build and solve this optimization problem, and then we dispatch vehicles from zone I to zone J based on the XYJ. So although these decision variables must be integer, we can always solve this as a linear program, as long as the Fy, I mean, all the constraints levels that we have on this optimization problem are integer as well, due to unimodularity, which I'm not going further here. So let me share some of results that we have. So we test this in a let's say not a very large scale model, but then a quite sizable network in Bloomington, Illinois, which has 3,900 links, 2,500 nodes, and then 185 zones. So then our decision variables, which is like every XYJ for every zone as origin to every zone as a destination, there will be 185 times 185 decision variables. So it's not very large, but then it's quite sizable already. So then we always use this 30 minutes rule for the demand estimate. We take reposition decisions every 10 minutes. And then we test 3 different fleet size, and then we enable and disable the reposition strategy for this case. Not going to much further details here, but then we are doing this on top of Polaris simulation platform, and then we use the matching algorithm. We are not considering dynamic rate sharing, and the matching algorithm is we are trying to assign to the closest vehicle as the request comes. So summary of the results here. The empty VMT, that's for sure it will always increase because you're moving vehicles because of some expected demand. So it does slightly increase, but then increases slightly. From the percentage of empty VMT goes from around 30%, without repositioning to around 33% with repositioning, as you can see here for the 3 different fleet sizes. Respect the waiting time, that's what we want to reduce. It reduced quite significantly from around 4.5 minutes or between 4 and 4.5 minutes depending on fleet size without repositioning.
Excuse me, Felipe.
Sure.
Could you wrap it up because we have to have some room for question and answer?
Sure.
So, yeah, thanks.
Quick, thank you. And then, so the wait times reduced. Yeah, and then even we exchanged a little bit from reposition of MT, but then you see like the share of pickup is lower because, you know, like always the vehicles are closer to the demand. So I think I'm going quickly here, but then so then this is the waiting time and the distribution for different fleet sizes. It got reduced, and also because we have a higher if the pickup trip is too high, the trip may be rejected. But then applying this optimization strategy, the repositioning strategy, we can serve more trips over time. And then just to wrap up, just showing here like some of the patterns of what happens. So then this is a small video. So then this is like what's happened on the morning trip, that we have this area here that's sinking a lot of vehicles, and then in the end, that's concentrated the vehicles. So then what's happening that once the trips come there, and then it tries to spread these vehicles to get closer where the pickup locations are. So just and then fine. I skip this one. So just like to have an idea what happens. So then if we don't have repositioning, this is how like vehicles will be organized by the end of the simulation. And this is what happens with reposition. So then, yeah, I think with that I can I can finish the presentation because of the time.
Thank you, Felipe. Any questions? You can write down your questions in the chat box so that I can read it for Felipe and maybe he can. Yeah. Kara asks, what is the ratio of the travelers or trips per SAV?
Yeah, in this case here, we have sort of like a baseline in Bonito model, but then we have more or less in this scenario, 10 to 15% of the trips are SAV, whereas maybe I don't have all the numbers here, but then most are SOV. So then this is one scenario that we have the share of trips being SAV is slightly higher, or I mean, instead of like being around 2 or 3%, it's like around 12% of the trips are SAV.
30 minutes is long time to wait to become unserved. Do the caller know early, like we do with Uber or Lyft, so they can find a backup mode?
Sorry, I think the last slide here, it's not correct. We set to 10 minutes.
Okay, 10 minutes waiting time.
10 minutes, which is true. But then, as you can see, yes, so then that would be too high, but then let me show you just quickly. So then these are the waiting time distribution. So then we can see here that most of the trips are served within 3 minutes. There are like a few that's exceed 10 minutes because this is like as the predicted travel time before the trip starts. So then if it gets a little bit longer, but then, you know, it's our caps are around 10 minutes, and then most of the trips are less than 5 to 7 minutes, as you can see there.
Okay, Mahmoud asks, can you elaborate on the balance between empty vehicle kilometer vs increase in the waiting time?
Sorry, the empty?
Yeah, empty vehicle miles or whatever you calculated vs the increase in the waiting time.
So I don't know if I get the question, but then if we don't have this repositioning, the empty miles will be slightly lower because we don't have a reposition enabled. So then we usually don't quote unquote waste some miles to get close to the demand.
Yeah,
so then, but then.
Yeah, for instance, you said that the empty mile traveled increased like 3%, right?
Yes.
But the waiting time reduced, like, I don't know, maybe it reduced to 10 minutes.
Yeah, 23%. So, yeah, what happened, and I think I can show you in the video that we always are moving. Let me see, like one, maybe earlier. No, I think. So we always keep moving the vehicles. So you can see here, like these red trips here. We are always trying to move vehicles closer to where the pickup you're going to be. So then in the end, the pickup trip becomes smaller because like usually the vehicles are already very close to the pickup location. So in the end, we increase because, you know, if we made like, for example, some of these red dots here that they are traveling, they go from a location that they have, in the end, they're not getting a new trip. We just wasted this mileage, right? Because it's not getting newer trips. So then this increased slightly because of that, because it's sort of dependent on how well we can predict the future demand. But in the end, if we have good predictions, we always will have vehicles very close to the pickup location. So then it's sort of like you ask your Uber to come to you, and then Uber is right to your door. That would be the ideal case. So then it's sort of like it already made this pickup trip before. I don't know if that answers this question.
I may have another question. So, okay, Irena asks, do you assume that there is enough space in the road for vehicle to stay idle and stop anywhere?
That's a good question. Yeah, we assume so that they will be idle and waiting either in a parking spot or somewhere that they are not impacting the traffic by that time. So I think it's we assume that we have enough storage on the roads.
Yeah, so Luis also asked that it seems to me that long waiting time are more of an issue, and how much would it rebalancing reduce long waits? I think you answered already this question.
Yeah, this is the overall change. Around.
So Luis says, I think he said that the rebalancing strategy reduced waiting times by 23%. Is it true?
Yeah. Okay.
I
mean, of course, it varies by case and then the prevailing demand. You are doing some preliminary runs in a larger area. It's sort of like this is the same, maybe 20%, 18%, but then, it does reduce most of the time.
Mm-hmm. Are the vehicles moving around, or they just start the repositioning once a demand is there?
So the thing is, we do the recent decision, like say every 10 minutes, and then we always have sort of a predicted demand. So then if one location had higher demand on the previous, in this case, half an hour, we may send the vehicle if there's not enough vehicle on that specific zone. So then we move the vehicle if there's no vehicle there. So then I don't know if that answers the question, but the idea here is that we are trying to move so as to match the demand.
Yeah. Luis, you are unmuted. So you can also re-ask your question.
Yes, what I meant isn't how much do average wait times reduce, but how much do long wait times reduce. So for example, wait times over 10 minutes or wait times over 5 minutes, that may be more important as a customer service metric than the reduction in average wait times.
Yeah, that's a good question. So then I think this is the distributions with the red being with that enabled and then blue with disabled. So then we have quite a, I mean, you can see here, let's say for 700 vehicles, a significant share that is higher than 5 minutes. But you can see here that when I have this enabled, we sort of reduce that by roughly a half. So then that's what happened. But then I would say that there are like two things also going on here. So then if the fleet size is too small, sometimes we cannot serve. And then actually maybe the matching algorithm also plays a role. So then, but I think, yeah, I mean, it's a good question. I think it does reduce, but then also in those situations, also maybe the matching algorithm can also play a role on that.
Thank you, Felipe. I think it's time to move forward to the next presenter. If others have other questions, you can approach Felipe later.
Thank you.
So
yeah, great. So our second presenter is Jafar Baraga. I start by apologizing if I mispronounce any of these French words. Jafar Baraga is graduated in civil engineering and mobility planning from École de Pont, Paris, and he joined BDCom in 2016 and obtained his PhD in 2019 in demand modeling and transportation economics. His research interests focus on assessment of the socioeconomic impacts of new mobility services. He had contributions in simulating demand for autonomous taxis, coupling a BDCom agent-based model with a macroscopic model. On the other hand, he's teaching discrete choice analysis and prediction of individual behaviors in the École de Pont Paris Tech, or ENTC. Currently, the leader of the research team and economic analysis of mobility systems and the assistant director of the department of the Econometrics and shared energy at BDCom. He's also involved in several national and European projects of arcade and looking forward to hearing the presentation. Right, so
I start.
Now,
let's start.
Illinois, we're going to Paris, I guess.
Yeah. Do you see my screen?
Yeah, we do.
Okay. So thank you for the introduction and thank you for giving me the opportunity to present my work. So it's about economic and socioeconomic assessments for strategies to replace conventional public transit with on-demand ride-sharing service, and specifically in low to medium density areas. So the work was done by me and Alexis Poulies from LVMT, which is a lab in Paris too. So as a quick introduction, so in low to medium density areas, we have very specific constraints and needs, and existing transit modes are often suffering from low demand during off-peak periods, but not zero, so we have few passengers to serve, and transit modes also consequently have often low quality of service with long headways, long waiting times and transfer times, and low loadings, which makes the service less attractive for passengers and less profitable for the operator. On the other hand, intermediate transport modes, including DRT services or for hire services, in general ride-sharing services, are emerging based thanks to two main characteristics. The reduction of transaction times, which are for me the times of connection between the passenger and the vehicle, and the reduction of costs for suppliers and customers, which comes from the fact that these services are on demand and enabling then using vehicles more efficiently. So we point out two main issues. The first one is to determine when it is relevant to replace a bus service, which will be noted CPT for conventional public transit. So when to replace a bus service with a ride-sharing service, which will be noted DRT, considering the perspective of the main stakeholders. And second question is to determine what are the optimal operating conditions, and here I mean the fleet size, vehicles capacity, and tariff. We will see it later. So which conditions that maximize the gain for these stakeholders. In order to give some answers to these issues, we propose a technico-economic model, which is coupling an agent-based model that was published before that simulate the behavior of the RTs and the traffic equilibrium, so the demand-supply equilibrium, and a second model, which is an economic optimization model, which determines the optimal conditions, operating conditions for the service production. And in order to assess this model, we apply it on a real case study, which is a territory in Paris region with a real network and a real demand. So about the main assumption of the model regarding the operational conditions and production process, we assume then that we have a ride-sharing service. So we assume that also that trips are shared. We assume that it is a station-based service. So stations are the unique access point to vehicles. We consider that the fleet is homogeneous, so same level of comfort, same acceleration, deceleration, and etc. And we consider that the travel time is exogenous, so assuming that we will not consider congestion, but constant travel times on links. And finally, we assume that vehicles are assigned to passengers in order to, in an egoistic approach, in order to maximize the utility of the vehicle. So the vehicle chooses to be assigned to some passenger if it maximizes its utility, and in this utility we include the load of the vehicle, the empty distance, which should be minimized, and the waiting times, which should be also minimized. So this part this part concerns the agent-based model, and then for the strategic decision, we assume that the implementation of the DRT service instead of the CPT line is allowed if and only if subsidies for the RT are lower than or equal to subsidies that were given for the CPT line. So we assume that we will not put more subsidies for this DRT service. And for operating conditions, as I said before, I assume that the decision maker can play with fleet size, with vehicles capacity, and with tariff in order to determine his strategy. Finally, about the mobility assumption on mobility demand, we assume that passengers are sensitive to fare, travel time, and waiting time, and that the demand of DRT service and CPT are elastic and depends on the generalized cost. So that means that the demand for the RT is function of the demand of CPT, and of generalized costs of DRT and CPT with an elasticity epsilon. So the demand to go from I to G using DRT is given from this formula. And we know also that for on-demand services, the waiting time of vehicles depends on demand. So specifically when we have on-demand services, for higher volume of demand, for higher number of vehicles or lower number of vehicles and fixed demand, the waiting time will be modified. Or if we have, for a given fleet size, if we have higher demand, the waiting time will be higher. So we know that we have this interrelation between demand and waiting time, and based on that, we can say that the traffic equilibrium exists, and we obtain this traffic equilibrium based on a fixed point problem in demand or in waiting time. So moving to the economic model now. I consider that I have a problem. I define the problem for each stakeholders, and in these stakeholders, I consider the operator, passengers, environment, and society. And in society, I include the gain for operator, passengers, and environment. For the operator, I consider that the main problem, and it is the main problem for the operator, is to maximize its profit. And I define the profit as the difference between revenues and costs, while including in revenues from selling tickets and revenues coming from subsidies from public authorities. In costs, and costs could be divided into fixed and variable costs. For passengers, noted PU, the passenger surplus is given by the difference between the current generalized costs, so the generalized cost of the RT, and the generalized cost of CPT, assuming that it is the generalized cost that was accepted and desired by passengers. And for environmental surplus, I assume that it concerns only avoided and additional emissions of CO2 in terms of environmental impacts, and we measure the impacts of replacing CPT with DRT. And finally, for total surplus, it covers the gain for and the benefits of the service provider, which is the profit of passengers' gain and of our environmental benefits. The problem for the operator will be to maximize profit by considering that I have a constraint of subsidize. As I said before, that subsidize of the RT is lower than subsidize of CPT. I consider that I have a maximization problem for passengers and a maximization problem of gain from the environmental aspect. And for society, I consider, we assume that the maximization problem will be constrained also by the profits of the operator, assuming that subsidies will be given, but with a constraint that the service is at least not zero for the operator. So it's at least a reliable form. And finally, the main scheme here is simplified. So we have here the generation of conditions, so of fare, fleet size, and vehicles capacity, which are included in the agent-based model, which is given here in the operating costs is a function of demand that is calculated, and then it is included in the economic model, which is an optimization algorithm based on simulating annealing algorithm, and based on that we have a convergence criteria in terms of maximization of profits depending on the problem. So we run it for maximization of operator profits, of social welfare, welfare, and etc. Passengers' benefits and environmental benefits. And as outputs of this model, we have the optimal supply conditions, which are fare, fleet size, and capacity. So I will move quickly to the application case. The application case is a study case in the southwest of Paris. So here we have here a train station, the Black Cross. Here we have a scientific cluster with universities and labs. The idea is to replace bus lines here with dedicated lane using this green lane with a DRT service, while using also some roads here in red in order to provide a more flexible service and to feed here houses that are here. And here points are the stations that are considered. So we have also two speeds. So a speed here in the green, two different speeds. A speed in the green links which are dedicated, and different speed here in red links which are shared with private cars. Here we have some simulation parameters in terms of fixed costs, which are given from the literature. For the ticket price, it is optimized for DRT and given from literature for the specific Paris case. Subsidized, as I said, are lower than subsidized of bus, and revenues are then optimized since the fare is optimized. The emissions are also given from literature. The passengers volume is optimized, and penalties are also given from literature for a taxi service here. So they are not calibrated for the specific territory. So let's see the results. So as I said, we have 4 problems which are maximized. And for each maximization, we calculate the benefits for the society here. It is the total surplus, social welfare, for the users, for the operator, and for the environment. And we determine also the total demand and the average generated cost and the optimal operating conditions in terms of fleet size, fare, and vehicle capacity. And what we see here is that for the operator profit maximization, we have positive profit, but it is not really good in terms of social welfare. And we see that the operator would aim to minimize the number of vehicles for this territory and maximize the fare compared to other optimization. For the environment, we have also bad social welfare and also not high quality of service that is provided. For user surplus, we have really good user surplus here, but it is based on really a high number of vehicles, lower fares, which is really bad for the operator, and in turn it is bad for the society. And for the social welfare, I have a constraint to have a positive operator profit. The social welfare is not more than 0, but it is not bad. And we have a number of vehicles of about 20 vehicles and a little less than €1 in terms of fare. And here, in terms of capacity, we are more inclined to use here shuttles and mid-sized vehicles, while the operator would use smaller vehicles. We also investigate the results using 2D heat maps with considering fare and number of vehicles. And we see here the pink line is for the bus, and we see that for higher number of vehicles and lower fares is good for passengers, and it's bad for the operator. We see that for the environmental benefits, we don't see high impacts on the in general. And for the total benefits, we see that we could have several optimums here, depending on the trade-off between operator and passenger profits. Yes, 1 to 2 minutes. Finally, we perform a sensitivity analysis with respect to fixed cost and demand volume, and here we do it for the total profit, so the social welfare for both. And what we see is that beyond a threshold here of 0. So here the reference situation is 1, which is multiplied by 1.1, 1.2 or 0.8, and what we see is that for lower fixed costs, we have a positive social welfare. Also here, with respect to demand, we see that beyond a demand 0.95, it is better to use the CPT line, and otherwise we can use the DRT, which could be interesting from the social welfare perspective. So to conclude, we use an agent-based model and an economic model, which are coupled, and we assess the economic impacts. For the application case on Paris, we showed that replacing the CPT with DRT is not relevant from the society perspective. For the given demand and fixed costs. We see also that using shuttles is better for the society, and using small cars is better for private cars. We see that several social optimums could exist based on the 2D heat maps, and that some thresholds exist for demand and fixed costs, and for future works on some limits. So you consider that the demand is elastic, which is a strong assumption in this model. What should be done is a discrete choice model. So we conducted we did a survey in the territory, but it's not integrated in the model yet. And also the demand data is annual demand data from the previous survey, and the cost production is not of the real operator in the territory, but it's mean costs. Okay, so that's it. If you have any questions, please welcome. Thank you.
Yeah, thank you, Jaffa, for sharing your DRT optimization results with us. I'd rather take questions from the floor, but in the meanwhile, while people might be composing the questions, I just ask one. Do you think that people would see conversion from a fixed-route bus line to a demand-responsive transit to a DRT as elevation of service by transit services, or is it sort of seen by the public as a decline in service to the public? Because we normally would see that we would think that if there's more demand, we move from a DRT to a fixed route line, and then from a bus line to a rail line. But converting the other way around this might be seen by the public as a decline in service.
Yes, indeed, that's what we found, is that for higher demands, indeed, it is better to go to this bus line finally. So we had also this question. I think if I understood your question, I had the same question before. And finally, what we found is that for higher demands, it's for this, at least for this case study, it's a really specific case study with one point of injection of demands, which is the train station going to the scientific cluster. So it is really specific, and we cannot generalize the results directly. But for this specific case, what we see is that also for peak hours or for high demands, it's better to keep the bus line. But if you have lower demands, it could be interesting and more profitable, and also more attractive to use the DRT.
Right. Possibly one last question from Murthy. He's curious to know how did you differentiate between user surplus and social welfare?
Okay, in social welfare is what I I define as the total surplus. So I consider that it is user plus operator surplus and not just user surplus.
I see. Okay, thank you very much. I think in the interest of time, we should move forward to the third presenter, and I'll hand over to Ali for introducing the next presenter. Thank you very much, Jafar.
Thank you.
Thank you. Thank you, Jafar, for your nice presentation. So, yeah. Our next presenter is Xinyi Wang. She will present on variation in ride-hailing trips in Chengdu, China. She's a PhD candidate and graduate fellow in planning and public policy at Krueger University and adjunct instructor at the Department of Geography of University of South Carolina. His research focuses on the effect of new transportation technologies on society, human behavior, and urban forms. He is currently finishing his doctoral dissertation titled Travel Behavior of Ride Sourcing, a Data-Driven Analysis, which investigates several crucial aspects of travel behavior of those who use the emerging ride sourcing or ride-hailing services. Xinyi, the floor is yours.
Okay. Hello, everyone. Welcome to my presentation titled Variation in Ride-Hailing Trips in Chengdu, China. This is a part of my dissertation research, which I worked with my advisor, Dr. Robert Nunes. And the background of this study, actually, Ali already described very well at the beginning of the session. We have already observed the booming of ride-hailing services offered by transportation network companies. And we have seen the competition and the increase of the users and providers and the drivers as well in for-hire vehicle industry. And also, as Jafar just presented, why this is very important. My research is because we are wondering where and when people need such services. There is a gap between the supply and the demand. So we did this research to explore visual and spatial and temporal variation in travel demand of using ride-hailing services. The challenge here is we have limited data for ride-hailing, especially the detailed trip level data, because those big companies like Uber and Lyft and Didi in China, they are very reluctant to release the very detailed data. There are some exemptions, like ride Austin data in Austin, Texas, and also Chicago. Last year, Chicago released the data. It's trip level, but it's somehow also aggregated at the for the spatial and temporal variables. So there is the similar study using the Ride Austin data to look at the travel demand of using ride-hailing services. Yu and Peng used the data to look at the association between travel demand and the built environment and socioeconomic status at the census tract level in Austin, Texas. And they found most built environment and socioeconomic variables are statistically significant at the global level. And they also found the spatial non-stationarity or spatial heterogeneity in these the effect of those variables. So we are wondering if those. So first of all, we are wondering if the travel demand, the association between the travel demand and the built environment are similar in other areas. And also, Austin is one of the small non-profit companies in local Austin, but we are wondering if other more dominating companies like Didi also have the similar patterns and association with the environment. So we using the 30-day ride trajectory data from November 1st to November 30th in 2016 for Didi Chuxing trips in Chengdu, China. So the data includes variables of a driver ID, so we can identify the individual drivers, and order ID, we can identify the orders, and we can identify the very detailed, precise location with the longitudes and the latitudes of the pickup and drop-off points, and we also can find the time steps of the pickup and drop-offs. So the total numbers of trips in that month is more than 7 million, and the average number of trips per day is over 235,000. And average numbers of active drivers per day is almost 40,000. Average duration of the trips is about 21 minutes. So the objective of my study, as I mentioned previously, is to investigate the spatial temporal characteristics of ride-hailing and explore the association, associate the variation in ride-hailing trips generated with the built environment, and we also explore why this effect of built environment, different variables varied spatially using the generated in the GWR, geographic weighted regression models. So there is an overall picture of the trips between on the weekdays and weekends. So previously we know very well the traditional transportation mode has very different patterns on weekdays and weekends. Typically, they are 2 peak hours on weekdays and no peak hours in weekends. But we can see the patterns for ride-hailing services are for weekdays and weekends are very similar actually. Although the curve for weekends are a little bit more smooth, but basically they are very similar. So this study we focus on the weekdays, and we focus on 3 times of the period of the weekdays. One is morning peak, another is evening peak, and as the late night time as well. So the late night time, especially, we defined is the time that the subway, most subway and transit services stop running in Chengdu, China. And we also look at the patterns for different days. And we, interestingly, we found that the Fridays have very high demand and have very high number of trips compared with other weekdays. So in this study, we exclude Fridays in the weekday trips. And the study area, we confine well study area within the 3rd ring road of Chengdu, China, and the and we divided the area into 5,000, more than 5,000 grid cells. Each cell is 200 meters by 200 meters. And we also collected various data variables from various data resources because there are limited administrative data can be found in Chinese cities. So we use the European Commission estimate human population data and also scrape some data from the internet. So for example, the housing prices and the subway and railway stations, and also point of interest or POIs. We specifically focus on the recreational POIs like sports, entertainment, and restaurants. So because evidence and the literature suggests that those ride-hailing chips are highly correlated with those recreational purposes. And we also collected land use, road network, and floor area ratio variables. And this is the spatial patterns for pickups and drop-offs on different time of the day. We can see the during the morning peak hours, the pickups are more concentrated in the center, and in the evening peaks, the pattern is opposite. They are more concentrated for the pickups. And we can also see there is more concentrated for the pickups during the late night hours. So for the models, we use both the global chip generation model and the local chip generation model. So the global model is OLS model using the number of log number of chips as the dependent variable. And local chip model, the chip generation model, we use geographically weighted regression model, also called GWR. Those model assuming that the observations are influenced by the nearby, spatially nearby observations, and giving the observations a bandwidth for identify the effect of the nearby observations. So that's model. The local model will generate the varying local coefficient. So that means the coefficients are varying for different area, and that's the results for the local for the global chip generation model. We can see most built environment variables are statistically significant for most of the time. And for example, the population density, local road density, FAR, housing prices, subway entrance, and other intercity transportation hubs, and also the POI, the recreational destinations, except the land use mix. So we found that consistent for different time of day, the land use mix is not significantly associated with both the pickup and the drop-offs. But the local chip generation model provide more information about the effect of different variables. For example, we used the variable of population density as an example. This is how the local coefficient varied across the space and the time of day. We can see the blue color represent negative coefficients, and the red the orange and the red colors represent the positive coefficient. So we can see some areas have the negative coefficient and some others have the positive coefficient. But for most of the time, it has the positive association between the population density and the chip demand. So we are wondering why these variables or why these effects are varying across the space. So and that's the GWR model cannot tell us itself. So we explore it by using another regression, using the using the OLS regression, using the local coefficient of population density as the dependent variable, and and using the same set of the built environment variables as a dependent variable to see why these just explore why these local coefficients varying across the space. So we found, interestingly, the three variables are significantly positive, negatively significant associated with the local coefficient of the population density. They are local low density, subway entrance density, subway entrance, and the land-use mix. So that means, for example, if the area has high has the high local low density, that the impact or the importance of the population density will be reduced. Same as the subway entrance, the effect of the subway entrance and the land-use mix. And we also found the number of sports and entertainment facilities has the positive effect on the local coefficient of population density. That means if an area has a high number of high number of sports and entertainment facilities, that's increase the effect of the coefficient of the population density on the travel demand of using ride-hailing. So the key findings of this study is most built environment factors have positive associations globally, but the proximity to the transportation hub is also positively associated with the ride-hailing trips. Recreational destinations have a greater impact on drop-offs during the evening and late night. And many factors affect the spatial variation of local coefficient. Because we use the log model, so the local coefficient is also can be interpreted as the elasticities of the GWR models. The limitation here is that there are potential errors caused by the estimate to variables like the population density, because we couldn't find the administrative data for Chinese cities. And also the population, the potential errors caused by the grid boundaries, because we are arbitrarily defined the grid, the boundary grid, so it might cause some errors. And also the limited study area. So we only study the trip generation models in the central area of Chengdu, China. So future works, we maybe compared some the trip generation models between cities in China and US, also other countries as well, and also use travel behavior series to explain more ride-hailing behaviors, and also provide policy implications for ride-hailing regulations and development, especially for these times all the post COVID pandemic era, period, we need more implications and suggestions about how to regulate the or manage the ride-hailing services. So that's my presentation. I'm welcoming questions, and we also attached the tables for the statistics, both the descriptive statistics and the models, after the slides, in the end of the slides. So if you are interested, you can find it in the slides. And if you have more detailed questions, welcome to contact me in the through email. So that's my presentation. Thank you.
Nice, Chng. Thank you. It was a very nice presentation. So let's get to the questions. Mahmoud asked, what is the justification of a negative coefficient of population in trip generation?
Hold on a second. Oh, could you say again?
Yeah, of course. What is the justification of a negative coefficient for population in trip generation model?
So,
I guess yeah.
So like we don't really know what's the justification. We explore, so that's why we use the we do the further exploration about using the regression to regress the local coefficient to see why there is a negative coefficient or a positive coefficient. So we found that some variables, for example, let me show that. So it's like, for example, there are some variables can reduce the coefficient, the value of local coefficient of population density. So that's a local road density, subway entrance, and land use mix. And there is also another variable increase population positively associated with the local coefficient. So we interpret that if there is, for example, using the local road density as an example, if there is a high local road density, and so the local coefficient of population density on travel demand may be reduced by because of the road density. So we don't know the mechanism, but that's why we did the exploration to see why. I think that's the limit. We think that's the limitation of the GWR model, because the GWR model can present the spatial patterns, but not good at interpreting why it is like that spatial pattern. So we did that regression model to try to understand that.
I think that's also the subject of the next question. Luis asked that with WGR, there is a possible concern with overfitting. So did you explore hoarding out a subset for model validation to see if WDR is actually more predictive than a standard spatial error model?
No, we didn't do the validation, but we could, if there is other data set or sample, we can do the validation to see how fit the or how good at predicting the chip generation data, chip generation model. And we can also use so that's actually what I'm doing now. We are using the machine learning approaches to kind of kind of fix the overfitting issues. But we didn't do validation for this model.
Okay, so I think that's a nice recommendation, because even with other machine learning algorithms, sometimes the problem with overfitting exists. So if you can you can divide your data to some training subsets, validation subsets, and then you can train your model based on like 80% of the data and test your model based on the rest unseen 20% of the data. That would validate your model and add to your research.
Mm-hmm.
So I may have one other question. Could you go to your previous slide? Here. I can see now this one, the global trip generation model. So we can see that the subway entrance for morning peak for the pickup is insignificant. Could you somehow justify that? Why is that insignificant? Because I expect a significant for this variable, at least, because it's a subway entrance, isn't it? And in the morning peak hour. So.
Well, I don't know, but that's somehow is related to the. I think that's there's not so. So it's basically in central Chengdu. It's kind of the residential area. It's dispersed everywhere. So maybe people just there are many areas people not using the subway at all. So maybe that's the reason, but I don't know actually.
Yeah. So maybe that if you look, I really recommend that you get back into your data. Mm-hmm. Sometimes that when you discretize your data into morning peak, evening peak, and late night, this may unbalance your data. So maybe for morning peak hours, you don't have data for pickup at the subway entrance. That makes your model insignificant for that period of time. So playing around with those time intervals can make this variable significant sometimes. But that's good if you can look at your data.
Okay. Thanks.
Thank you very much. So if there is no other questions, we can move forward to the next presenter.
Mm-hmm.
Our lucky last today will be Dr. Liu. Yiyang Liu is an associate professor in the School of Sustainable Engineering and Built Environment, Arizona State University. She holds a BSc and BA Economics, I guess, degree from Beijing University, and received her master's and doctoral degrees in civil and coastal engineering from the University of Florida. Liu's primary area of expertise include intelligent transportation systems and transportation systems modeling and optimization. So she's with us today with a paper on planned special events network optimization model considering parking and ride-sharing drop-off. So without further ado, I pass over to Yiyang. So if you're ready, you can start.
Hello, everybody. Welcome to this session and welcome to my presentation. Thank you for staying till the end. My name is Yiyang Liu, Associate Professor at the Arizona State University. I'd like to begin by saying thank you to the event organizers and volunteers for providing this excellent platform, and that I am thrilled to connect with everybody virtually. So the topic of my presentation today is in fact, a network optimization model for a planned special event considering parking and ride-sharing drop-off locations. As the title has suggested, ride-sharing drop-off, ride-sharing is a component of this work, but the main topic is actually planned special event network design, network optimization. So it might be a slight shift of gear because this session is about shared mobility. This work was a collaboration with my former student, Xinyi, who recently graduated and is now a research scientist at Amazon. So what is a planned special event? I think we all know what planned special events are. We've all been there, a concert, a sports game. And this figure that you're seeing here is from Super Bowl 49, which was held in the city of Glendale in Arizona in 2015, and is one of our case studies. So that's going to be very interesting. Now with special event, of course, the transportation network is different. It's always different. There's going to be lane reversals, lane closure. Even though you know the area, the special events network is always different. Another challenge in planned special event is, of course, finding parking. It is such a headache. If you've been to a special event, you know how long it takes. Even with small special events like ASU football games, and even that I have done my homework before going there, you know, knowing where I should park, which routes I could take, it usually takes at least half an hour between the time that I arrived on campus and when I finally found parking. So that's a challenge. In practice, one of the tools that traffic engineers use to manage the unfamiliar network and the searching for parking issue is to provide route guidance. This may not be anything fancy. For example, especially for recurring special events, for example, a seasonal football game, a seasonal sports game, then the routes, the lane closure, the lane reversals could be more or less the same from game to game, and that routes guidance information could be published on the event website, or even given to event goers at the back of their event ticket. So route guidance is commonly used in practice. Sometimes there are also dynamic message signs deployed physically onto the network, displaying messages, advisory messages for event goers. Another feature of planned special event traffic is ride sharing. It's becoming, of course, more and more common and more popular option for event goers, because who wants to deal with the traffic and the parking, right? This is actually from Uber's website. Uber has been partnering with the city of Glendale and also Arizona Cardinals team to provide ride sharing for the games. And in 2016, Uber had one drop-off location designated, and in 2019, more recently, now they have two. So in this work, we'd like to, because traffic planning for special event is so challenging, so we'd like to provide a systematic framework for planned special event. So it will be a planning problem where we would consider lane reversal, lane closure, route guidance, and ride sharing drop-off locations as the decision variables. And of course, being a special event traffic planning problem, we have to consider the unique traffic issues in that scenario, which include parking search, compliance rates. You provide route guidance to the event goers, they may not actually follow it, right? And also congestion around drop-off locations caused by, for example, lane changing and of course pedestrian traffic. So this is how we do it. We established a model, and it's pretty standard modeling framework where the planning decisions, given a combination of the lane reversal, route guidance, and ride sharing drop-off locations, we have a traffic dynamics model running that incorporates the parking search, the compliance rate, and the routes and the congestion around drop-off locations. So the traffic dynamics model is able to estimate the overall traffic condition, including traffic flow and travel time, given a combination of the lane reversal, route guidance, and ride sharing drop-off locations. So this process then goes iteratively until we find a satisfactory solution. Of course, OD information and the ride sharing demand are necessary inputs to the traffic dynamics model. One thing that I would like to highlight in our modeling framework is how we converted the physical network into a node link representation. We actually divide a physical link between two intersections into three segments. There is a mid-block section and the approaches to the intersections or the ends of each physical link. The two ends of each physical link are treated separately. The reason that we use this model is so that there's more flexibility in terms of network design, in terms of the lane reversal, lane configurations. And by doing so, we are also able to model some special treatments of the intersection, for example, channelized turns or lane or median of the mid-block so that lane reversal is not possible, or just the number of lanes is different from the mid-block to the transition area, to the approach to intersections. So how do we solve the problem? Well, the problem is not easy to solve because with the route guidance, with the ride sharing drop-off locations, with the lane reversal, the decision variable space is large to explore. And the traffic dynamics itself is complex. So for problems like that, meta-heuristics are commonly used. And one of the standard meta-heuristic or common meta-heuristic algorithms is genetic algorithm. So we started by looking at using genetic algorithm to come up with a satisfactory solution. But we found it doesn't work very well, even with customization. The reason is because, again, the decision space is large to explore and the traffic dynamics is complex. But as we were exploring it, we found that comparing, the three decision variable sets, comparing to route guidance and ride sharing drop-off locations, lane reversal has a much smaller space to explore. And it is, in fact, easier to figure out the lane configuration if we hold route guidance and ride sharing drop-off locations constant. So if we don't change it, the reason is because if those don't change, it is in fact possible to estimate how the overall traffic would be affected if we change the lane configuration a little bit. Whereas route guidance and ride sharing, because of the complex traffic dynamics, it is not immediately obvious how the overall traffic will be affected if we change the route guidance and the ride sharing a little bit. So with that, we now separate the three decision variable sets into two subspaces. And we introduced a secondary optimization model. We call it congestion relief to explore that lane reversal space. It is in fact a knapsack problem with estimated shadow cost, so how the overall traffic condition will change if we change the lane reversal a little bit. Now this figure at the lower right corner of the screen it's showing one iteration of our GA plus CR algorithm. So all these columns, each of these columns represent a fixed combination of route guidance and ride sharing drop-off locations. And then CR would go on to optimize the lane configuration until we find the best lane configuration that will support that fixed route guidance and ride sharing drop-off locations. And then the GA will choose among these possible solutions which ones to keep for the next iteration. So with that, here's the case study results. And this is the Super Bowl 49 network. As you can see that this is our study area and the stadium is right here in the middle. Around the stadium, there are 5 parking lots, and these are our 5 destinations. The origins of this study area are the major roads, arterials, and freeway entrances to this area. So we have 6 origins and 5 destinations. We estimated the OD from actual traffic data from the Super Bowl 49. We had to assume that ride-sharing demand is 10% because we don't have data for that. We considered 3 paths for each OD pair as candidates for route guidance decisions, and 7 candidate locations for ride sharing. So here are the results. For customized GA, for general GA with a little bit of customization, it doesn't really improve the overall traffic that much. The numbers that you are seeing here are in vehicle hours for the ingress. The baseline, so if you don't do anything, no lane configuration, no ride sharing designated drop-off locations and such, then the baseline ingress overall vehicle hours is about 167. So with the GA alone, it doesn't really improve the overall traffic condition that much. But with GA plus CR, in the first iteration, it was able to reduce the overall congestion down to 110 vehicle hours. And after 5 iterations, it is 101. And comparing to the original baseline, which is about 167, this is a 34% reduction. We also noticed some interesting, we had some interesting observations here, comparing the results from our model to the actual traffic management plan implemented. I do want to clarify here that the actual traffic management plan implemented that we use here for the comparison is from a regular seasonal Cardinal football game. It's not from Super Bowl 49 because we were not able to access that data. So the comparison shows that for a regular seasonal game, the Uber drop-off location is on this east-west cardinal way, whereas our model will place the drop-off location on this north-south 95th Street. Another observation here is that at the lower right corner of the study area, this intersection is considered so far away from the actual event location that in practice, in implementation, no special treatment was given to this intersection. Whereas in our model, the model recommends all westbound traffic to be pushed north. The reason is so that the pressure on the freeway and therefore the pressure on the off-ramps leading to this event location will be reduced. Another observation is for this intersection right here, right next to the actual stadium. And this is definitely a key intersection. And our model recommends all the eastbound traffic to go either north or south. This is consistent with the actual traffic management plan. But in the actual traffic management plan, this road is actually closed completely, except for buses. Whereas in our model, the results recommend the northbound traffic to go, to turn right and go on this Maryland Avenue. The reason is likely because we did not consider pedestrian traffic in our model, because right here in this gray area, that is a major entertainment center, restaurants and such. And event goers are likely going to go between these two locations on foot. And this is obviously a drawback of our model, that we don't have the pedestrians modeled explicitly. And that will definitely be a future research direction that we'll be looking into. But that being said, to summarize, this work explicitly modeled parking, ride-sharing, and lane closure in the special events traffic management problem, and provided a comprehensive traffic management plan by through this modeling and the solution algorithm. So that is all for my presentation. Thank you again for listening and joining the session live. And here's my contact information. If you have any questions or would like to bounce ideas off, I'll be more than happy to connect with you. And with that, I'm happy to answer any questions now.
Yeah, thank you, Yiyang, for this energetic presentation. Depending on where you are around the world, it could be really like in the middle of the midnight or really early morning. I guess in Arizona it's like middle of the day. So
yeah, it's 1 o'clock.
Good. I have a couple questions. Can you compare your baseline in terms of those objective function values? Where does it stand?
So baseline was about the same as in the first iteration from the genetic algorithm. Baseline was 167 vehicle hours, about that much. And at the end, we were able to improve that to 101.
Right. So the baseline was the actual traffic plan, which was the experimental one.
The baseline was do nothing.
Oh, I see. So how about the actual traffic diversion plan?
So the actual traffic plan, that's a good question. We actually didn't test it because the plan was not exactly, well, the data that we were able to access was not completely, was not complete, that we don't have a full picture of what's going on in the overall study area. But I feel confident saying that the actual plan implemented will definitely be better than the do nothing, but may not in our model may not be as good as the final solution that we are able to arrive. But then again, we don't have pedestrian traffic modeled in there, which is a I would definitely agree that this is a major issue with the model. Again, because we don't really have data for pedestrian traffic.
Right. There's a question from Murphy. He's asking about whether or not you considered right source and stop location, which I believe you did. But if you want to comment further on that, I'm reading the question off the chat.
Thank you. So for this work, what we consider is the ingress, so going into the event, where the ride sourcing pickup location would be, we consider outside of this area. So like you're from other parts of the city, you're going into this event area. So we only considered drop-off locations. And for drop-off, in practice, that is what the city of Glendale and the Cardinals team have come up with Uber and other ride sharing. There will be designated areas for drop-off. So that's what we have considered.
Yeah. I might have missed that about the travel guidance. How does it affect your model? How is it seen in the equation?
So the traffic guidance is we would provide a route that is recommended for travelers, and that will be in the model we consider that will be given to the travelers in advance, but only a portion of the travelers will follow this recommended route. So that's how it's going to affect traffic.
Yeah, what's the compliance rate?
You can vary that. We did a sensitivity analysis on that as well.
Yeah. Was it supported by experimental observations?
The compliance rate?
Yeah.
No. So that's why we don't know what the empirical compliance rate is. So that's why we varied the compliance rate in our numerical experiments.
I have a question from Yiyang. Could you please elaborate a little bit about the differences in the city customizations in applying the model to different events?
So to customize, of course, the network needs to be customized, the demand, and so local knowledge about which routes are possible candidates for recommendation, and or those could be the routes that traffic planners think are good in terms of reducing congestion, or it could be familiar routes to the general population in the area. So there are different reasons there, right? And another thing is, and of course you have to work with the vendors, because sometimes vendors would like traffic to go through their location so they get business. So there are a lot of local knowledge that needs to go in that the model just couldn't handle as a generic set of inputs. So these all need to be customized. Another thing, of course, is the empirical compliance rate. So how much of the traffic, what's the percentage of event goers we estimate will follow the recommended route.
Yeah. Interesting. Thank you. One more. Yeah. So before I ask that question, no, I thought there was a new question coming. And did you think about the changing the signal timings as well? Because I could see that you have intersections there.
Right. So yes, it definitely could be considered in there. We did consider signal timing, but it was a pretty simple fixed timing solution there for this particular traffic arrival rates.
Yeah. It's so many areas of improvement. I'm sure you're lining up the next student, the next proposal on this topic. So,
it is very interesting and of practical significance.
Yes, indeed. Yeah. Okay, great. Thank you very much. I don't see any further questions from the audience, and with that, I think we can give a couple of minutes for the preparations for the next session. As you know, we don't have any breaks between the sessions. So thank you very much, Yiyang. I also would like to thank other presenters for today. We had Chng, we had Jafar, and we had Philippe. Ali, the floor is yours. I want to thank everyone and wish you the best for the rest of the day, and would like to see you in future events like this.
Yeah, I would like to thank everyone as well.
Yep. So good morning. Well, good afternoon. It's morning here. I'm in Sydney, Australia, where it's 6 a.m. and freezing cold outside because we're in the middle of winter. But good morning, good afternoon, and welcome to this final session in track 5 of the Bridging Transportation Research Conference 2. My name is Dr. Jennifer Kent. I'm from the University of Sydney. To begin with, I'd like to acknowledge that although collectively we're scattered across the world right now, I'm meeting you today in Australia and I'm on Aboriginal lands. I live and work on the traditional lands of the Wang clan, one of the 29 tribes of the Eora Nation, and I want to acknowledge the traditional custodians of these lands, to acknowledge elders past, present and emerging, and to acknowledge country itself. I also want to acknowledge that the lands that I convene on today are unceded lands, and to acknowledge the continued injustices that are experienced in Aboriginal and Torres Strait Islander communities in Australia today. So today we're discussing transport safety, and we have 3 presentations, all looking at ways to measure both the extent and the impact of transport-related collisions, as well as ways to make the way that we travel safer. For me, these presentations are of particular interest. My research has its focus on why people continue to be so attached to private car use in cities around the globe. And when we dig quite deep into the barriers against the use of modes like walking and cycling for travel, concerns for safety are often very much at the heart of people's resistance. My research looks specifically at the way that families travel, and again, safety is a key concern when it comes to considerations of how we allow and facilitate children to navigate their worlds, both with mum and dad and as independent little humans. On that note, I just want to cover a few housekeeping things. If we can still say that we're housekeeping collectively, even though we're all online. Each presenter today has 20 minutes to present and 10 minutes for questions, and they're under strict order from me to stick to time. If you have a question, please type it in the chat session, and my colleague Milad will facilitate the question and answer session at the end of each particular presentation. At the end of each session, I'll then introduce the new presenter, and so it goes. Okay, so now that that's out of the way, I'm going to start by introducing Martina Fazio, who will be presenting our first paper. Now, Martina is a first-year PhD student, welcome Martina, in complex systems for physical, socio-economic and life sciences at the University of Catania. Her research focuses on the integration of discrete choice models with agent-based analysis for the simulation of urban freight scenarios, big data and GIS-based analysis. These techniques are applied in order to analyse current transport scenarios and to understand how we can better promote the ideals of sustainable mobility. So I'll hand it over to you, Martina.
Okay, can you hear me?
Yes.
Okay, let me share the screen. Okay, so good afternoon. Thanks for the presentation. My name is Martina Fazio. I'm a water and transportation civil engineer and a PhD student in the Department of Physics and Astronomy at Torre Mariana of the University of Catania. The main topic of my research project is the application of big data in transportation field, and the study that I'm going to present concerns the combined use of GPS tracks and accident data in order to improve safety of cycle paths. The model imbalance in favor of private vehicles leads to negative consequences such as road congestion, pollution, social exclusion, and low user safety perception. Sustainable mobility can be a valid solution as it is able to decrease the environmental, social, and economic impacts generated by private vehicles by providing alternative modes of transport. In particular, in this study, we will focus on cycling mobility as an active form of mobility that allows people to perform physical activity, move efficiently with minimal effort, and avoiding the externalities associated with transport. So, in order to encourage cycling, it is necessary not only to provide adequate and dedicated infrastructures, but also to intervene on the control of other road users. For example, by introducing measures to reduce traffic volumes and speed. So, with the aim of favoring cycling usage, it is necessary to focus attention on these characteristics in order to create adequate and safe cycle facilities. In recent years, the rapid development of new information and communication technologies, for example, GPS and smartphones, and wider access to open data has made possible the exploitation of a large amount of data called big data. The acquisition of big data takes place from different sources. Among these, GPS devices are the most common. The field of application of GPS data in transport engineering are disparate. Travel mode detection, activity recognition, driver's behavior analysis, road safety analysis, and so on. So now we come to the aim of the presentation, that is to provide a methodology to calculate the bike safety index for the assessment of cycling safety of roads in urban areas. The calculation of the index includes GPS tracks, accident localization recorded by official sources, and other information provided from GIS tools. We propose a combined GPS and GIS methodology that is able to fix some of the gaps of an analysis based only on one of these two aspects. In fact, if on the one hand the use of GPS data can lead to an improvement in the reliability of the only GIS-based analysis, on the other hand, this type of data need processing tools capable of making the information provided more intelligible. The methodology was applied in Catania, a medium-sized city located in southern Italy. We believe that this methodology can help decision makers and planners not only to carry out a safety analysis, but also to identify the main weaknesses of an urban road network and maybe understand how to intervene with the aim of guaranteeing safer and more reliable routes for cyclists. The methodology proposed for the evaluation of the bike safety index is based on the following 4 steps. The first one consists in the extraction of road network data from OpenStreetMap services. This was done through the QGIS plugin named QuickOSM, which allows to download special OpenStreetMap data. Follow GPS route retrievals through the JOSM application and the travel mode recognition. The third steps regards the evaluation of partial indices through a spatial analysis thanks to the use of QGIS software that allows to assign to each arches of road network the presence of GPS tracks, accident and speed data, and existence of cycle infrastructures. Finally, a scenario analysis was performed by varying some input data to understand the factors that most influence road safety. The study was applied in Catania, a city with about 300,000 inhabitants located in Sicily in the south of Italy. The study area highlighted by the purple area consists of the urban area of Catania. Therefore, those zones located in the south of the city, which are mostly the site of logistical and industrial buildings, have been excluded. Catania suffers from many mobility problems, mainly related to the high usage of private vehicles. This can be ascribed to lack and poor quality of infrastructures for active mobility. As far as cycling mobility is concerned, the city of Catania has always had the low national performance indicator, often attributed to the presence of slopes in the city and therefore to low attractiveness of the routes for bicycle users. Actually, one of the main causes of the scarce diffusion of the bicycle in Catania is due to the absence of an adequate cycle infrastructure. As can be seen from the rightmost figure, the current cycle network of Catania is a set of disconnected paths. Hence, the need to evaluate the safety of current cycle routes and to evaluate how the introduction of new infrastructures and measures can improve the overall safety of cycling mobility. Let's get into the methodology by talking about GPS route retrieval. A user-friendly way to obtain GPS tracks of a specific area is through the use of Java OpenStreetMap Editor software, which is a desktop application with downloading and advanced editing features of OpenStreetMap data. GPS tracks can be easily downloaded through a processing tool that allows to download the data from OSM in GPS format. This data can be uploaded in QGIS projects and transformed into shape files for editing and spatial analysis. 2 types of files can be downloaded, linear and point. In the first one, there are information regarding the name and the description assigned by users. In the latter, the information is more specific. Oh, sorry. It contains the device identification number, the progressive number, latitude and longitude in WGS84, and the timestamp. A travel mode recognition was performed in order to detect the used travel mode and to filter the traces related to cycling use. In the GPS data obtained, users could enter information regarding the used mode. But unfortunately, in most cases, this information is unreliable or missing. Therefore, it is necessary to recognize the used travel mode. So, knowing the GPS coordinates of latitude and longitude, the timestamp, the identifier number, it is possible to calculate the distance and the time lapse between two successive points. These operations were carried out with accurate precision thanks to a sampling frequency of 0.2 Hz, that is, the data are collected every 5 seconds. Subsequently, it was calculated the average speeds using the equations shown in the slide. After calculating the speeds, it was possible to categorize the GPS points according to the most probable mode of transport referred to each track collected. The threshold were selected based on Italian website and research studies that rely on transport mode detection. Since the study is aimed at a safety analysis of cycling mobility, it was decided to take into consideration only the GPS tracks in which the calculated speeds vary from 12 to 20 km/h, hence the most likely speeds that can be referred to the use of cycling. The figures show the JOSM application interface. In particular, it can be seen the data collection area and the downloadable tracks of the network. From JOSM application, 244 GPS traces and 181,113 GPS points have been downloaded. A first data cleaning has been performed in order to exclude incomplete information, reducing the total number of data. Moreover, the travel mode recognition previously presented allowed to select 4,726 points to be used for the analysis. That is, those related to a speed ranging from 12 to 20 km/h. Now, let's analyze in detail how the partial indices were evaluated. The first one that we talk about is the GPS index. The index has been evaluated by taking into account the proximity of GPS tracks point to each arc A of the road network. In particular, the index was calculated by counting the number of GPS tracks points that fall within a buffer of radius with a radius of 100 meters of the arc considered. This number was subsequently normalized, and the GPS index was calculated according to this equation. Accident data have been downloaded through the open data section of the Catania municipality for the year 2017. The information provided for each accident include identification number, date, location, and number of users involved. The latter are distinguished in fatality, reserved prognosis, injuries, and unscathed. The accident data were easily geolocated through the geocode command of the MMQGIS plugin, which always refers to OSM service. Also, in this case, were considered the number of accidents that falling within a buffer of 100 meters from each arc of the road network. The index was calculated according to the equation, by assigning a different weight labeled with the letter W in function of the type of accident. Regarding the speed index, it were used data from OSM service. In fact, the OSM road network provides a classification of roads into 14 categories. In addition, the database gives the max speed attribute for each road. Where this information was not present, the speed limits on those roads have been implemented. The figure shows the speed assigned for each arc. Then the speed index has been evaluated by taking into account the normalized values for maximum speed for each arc of the road network. Finally, the cycle facility index has been estimated by considering the presence of cycle infrastructures in each arc of the road network. It was assigned a different weight according to the type of facilities that are classified in segregate path, shared path, and no presence of cycle path. The BSI index for each arc will be given by a linear combination of the partial indices as shown in the equation. The beta are the weight for each index. As can be seen from the map, the higher the BSI value, the greater the risk associated with arc A. Purple arches are therefore the least risky, whereas the yellow ones are those with the most risks. Two different scenarios have been introduced beyond the current state. Scenario 1 involves the introduction of a cycle network that includes a planned path design for the Librino neighborhood, indicated in green, and the cycle path proposed by Giuffrida et al. In this scenario, the only index that varies is the cycle facility index due to the addition of new cycle paths. The variation was applied by taking into account the classification of cycle paths presented previously, but now based on the cycle tracks type proposed by Giuffrida et al. For scenario 2, it was decided to reduce the current speed values of the secondary and tertiary roads to 30 km/h. Hence, the changing index is the speed index. For each scenario, the new BSI values were recalculated according to this variation. The figures show the result of the calculation of BSI value for the three scenarios considered: current state, scenario 1, and scenario 2. In the three scenarios, the accident index and GPS index will keep with the same value, since they are based on information derived from historical database. So now, with the aim of identifying the best scenario among those proposed, two comparisons were made. The first one between the current state and scenario 1, and the second one between the current state and scenario 2. The arches were classified in terms of safety improvement according to the values shown in the table. As can be seen from the maps, but also from the graph, on the right, scenario 1 resulted in a greater improvement in the safety condition. This means that the presence of a broader cycle network contributes more to the improvement of safety conditions compared to the reduction of the speed of vehicles on the road. In conclusion, summarizing the main results, since cycling mobility safety is one of the factors that most influences user in their process choice of mode of transport, it is necessary addressing this issue. Furthermore, thanks to the rapid spread of new technologies that allows the crowdsourcing of data relating to user GPS traces, it is possible to conduct more reliable analysis in these fields. Hence, in this study, we propose a methodology that allows to calculate the bike safety index of roads for roads of urban area by involving GPS traces, accident localization, and GIS data. Through a scenario analysis that emerged how the presence of cycle networks strongly influences the safety level of roads. Lastly, the methodology proposed can be useful for decision makers to identify intervention priorities in order to improve the safety level of road for cycling mobility. Nevertheless, the study has limitations that suggest potential improvement for future research. For example, considering other type of data, such as traffic volume, as a factor that strongly influences the safety perception of cyclists. It is fair to point out that a proper travel model recognition would require the analysis of acceleration, as was done in the study of Shafiqo and Dato in 2016. Moreover, considering a large amount of data of cycling traces can be a limitation of the methodology, since it could lead, for instance, to have high BSI index with high GPS traces points and few accidents. Maybe this issue could be fixed by implementing proper weight to partial indices calibrated according to on-site surveys. So thank you all for your attention. If you have any question, I'm ready to answer it. And for any other information, please contact me via the email address here. Thanks again.
Thank you so much, Martina, for your presentation and the analysis of GPS and GIS for your big data. It's really interesting. We have one question from, let's say, Mr. Yiyang. Sorry if I missed it, but can you please explain the rationale behind the weights used for the different severity levels of crashes?
Oh, yes, this is an interesting question. For this study, the weights are, sorry, can I, screen? Okay.
Yeah, sure.
Yes. Okay, due to the fact that the greater BSI index, the higher is the risk associated to each arc, we assign a higher weight for the accident with fatality injuries, and so the lower weight for the accident less dangerous. For this reason, we implemented this weight.
Okay, thank you. And also, what is the source of GPS data, Mr. Langsman, we should say it?
Yes, the GPS data were downloaded through the Java OpenStreetMap data. Is always a QGIS plugin. Is provided from Quick OSM, from OpenStreetMap source. It is open source software, so anyone can download this data.
Okay, thank you so much. All the participants, do you have any questions? Okay, I have 2 or 3 questions. First of all, as I said, it's really great and interesting topics. I saw the weights that you use for the accidents, but would you please let us know the reference for those weights? It's, for example, kind of manual or not?
Sorry, can you repeat, please?
I want to know the reference that you use for the weights of the accidents. I mean, for example, fatality, you put 1 and etc.
Yes, the data were downloaded through open data site of Catania municipality, so we referred to this site.
Okay. Okay, thank you. And another question, you used for speeding, for GPS, for facility, used some index, and you use them for example, intervention to improve the safety. But, we have the reference that in that reference, for example, we have these index. But for your country and the case study that you use these index, is it necessary to use a kind of, for example, modification for these index? For example, let me clarify for you. For example, let's say for the case study that you used, the populations, are, for example, much older than the younger. So maybe, for example, we should modify those indexes. So do you consider this problem or this issue?
Yes, no, for this study, for the purpose of these studies, we decided to consider just this index. So I agree with you. This is technically a generalization. Maybe for future studies, we can implement this information for the calculation of the assigned index. Yes, I agree.
Yeah, it's really great for the future study. And also, I saw in your presentation that you tell us some scenario and improvement based on those scenario and based on BSI index. But those scenarios are related to, spatial pattern and, parameters. Can we use the time, for example, beside of the spatial temporal analysis for improvements? Maybe, for example, some accidents are occurring at the specific time of a day. For example, let's say for the improvement, we can use, for example, the speed limit that are that varying across, for example, in a kind of day, let's say. So do you consider this factor, time in your study?
No, we don't consider this information due to the fact that we based only on the information provided from the city, from the site where the data were downloaded. So certainly it can be implemented in the future research, but it's based only on the data. So we consider just the information.
Yeah, it's great. The source of your data, do the source of your data have a time in your data? For example, I saw that the accidents have a kind of date, but the facility and the improving of facility and changing of those, or let's say the speeding, do they have any days and time for each record?
Yes, we have the date, but the information are often missing or unreliable. So we decided to not consider this information.
Okay. Thank you so much. And I think it's really great to consider this issue in your future study. So I do not see any question according your let's say topic and presentation. Dr. Jennifer, I think we can go to the next presentation.
Okay, thank you very much, Milad, and thank you very much, Martina. Really interesting presentation. I really appreciate it. So our next presenter is Mohammad Reza Kulashani, and I apologize if I've not pronounced that correctly. He's a PhD candidate at Florida State University College of Engineering in the USA. Mohammad Reza is doing PhD on youth-involved crashes, investigating spatial temporal patterns using extensive statistical methods, and that's what will be discussed today. So with no further ado, I'll hand you over for the presentation. Thank you very much.
Hello, everyone. Sorry. Hello, everyone. My name is Mohammad Reza Kulashani, a PhD candidate in FAMU FSU College of Engineering, Florida, United States. Let me stop my video for. I hope you're all in good health and doing great during these unprecedented days. I really appreciate Dr. Kent and Dr. Delaware to coordinate this session and for giving me this opportunity to present this research to you on behalf of my supervisor, Dr. Eren Erman Özguven, and all the other authors who contribute on it. This research is about examining special patterns of youth-involved crashes around university campuses in Florida. My talk is divided into these parts. First, I'm going to present introduction, motivation, and problem definition. Then I will talk about the goals of the research. Then I will introduce you the methodology and its steps. Next, I will focus on free counties as a case study and provide you some conclusion to obtain, which obtained based on the results. Finally, I will suggest you some idea for future works. Let me provide you some information to justify why we are studying crashes. The increasing trend of urbanization and rapid population growth, which result in significant development in transportation. One of the adverse inevitable outcomes of transportation is crashes, which lead to injuries and loss of lives. And they have significant political, economic, and social consequences. Based on World Health Organization research, the estimated total cost of fatal and serious injury in the US in 2013 was more than $1,800 billion. But in this research, we focus on youth population because approximately 20% of new youth drivers are known to have a self-reported collision in their first 6 months of driving, and youth population aged 15 to 24 years were accounted for approximately 27% of driver fatalities across countries in 2004, while they represented only 10% of the overall population. Road crashes are the leading cause of death and injury among youth people under 25 in the United States, Canada, and European Union. Now let's examine this assumption that risk takers are crash makers. Youth drivers are more willing to take risks than other age groups, and they couldn't perceive dangerous situation, meaning that closely following the front car without considering its irrecoverable consequences. The greater risk among young drivers is mainly a function of tendency to take risks while driving. As such, this research intends to identify the youth-involved crash clusters around university campuses as locations where populated youth age from 16 to 22. Besides, we try to evaluate the geospatial differences between youth and other age groups involved crash based on the comparison of high-risk crash locations. To achieve these objectives, we will try to find appropriate responses for these questions. Our youth drivers behave differently than other drivers due to their more risky nature that I discussed before. We expect them to behave differently, and should we take special measures with a focus on youth driver? Which location has higher youth-involved crash? Is there any special correlation between youth-involved crash location and campus area with populated this age of group? This group age? Are there special differences for youth-involved crashes in this specific area, and how and who can benefit from this study? Because we know that all society would gain benefit from young age population and their potential. I'd like to illustrate the methodology in this slide. The first step is extracting crash data mainly from F.dot database. Next, we use ArcGIS to do a spatial analysis to find hotspots and the density map using SANET, spatial analysis along network. As third step, I would try to find an innovative method to visualize crash data to make comparison between different age groups to gain better understanding of used involved crash pattern. Next, I would conduct an extensive spatial analysis of used involved crash to identify hotspot area where there are a noticeable number of used involved crash comparing to other age groups. Finally, I provide you evaluation and interpretation of the results. In the first step, we extract crash data from F.dot database, ranged from 2011 to 2014. These comprehensive data have many attributes and properly prepared for GIS as shapefiles. F.dot gathered these data from official crash reports, so they are reliable enough for this purpose. Moreover, we used F.dot roadway network, also the location of colleges, universities, and professional schools obtained from U.S. Geological Survey. In order to investigate the geospatial pattern of used involved crash density, we employed kernel density estimation, which is widely used as a method to create density surfaces using spatially distributed point data. Here are some application of KDE, which stands for kernel density estimation in this presentation, in previous research. For example, in criminology disciplines, they utilize these methods to find hotspots with high rate of crime. In social sciences and medicine, to explore the relationship between cancer and nightlight exposure and to identify the density of high crash occurrence location. This method has been widely used in literature review. Literature. KD is a non-parametric way to estimate the probability density function of a random variable based on this formula. And it's worth to mention that kernel function could be uniform, normal, or triangle. Here, I want to introduce you one of the most challenging part when utilizing KD methods, which is choosing bandwidth value. As you can see here in this picture, higher value for bandwidths make the KD smoother, while the bandwidth value should be optimal. Based on literature review and similar research that utilized KD for airband network, a 200-meter bandwidth has been selected, and cell width value is equal to 1/10 of the bandwidth. So in this research, we use these two values as bandwidth and cell width for further analysis. There are two different methods for KD methods. Planar distance based, which considers the shortest distance between 2 points as a straight line, Euclidean distance I mean, and roadway network distance based, which conduct spatial analysis along network owing to the fact that crashes occur through roadway network. RND, which stands for roadway network distance, provides us more accurate results for crash density pattern comparing to the planar distance, which is calculated based on Euclidean distance. It's worth to mention that planar distance-based method results in overestimation or underestimation, meaning that low-risk roadways, low-risk segments, locations are shown to be very risky as overestimation, or high-risky roadway or high-risk roadways are not shown very explicitly. These are two issues which stems from planar distance. And it's obvious that roadway network distance is not necessarily equal to Euclidean distance. as you can see here in this picture. So in this research, we used SANET to avoid this issue and obtain more accurate results. In order to investigate the crash density pattern for two age groups, that is between 16 to 22 and 23 and over, we developed a density ratio difference, which presented by Ulak in 2017. Using this metric, we would observe the spatial pattern of youth involved crash and detect age group specific hotspots. This figure illustrates the location of counties selected in this research as the study area. These counties will be selected based on their high crash rates with respect to their youth population due to the great number of colleges and universities. You can see the location of the colleges and universities on each map with blue dots, and we intend to investigate whether there is a particular crash density pattern around campus area in these counties. Also, based on this table, Alachua, Duval, and Leon County have a great number of educational centers. For example, University of Florida and Florida State University, located in Alachua and Leon County respectively, have a noticeable number of enrollment. Since these two counties have distinguishing factors of a college-oriented counties, whereas Duval County, which is a metropolitan area, but still it has a considerable university population, despite we consider this county to make comparison between results. This figure also shows you Leon County, Alachua, and Duval are among the counties with a high rate of youth involved crashes. Yeah. This map shows the density ratio difference, DRD metric, based on planar distance KDE in Leon County, and these dark red identify the location with high density for youth involved crash based on the legend here. It's obvious that there are a significant increase around universities campus in this county, but we couldn't identify the exact location and road with high density. So we have to use SANET to evaluate this assumption accurately and identify the exact location where a youth involved crash density increase comparing to the other age groups. But still we can find that there are some increases around university campus in this county. Also for, let me show you next step, for Alachua County provides the same results for Leon County due to their similar characteristics. Again, there are some increases around university. You can see University of Florida in this county, but for Duval County as the metropolitan area, metropolitan county, that follows different pattern in comparison with Alachua and Leon County, as we expected before. There are some decreases in youth involved crash density around universities, as you can see here with dark blue-red area, and in some part of the county, and some increases which are far away from the university campuses, but still there are many increases and many hotspots around university areas. In these slides, R&D-based KDE, R&D stands for roadway network distance, and KDE for kernel density estimation, results for Leon County shows more detail for hotspots. Based on the location shown by red color, intersection needs specific attention to improve road safety and prevent crash, and also this 3D view. Let me show you this map. You can see this area in 3D view here, which depicts the difference between planar and R&D methods. You can see the planar results in perspective view and R&D based methods as 3D view on top of it. The overestimation associated with segments, which are along, which are among the ones with low KD are illustrated here. Moreover, paths that lead to university have a higher KD for use-involved crashes. The Florida State University has been shown on this figure. Also for Alachua County, we can obtain the same results, and in a 3D map for Alachua County is illustrated in this figure. You can also find the University of Florida in this map, and it's crystal clear that the highest KDEs belong to the roadways that leads to university. Also for Dual County, which follows somehow a different pattern for use-involved crash density. Again, you can find some high KDE values around the university. Can see University of North Florida and Jacksonville University in this county, and these high-risk segments here in these slides. In conclusion, let me sum up the main findings here. Based on DRD metric, the hotspots for use-involved crash densities appear to be different to those of other age groups. We found that there were some increase in use-involved crash density around campus area. First, we employed planar distance-based KDE to conduct this analysis, and that resulted in over and underestimation for crash density, since network distance-based KDE approach was used to avoid this issue. Key findings provide that the use-involved crashes and area with high use population are highly correlated. And in this research, we consider campus area as a location with great number of use population aged from 16 to 22. So we concluded that a noticeable number of use-involved crashes occurred along a segment that leads to campus area, particularly in college-oriented counties, meaning that the spatial allocation of use population around university have a significant effect on the likelihood of crash to be use involved. Based on accurate results obtained from R&D-based KDE, use-involved crashes tend to occur more in the presence of intersections. The results of this research can be extended in the future by a statistical model to identify the significant factors behind these crashes, and this can help researchers to better understand the prominent reasons explaining these crashes and focus deeper on used driver behavior. And some finding of this research may be site-specific. Therefore, another interesting area of research is to expand this research to other locations, also categorizing crashes into various types of crash would result in more detailed information based on use population behavior. Thank you for your attention, and now I'm happy to answer any question you might have.
Thank you so much, Mohammed Reza, for your presentation. Great study and great job. And as Krishna said, great visualize. And yeah, just the first question, thank you so much. The first question, Mr. Luxman said, how do you plot your 3D? Because I think all the participants like from your visual, presentation. You plot your 3D plot in, for example, ArcView or not?
Actually, I used ArcScene in order to plot this 3D view, and yes, I export the data from SANET and import them into ArcScene and extrude them with. Actually, I tried some values to exclude them and create these 3D plots using ArcScene. Yeah.
Thank you so much. As you said, there urbanization are growing fast, and the first outcome of this rapid urbanization or accident, as you say, the first cause of this between the age 15 to 29, it's the World Health Organization is related to the accidents, and this is really important, and your study will be so important for this point. You know, I saw that you used the data, but the first question, can you say that in your future study you can, for example, extend your data, for example, to all the regions in the US or something like that?
We can try that, but in this case, we just need to make comparison between college-oriented counties which, based on their population. We know that, for example, for Lyon and Alachua County, their population is around 200,000, 300,000, and we couldn't consider these counties as metropolitan area. We just want to make comparison between these type of counties named college-oriented and metropolitan area, which dual county in this research. But yes, we can expand this research into other counties in future work. We are still working on this. Yeah.
And also, Mr. Laxman said also, how have you taken care of crashes around intersections, as some of them can be counted more than once?
I'm trying to get this. You mean the last question, yeah? What is the sense of how the...
Yeah. I mean, avoiding double, no, not the last question.
I'm trying to get your. Sorry, I can't get your question. Could you please...
Yeah, I repeat it. Mm-hmm. How have you taken care of crashes around intersection? This is because as some of them can be counted more than once. I mean, avoiding double counting of intersection crashes. Thanks.
But actually, we count each point as a crash, and I think it's not double counting. Each point represents a crash. So if we have 10 points around intersection, it means that we have 10 crashes which is occurred around intersections. That's why it's not it's this issue. It's not a double counting. Each point is a crash, which is occurred around an intersection. And based on the 3D view, we found that around intersection that is located around around university's campus area, we found that these intersections needs urgent attention in order to improve the safety around universities. But there is no any double counting or anything like that. Each point is represents a crash around intersection in this research. Yeah.
Thank you so much. And from Dr. Chng, what is your sense of how the profile of youth-related crashes demonstrated by your research differs from those involving other groups?
Actually, this is our objectives in this research. We are trying to illustrate this difference, and we found that for these specific age groups, which is between 16 to 22, they are more concentrated around university, around campus area. But for other age groups, we found that, I can also share my screen again. We found that we can't find any increase around university for other age groups, which is 23 and over. And in these age groups, I mean 23 and over, we can find some increases far away from universities. So it's a difference between the pattern of crash density for these specific age groups. And we found that these specific age groups between 16 to 22 are more concentrated around universities in campus area, I mean.
Thank you so much. And I saw that for your future study, you say that more statistical modeling, especially knowing the significant factors. did you have any field observation, for example, in Florida, to see the logical reason of your output?
Output of statistical models or spatial analysis using GIS?
Spatial analysis. For example, you say that these types of group in this specific, for example, location are high. So why? For example, let's say, for example, speeding, yeah, or during the specific time of a day. What are the reasons that is related to your output?
Thank you. Interesting question. Actually, we need more statistical model to answer this question, but based on the results, and I said that f.data contains a lot of attributes, and we can use them to develop statistical models to answer this question accurately. But for now, I think the most the main reason is related to the population of the number of young driver around universities, and it's obvious that around campus area we have more young driver and they are more risky, and it results in more crashes. But yes, we should consider some other factors such as speed limit and their speeds, and maybe some drug or alcohol abuse, or I don't know. We should all of these attributes in order to find which of them has was more significant effects on youth-involved crashes. Yeah.
Yeah. And also, again, Mr. Luxman said a good point. I think that maybe in future study you should check, that the volume with respect to the time of the crash. Yeah.
Exactly. It's a kind of temporal analysis. Yeah, it needs for more research actually.
Yeah. It seems that you have a lot to do.
Yes,
in the
exactly.
future. Yes. Yeah. And also, I have a question. Do the U.S. government have a kind of intervention for the safety, I mean, the accidents related to use?
Actually, yes, I think I got your question right. Most of the, as far as I know, most of the policies and regulation is focusing on aging population. But maybe for these kind of area, I mean the college-oriented counties, somewhere like these ones that I consider in this research, it's better to focus on this specific age group in order to improve road safety. And in this research, we focused on youth-involved crashes. Maybe the driver in this type of crash are 23 years or over. And if we can find a way to improve these type of crash, all the community in these type of counties can gain benefits. Yes, but the most of the policies focusing on aging population now. But yes, they need to. The youth population needs a specific attention.
Yeah. Thank you so much. And just the last question I have, and also participants, do you have any questions for the last 2 minutes of the presentation of Mohammed Reza? Just the last question. For your modeling kernel, I know kernel in non-parametric modeling. For each modeling, we have 3 stages: identification, estimation, and diagnostic. For the diagnostic, do you check the error of your, for example, do you have any error? I don't know, in GIS, we have the criteria for checking the error or something, for example, to check that your model are okay or not, or something like that? Because I didn't see any of these in your presentation.
No, actually, I didn't check for error in this research, but it's an interesting idea. We can do it later. But as far as I know, we can't find I can't find any methods to check this using built-in toolbox in GIS. Maybe we can write another codes in Python or I don't know, another programming language in order to check their outputs. But as far as I know, there is no any built-in toolbox in GIS in order to do that. We should do it later. Yes. Thank you. Thanks for this great idea. Thank you so much.
And thank you to Muhammad Reza for your great job.
Thank you so much, and thank you all for listening to me. Thank you.
And Dr. Khent, the next presentation.
Okay, thank you very much, Milad, and thank you, Mohammed Reza. It's a very interesting presentation. Some great work coming out of Florida. Without further ado, our final presenter for today is Eric Dunbar, who I don't think needs much of an introduction. He's professor at Florida Atlantic University and the Associate Director of the Collaborative Sciences Center for Road Safety. He is an associate editor of the Journal of the American Planning Association, and his work generally spans the domain of urban transportation, including planning, policy, engineering, and design. Over time, he's received the profession's premier scholarly accolades, including Best Paper Awards from the Transportation Research Board of the National Academies of Science and the Journal of the American Planning Association, among others. So Eric is going to be speaking to us today about income disparity, crash risk, and the built environment. So take it away, Eric. Thank you.
Thank you. I think I've got it up now. Yeah, income disparity, crash risk, and the built environment. I want to start by acknowledging my co-authors here. This was a collaborative effort with Yanmei Lee, Dr. Debakar Sahan, Louis Merlin, all colleagues of mine at Florida Atlantic University. So some background on what we're doing. It's just something we've been talking about in other research efforts for a while. It was something that we wanted to explore. When we conduct safety research, we sort of take it for granted that we need to include variables that account for the presence of lower income populations or minority populations. We drop them into models as control measures. They always come up significant. And then we say nothing else really about them, right? And the implication with this is often that implicitly that, well, something about these populations encourages them to behave in a less safe manner. And really nothing else really needs to be said about that. So we really wondered, well, okay, this sounds fine, but do these built environment characteristics differ for higher income and lower income populations? So could it be that built environment characteristics may explain some of the differences that we observe with low income and high income populations? So what we wanted to do was do the kind of research that is normally done for research into this area, but see if there's difference once we stratify by high income and low income groups. We did this for Orlando, Florida. The study was at the block group level, rather for Orange County, Florida, which the city of Orlando was housed in. You guys may be somewhat familiar with the geography. Just south of there is Disney World, which is open now if you'd like to go visit and give your family COVID. But that's not here. We're just looking at the Orange County and Orlando is study area. All right, so the next thing was we need to figure out how we're going to stratify high income and low income. So we used classifications provided by the Department of Housing and Urban Development. The area median income for Orange County is $51,586. And for policy purposes, HUD categorizes low income as being 80% of AMI or less, which in terms of Orange County's income is about $40,000 or less for the household. And high income is 120% of AMI or greater, or $65,000 or greater. So we've now got the two group definitions, high income and low income, and we categorize block groups as belonging to one or the other of those groups, or the middle group, which doesn't belong. Crash data we got from the Florida Department of Transportation for the 2014 to 2016 period. So there's 3 years of data, which lets us to address regression to the mean effects that might affect this. The dependent variables we looked at were total crashes, so the total number of crashes involving all users. We also looked at KAB crashes, which is a measure of injurious crashes, which includes fatal, incapacitating injuries, and non-incapacitating injuries. So what we did is we summed up those three types for a total of KB. And then we also wanted to look at pedestrian-involved crashes as well. So we look at the total of those. Independent variables are the ones you see in this research consistently. We didn't try anything new here. Population, which is a control, more people, more crashes. We looked at income to see if that higher incomes might affect things once you stratify between the AMI categorizations, level of college education, percentage white population, so that's white non-Hispanic. We looked at miles of urban arterials. Consistently, what this research finds is that the presence of urban arterials is a significant risk factor, so we included that. Commercial parcels, likewise, the number of commercial parcels in a block group, these are consistently risk factors. They're trip generators, trip attractors. Down in Florida, they often have driveways, so they can create conflict points that create crashes, so we included that. Intersections is typically in this research. And intersections is an interesting variable because it comes up differently in different studies. Much of the work I've done before has found more intersections at the block group level to be a risk factor. Other studies have found it to be associated with fewer crashes. Quite a few studies have found no effect. So we added that in there to see what it would do. The percentage of streets with a sidewalk. So how many streets within the block group have a sidewalk? And then Florida DOT had an interesting variable we wanted to play with, which is the percentage of sidewalks with a buffer. And a buffer is something that separates the sidewalk from the vehicle travelway. So these can be things like landscaped areas in between the sidewalk and the right-of-way that may have street tree plantings, or whether or not there's on-street parking present. So we know if that's there. All right. And then as background, is at first start, we just ran the model for the whole county to see if Orange County performs like other areas where this research has been done. And lo and behold, it does. It's really no different at all. Population, significant for total, KB, and pedestrians. Income, higher income, fewer crashes of all three types. College education, significant only for total, but that's okay. White population, the percent white, non-Hispanic there, consistently associated with fewer crashes. Urban arterials, consistently associated with more crashes at about each mile of arterial, adding up to about an extra 20% crash risk. Number of commercial uses, significant across the board. Number of intersections, not significant in these models. Percent of streets with a sidewalk, significant for total crashes in a positive way, but not for the other two. And then the last one's rather interesting, and we'll talk about this as we go on later. The percentage of sidewalks with a buffer, so that may have a landscape buffer between the sidewalk and the right-of-way or parking, consistently associated with more crashes for total and KAB. Oh, I should also add that what we use, the models here are negative binomial regressions. This is consistent with this work. It's count data, it's over dispersed, so negative binomial is what we used. All right, so that's Orange County. Now let's see how these, and this is what we really wanted to get at with this study. How does this shake out when you look at high income and low income areas exclusively? So if we go at high income, more population as you would expect, more crashes. Income, that effect is lessened. College educated, same thing, but really lessened and often not significant. Here's where it gets interesting. White population, negative, but not significant here. All right, miles of urban arterials. Remember that for the region as a whole, each mile was associated with about a 20% increase in total and KAB crashes. Here, the effect drops down to about a 9% increase. And not significant at all, by the way, for pedestrian crashes that you can see there on the right. Commercial uses, significant at the 95% level or nearly so, with a positive effect on all three. Intersections, not significant again. Streets with a sidewalk, significant for KB, but positive in all cases. And then this is one that's also interesting. Percent of sidewalks with a buffer. More sidewalks with buffers, so with those landscape plantings or on-street parking, significantly associated with more crashes in the higher income areas, not the lower income ones. All right, so this is the background for our affluent areas. How does this shake out for lower income folks? Population, Significant, as we would expect. Income, not significant. It seems like once you cross that threshold of 80% of area median income or lower, income doesn't really matter anymore. You're in that low income group. College education, significant for pedestrians, negatively. This is very likely young professionals more likely to walk in the urban areas of the region. Now, here's where it really gets interesting. Look at this now for white population. Doesn't matter how many people are white in upper income groups, but for lower income block groups, higher percentages of white is associated with significantly fewer crashes. To state this another way, issues of income disparity in lower income areas appear to be exacerbated by issues of race. More non-whites, more crashes. Miles of urban arterials. We saw the effect that declined when we compared to the region for our higher income folks. For lower income folks, these coefficients are quite a bit larger than we saw before. Every mile of urban arterial is associated with a 29% increase in total crashes, nearly a 30% increase in KAB crashes, and a 20% increase in pedestrian crashes. Remember, too, that arterials weren't significant for the higher income folks. Intersections, not significant. Sidewalks, percent sidewalks, not significant. And sidewalks with the buffer, not significant here. The big factors for low income folks are really those miles of urban arterials and whether or not they're black or white. All right, this is a comparison. I kind of described all this for you. We'll just have this in the slides for later. So what are the big findings that we came out of here? What can we conclude after having done this about differences between high income and low income environments? Commercial uses, those effects are really the same for high income and low income populations. Consistently, they're negative. They're something that we want to address through design. Urban arterials, on the other hand, and mind you, particularly here in Florida, we focus a lot on arterials for safety, but the problems of these roads are much greater in lower income environments than higher income environments, and we compare them against each other quite a bit so. So in lower income block groups, each mile of urban arterial is associated with 300% more total in KAB crashes and 3,800% more pedestrian crashes. And I should also note that for higher income groups, arterials didn't prove to be significant for them at all, right? This is just me running the coefficients against each other. And I think the reason for that is if you start running some unpleasant arterials in higher income environments, these folks just choose not to walk, they'll drive. Lower income folks don't have that flexibility. Sidewalks and sidewalk buffers. This also is an interesting thing, particularly for sidewalk buffers, and we found them associated with increases in total in KAB in higher income populations. What I suspect is going on here is this is associated with the more urbanized section of the city of Orlando, which is on the northern edge of the city, that often has a lot of these features and is trying to balance them out against traffic volumes. It creates a risky environment because they create more conflicts. But the data doesn't quite sort that out yet. Lastly, race and income. I want to underline this again, that once you reach a certain level of affluence, right, that 120% of area median income or higher, race doesn't seem to be a particularly significant factor in terms of crash incidents. But in those low income block groups, it is, right? In those low income block groups, more whites is associated with fewer crashes, or conversely, higher proportions of non-white populations are associated with more. And you can also see that these race issues stratify in those block groups. That's what this table shows you down here, right? For lower income block groups, there's only an average of about 45% of the population that's white. And significant areas of them have a population that's totally non-white. Consider higher income here. The average is about 83% white. So issues of race and class clearly are a factor here in understanding what's going on with safety. Just a few concluding points I want to get here. So what did we find out? Issues of urban arterials are more problematic in low-income environments than high-income environments. And this raises a point that we don't get at in this study, but we need to look at, which is there's a big push to start taming our urban arterials to make them more livable, more pedestrian-friendly. But a lot of these efforts tend to go into areas that are already more affluent, already more advantaged. or towards areas that are looking to be quote unquote revitalized, right, where we're looking to target new development. So it may well be that the types of strategies we put into place to address arterial safety may be directly designed to advantage higher income populations rather than low income ones. That's something that needs to be looked at later. Same thing with sidewalk buffers. One would expect these things to enhance safety. We didn't find that to be the case here. And interestingly, it wasn't for pedestrian crashes that they were a problem. It was for all crashes and all injury crashes. These are ones involving vehicles. So there needs to be an examination into how the presence of these features may issue things like intersection sight distance or intersection movement and the like. And then finally, the presence of non-white populations appears to exacerbate income-based disadvantage, right? So to conclude all that, issues of income and race, as one would expect, clearly commingle in these results. And that's sort of a sum of what we have here. So I'll go ahead and turn it over to questions.
Yeah. Thank you so much, Dr. Rick Bong, for your great presentation. It's really interesting to know the impact of economical problems on the accidents. You told really great for the impact of high income, low income, let's say even infrastructure like the number of intersections, percentage of whites, and the relation between let's say the income and low income and accidents. Participants, do you have any questions? Okay, I have a question, Doctor. In middle income countries, as I know, the government want to use, for example, the economical factors to reduce the crashes. For example, like increasing the cost of fuel, and they want to explain that increasing the fuel cost may decrease the crashes. So, according to your outputs and the results, do you confirm this fact?
I'm not sure I quite follow that. Could you, what should I confirm or disconfirm? I'm not sure. I'm not quite sure I got that. And I've done quite a bit of work in low and middle income countries, but.
Yeah. Because you, for example, work on the income and low income and, the middle and the high income regions, and the impact of the economics on the accidents. So do you, for example, can have a kind of correlation between, for example, let's say increasing the fuel costs as a kind of economical factors to reducing the crashes? Let's say, is it possible?
Well, I guess I should take a step back. And when we're dealing with Orlando, we're dealing with an area that is almost entirely personal automobile use. Everything else is comparatively low. Where when you're dealing with low and middle income countries, the distribution of crashes are quite different. The big problems there are pedestrians and in particular motorcyclists. I've been doing some work with motorcycles are tough because motorcycles, they have all the vulnerabilities of your pedestrians, but they move at the speed of motorists. Our speed control measures don't really work particularly well for them. So with that, I would put a caveat on trying to draw conclusions from this research to the specific problems of low and middle income countries. That said, I think a lot of what we're seeing that these results are reflecting are not necessarily behavioral level issues. Some of that may be involved here, but I think it's a matter where we direct our safety investments. So when
thank you.
Yeah.
Thank you so much. It's not related to the directly to research, but because it's related to economical problems, just I ask that, and thank you so much for your explanation.
Okay.
And Krishna told that would it have been better to model the data simultaneously while interacting income and other variables? Was this done, or was it two different data sets based on low and high income block groups?
Let me see if I can bring that question up, because it's hard for me to, my screen's all kind of weird now. Where's the, see if I can find the, I guess I have to stop sharing to do that. There, hold on. There we go, now I can see the chat. Let me see the chat question, yes, so I can answer that.
I'll repeat it, or?
Model the model data simultaneously while interacting income with other variables. Good question. Honestly, I don't know. We didn't do that. We had 3 data sets. We had one for Orange County as a whole, and then we had 2 separate data sets, one that was just lower income populations, another that was just the higher income, and we ran models on the 3. So we ran 3 different sets of models. My colleague, Dr. Saha, he actually, I don't think he's on the call today. I think he had something else going on. He'd be the one to ask about that. He's my modeling guru. So he'd give you a much more intelligent answer than I think I'm capable of at this point.
Thank you. And another questions? Yeah, Dr. Chng say that, can you talk through some of your ideas, feelings and results related to sidewalk buffers?
Yeah, yeah, my gut feeling on this, I think it's revealing that it's not the pedestrians that are involved here, that it's the total and KAB crashes, which means that something going on in the design of these facilities is affecting multiple vehicle interactions. I do believe that a lot of this stuff gets lumped in without a lot of thought to design. It's been a while since I've been through Orlando, and I'm certainly not going to be there anytime soon.
Yes.
But they'll often bring, for example, they'll bring the on-street parking all the way up to the edge of curb, and that creates a sight distance obstruction. They also have a tendency to put these things on multi-lane roads, and they'll permit unprotected left turns. So I think the combination, if we were to break it down more finely, of sight distance obstruction and left turns, multi-lane roads, and the like, I think that's probably what's driving it. I mean, the way to get at that would be to get at multi-vehicle crashes occurring at intersections. Particularly if I had to take a guess, they're going to be angle crashes.
Yeah.
And that's certainly going to drive up the KAB results, but we didn't have that data, and I didn't look at that. But I suspect it's going to be a confluence of those things.
Thank you so much. And also, Dr. Chng said that it might be interesting to look at other ways sidewalk buffers were treated.
Yes. Yeah, we didn't stratify them based on type. We didn't get any measurements of anything. I did some of that work ages ago in my dissertation. And if it really the issue was the relationship of intersections to approach speed that was causing the real problem. Wasn't what you would expect to happen. It was all multi-vehicle and vehicle running off the roadway and back a curb because of the high approach speeds. But yeah, I agree. I think that's exactly right. And that's another step that we need to go with this.
Yes. Thanks for your answer and questions.
All right.
Well, it looks like everyone's pretty satisfied with that presentation and with your responses, Eric. So do you think Milad, should we wrap things up?
Yes, I think, yeah, we don't have any questions. And also thanks for all the presenters for the great presentations.
Yeah, I agree. Some really interesting methods being used to all sorts of research questions and problems that, you know, urgently need to be explored if we're going to seek to make the way that we travel a little bit safer, and in particular to promote modes alternative to the private car. So on that note, I think we'll say good night to those of us who were there in the evening, and welcome to the day, those of us who
Yes.
are just starting off their days. And hopefully we can keep these conversations going after the conference. And I'll leave you all to the rest of your days. Thank you.
And thank you too. In Iran, it's almost 2 a.m. And also I should thanks for all the organizer of this conference. During this pandemic and COVID-19. So these conferences are really great to share our ideas and thoughts and also results to know more about each other. Thank you.
Thank you very much. Bye, everybody.